multi-sensor SAR amplitude imagery, presented by Arthur Hawk.
Hi everyone, thank you for being there so early. So my name is Arthur Hawk, and I'm a third-year PhD student at IPGP in Paris. In this presentation, I'm going to show you an overview of the work I did during my PhD about the measurement of ground deformation and the reconstruction of topographic changes from multi-angular and multi-sensor SAR amplitude imagery. So as you see, we won't talk about phase or fringes in this presentation, but I'm still half in the topic of this session because we will talk about volcanoes. So as most of you know, I guess, to assess the state of activity of a volcano, one key parameter is the ground deformation that can be first measured using ground-based instruments on a daily to sub-daily basis. So with such instruments, we can build time series, such as the one you see here on the upper right plot. This is an electronic distance measurement that measures the length of a baseline between an emitter and a receiver on the ground on the Merapi volcano in Indonesia. And what you see is that before the 2010 eruption, the deformation was quite steady in about 1 month and a half, and there was a sudden acceleration just 5 days before the eruption. So we need to detect such transient sudden events, and therefore we need to have the daily temporal resolution. But when the eruption is occurring, it may be too challenging to reach the stations because they may have been destroyed or because they may be unreachable. And therefore, we also need to rely on other observations, such as space-borne SAR imagery, which has the advantage of penetrating through clouds and plumes. And as you know, to measure deformation with SAR, we use interferometry, and to build an interferogram, the constraint is that we need to have a strict repetition of the acquisition geometry, which limits our revisit time to about a week. The goal of my PhD was to develop new methodologies in order to decrease this revisit time using a multi-sensor approach, which poses the challenge of having a changing geometry and sometimes no reference image at all. So on the figure on the right, you see basically visually what it will change in the game. It's like usually we have what you see on the upper part, so the same sensor with the same geometry with a weekly revisit time. And in this case, the changes you will see between one image and the next one are only due to actual changes that occurred on the ground. But when you want to reach the daily basis, you need to combine multiple sensors with multiple geometries, and therefore when you will compare two successive images, some of the changes will be due to actual changes on the ground, but most of the changes you will notice are linked with changes of the sensor and of the geometry. So then the point is to disentangle those two sources of changes and to find a way to compare such dissimilar images. To make this comparison, we propose to find a common reference to all these images that we will find in a pre-eruptive digital elevation model that can have been acquired months to years before the eruption. Then the eruption starts, and you get your first co-eruptive image that comes with its metadata. You can combine this information on the acquisition parameters with the pre-eruptive digital elevation model to make a simulation of a synthetic image which corresponds to what the satellite would have seen if it had passed over the volcano with the same geometry but at the time of the DEM. We will use this synthetic image as a reference, and we will need to compare it with the real SAR image to see what has changed between the two dates. To make this comparison, we use the image correlation technique, which outputs two shift matrices, one along the orbit of the satellite and one along the line of sight of the antenna. And we also have a correlation score matrix that will map the places where the two images look the same and the places where they look different. And doing so, we will be able to map surface changes, such as lava flows in the case of an eruption. So this will be the first part of this talk. And in a second part, I would like to focus more on smaller scale topographic changes, such as this isolated volcanic cone that you see here, because we want to also know what's like the topographic changes occurring at the vent. So here you see that the volcanic cone was present in the real image, but not in the synthetic one. And so what we will do is we will artificially modify our digital elevation model to solve an inverse problem reconstructing the structure. So let's start with the first method, the change detection method. How does it work? Here you have a synthetic image. The scale is given here, so 100 meters. And in this synthetic image, you can see several structures. So valleys, ridges, bumps, and dips with sizes ranging from a few meters to a few tens of meters. And if you compare it with the real image we got afterwards, there are some markers that you can recognize that are in common between the two, such as this valley here. And so these markers, we will be able to track them with image correlation, and therefore we will get access to the ground displacement in this area. But if you look more carefully in the lower right part of this real SAR image, you see that here you cannot find any common marker because the surface got changed by the emplacement of a lava flow. And this is very well translated in the correlation score matrix because you see a sudden drop of the correlation. So in these areas, we won't get access to the deformation. We first wanted to validate the method and check that we were actually measuring ground deformation. So we did a validation study over the Piton-la-Fournaise volcano, which is kind of our French Kilauea in the sense that we usually use it to validate the methods. Piton-la-Fournaise is in La Réunion Island in the Indian Ocean. Here in the background, you see the digital elevation model I used to simulate the synthetic images. And on top of it, you see a footprint of a Capella space image. So I applied the method to this image, and as output, I got two shift matrices, one along the line of sight, one along the azimuth. If I use the whole dataset we have, it's made of 6 Capella space images with very variable looking geometries. So in total, I got 12 independent components of the displacement field, and I could solve an inverse problem to retrieve the 3D displacement field of the volcano between 2018, when the DEM was acquired, and 2022, when the SAR images were acquired. So the color map shows you the vertical displacement, and the black arrows shows the horizontal components. And to make the validation, we collaborated with the Piton-la-Fournaise Volcano Observatory to get their GNSS measurements and to make so point-to-point comparison that you see on this scatter plot here. So on the y-axis, you have our results. On the x-axis, you have the GNSS. And you see that for all the components, they fairly match. And this allows us to evaluate also the precision of our method, which in this case is of 10 to 20 centimeters. So of course, if we compare it with INSAR and GNSS, we are far less precise. But it will be suitable for very sudden, large deformation. And the good thing is that it allows us to use any high-resolution SAR image, no matter if we have a reference or not. And therefore, it can help us reduce the revisit time to about 1 day instead of the order of 10 days for INSAR. The other result of this study is the 2D mapping of lava flows. So here on the left, you see 3 correlation score matrices obtained from 3 images acquired during an eruption with 1 day interval. If you geocode these correlation scores to bring them back in the longitude-latitude coordinates, you can recognize the same lava flow, but its morphology is evolving through time just because the eruption was ongoing. Again, we validated these outlines with the outlines from the Volcano Observatory. And so this shows that this method is also suitable for tracking changes in the dynamics of the eruption. We even realized that in a very specific case, which is the initial phase of the Mauna Loa 22 eruption, we could even measure the 3D shape of the lava flow. So not only the horizontal extent, but also the thickness. So this is a bit contradictory with what I said before, but I told you that I cannot have any displacement measurement where the lava flow is in place because the correlation score just drops. But in this very specific case, you see in the synthetic image, you have some lineaments here that you can somehow retrieve in the real image, especially in the area where you have the 2 yellow arrows. And so here in the correlation score, which is on average low because of the lava flow, there are some markers that are well correlated that we will track along slant range, and we will convert this slant range shift to vertical shift that will give us a measurement of the lava thickness. So this is the lava thickness map we obtained with this method. We compared it with the ground truth given by a digital elevation model difference, and this is the comparison between the DEM difference and our method. And so to the first order, they fairly agree up to a certain thickness. This made us think also about scenarios of lava emplacement to try to explain how, when you emplace a lava flow, you can still preserve the pre-eruptive topography just by coating the terrain. We started touching a bit the 3D reconstruction with the last example, but this is not systematic. It was a very particular case. And now we want to move towards something more general to make a 3D reconstruction of topographic changes using inversion. and we will now focus on structures that are forming at the vent. So why are we interested in these structures? Because they are the most informative to anticipate the evolution of the eruption. In particular, if you consider a dome-forming eruption, so tracking the morphology of the lava dome with time will help us anticipate the transition towards an explosive regime. This is what has been shown by Joale and colleagues in 2023 on their paper of the St. Vincent 2021 eruption. So they used different star backscatter images coming from different sensors. They applied the radar clinometry method to it, and they managed to get a DEM time series of the lava dome that was growing at that time. From this DEM time series, they could extract a dome volume time series that you see on the upper plot. And so this is the only end of the time series, but what they saw is that for about 3 months, the growth rate was quite steady, and just 3 days before the explosive phase, they measure a sharp acceleration of the growth rate. So again, a very sudden event that we need to be able to detect by having DEM time series with hopefully a daily temporal resolution. And so radar clinometry is one of the ways of doing it, but the challenge is that it fails in layover areas, and as you know, slopes may be steep on volcanoes, so layover may be very present. So we need to have a complementary approach that also exploits the data in these layover areas. This is the method we propose to use, so it's an inversion, also based on the principle I showed at the beginning. So what we will do is that we will modify our digital elevation model until the synthetic images match the real images. The first approach we can have to solve the inverse problem with very few parameters is to consider that the structures we want to reconstruct can be approximated by assembling simple geometric shapes, such as cones or domes with circular or elliptical bases. For instance, a volcanic cone can be approximated by a positive truncated cone and a negative cone that will form the crater. Once you have your synthetic volcanic structure, you can incorporate it in your pre-eruptive digital elevation model. You obtain a modified DEM from which you can recompute the synthetic images and see how far you are from the real images you got during the eruption. Then you need to explore the parameter space to find your preferred model. A first way of doing it is to do it by hand interactively with this interface I developed. So each time you will change a parameter, you will recompute on the fly the synthetic images, and then you can converge toward the real observations. And you can also do it automatically by guiding the exploration using a metropolis algorithm, for instance, starting from an a priori volcanic cone and iteratively converging toward your preferred model, which in this case is given by the yellow lines. And we see here that the method fairly well reconstructed this volcanic cone of Piton La Fournaise, of which the ground truth is given by the black line. So what I just showed you works well for simple topographic changes in the sense that we only have to add or remove one structure from the pre-eruptive topography. But in some cases, several events may superimpose and the topographic changes may be too complicated to be approximated with the former method. So we need to change the inversion scheme by having this time each DEM point elevation as one parameter to adjust. So this multiplies by 1,000 the number of parameters we will have in the inversion. So we need to rely there on more advanced methods for exploring the model space. And one of this method is the radar fields one, which was developed by Thibaut Heret and colleagues in 2023. And this is an extension to SAR imagery of neural radiance fields that you may have heard of, which is a 3D inverse rendering method based on the optimization of neural networks to reconstruct scenes from multi-view optical imagery. So radar fields was developed in 2023, but for now it was only validated on synthetic cases, and this study I will present to you is the first one trying to apply it to real SAR data to see how it performs in this case. For validation of this method, we started from a volcano we know quite well in France, which is the Soufrière de Guadeloupe volcano in the Lesser Antilles, that has a very nice lava dome that you see here on the reference DEM. We carved artificially this DEM to form a synthetic collapse structure, and then we used 2 TerraSAR-X images, one ascending and one descending, to reconstruct the shape of the dome and see how far we are at the end from the reference. If you use only one image, you see that half of the dome is fairly well reconstructed, but the other half is completely missing, the one that is in the dark. But there is already one good thing, is that in the layover areas, we already have some good performances, so it means that this will be complementary to the radar clinometry method I just mentioned at the beginning. And when you only use 2 images with complementary geometries, we reach a vertical precision of about 15 meters, compared to 300 meters that we removed at the beginning. So it's like 5% error. After this validation step, we wanted to apply it to a real case eruption, that is the Fringe2026 eruption in Russia. So in this case, what happened? So before the eruption, there was a large lava dome forming the summit of the volcano, and the 23 eruption started with a large explosion that completely cut the summit of the volcano, forming a large explosion scar that you see here. And afterwards, in this scar, there was the formation of a new lava dome. So here you see the superimposition of several events. And without the method of radar fields, what we had was a pre-eruptive knowledge of the topography given by the Copernicus GLOW 30 DEM, and the final state of the eruption with this digital elevation model built from Pleiades stereophotogrammetry given by colleagues in Russia and Germany. So we had only a static view with the initial state and the final state, but nothing about the dynamics of the growth of the dome during this eruption. And this is where radar fields come to play and can be complementary to other techniques producing topography measurements. It's because it helps us exploit some SAR images that may have been acquired during the course of the eruption to build intermediate digital elevation models and therefore densify the DEM time series. Here, this is the intermediate digital elevation model we obtained from the joint inversion of a Sentinel-1 image and a Capella space image. And if you compare it with the initial state, the main change you see is a negative elevation change just due to the fact that the summit of the volcano was completely cut at the beginning. Then if you compare it with the final state 1 month later, on the dome, you see a positive change because the dome has grown. Around the dome, you see a negative change that may be an artifact due to the fact that we over-smooth because we need to apply some regularization at some point in the inversion. So yeah, just to conclude about radar fields, the good thing is that it will help us densify DEM time series during the changes that are occurring in the eruption, and therefore we will gain insights into short-term eruptive processes. So to conclude, we wanted to decrease the revisit time. We propose to use a multi-sensor approach that poses the challenge of having a changing geometry and sometimes no reference image, so we couldn't compare SAR images with other SAR images, and instead we had to compare SAR with digital elevation models. We developed methodologies to retrieve deformation, lava flows, and reconstruct topography out of it. Here are the references I used in this presentation. I thank you for your attention and would be happy to answer your questions.
We have time for a couple of questions. Francisco?
Thank you, Arthur, for the presentation. There is something I did not understand about the methodology. All these images are acquired from very different orbits and very different look angles, so you sort of are like orthorectifying them with respect to the original DM? Is something like that?
No.
No?
No, but I mean, I can understand it's confusing. So the point is really that because the DEM we have may be too coarse or not up to date, and some images are like below 1 meter resolution, we don't want to degrade the quality of this data by wrong geocoding. So this is really the idea of the first slide, is that instead of geocoding the images, we project the DEM in the image geometry. You see, that's the difference here. This step on the left.
But if you project them, you are just getting the DDM projected onto the radar geometry, and the radar geometry is still different for every image.
Yeah, exactly. So what you will get, if you look at, for instance, the lava flow mapping example here, so you have 3 geometries. Mm-hmm. And so we do the geocoding, but afterwards. So first we detect the changes with the highest resolution we have to make sure that the only changes we detect are really due to the different bit of the topography, basically. And then we just geocode for visualization and comparison. But otherwise, no, yeah, you're right that the images stay in their own geometry, their own native range Doppler geometry.
Thank you.
Shani?
Yeah, thanks for a very interesting presentation. I was thinking about the lava thickness. What exactly you measure? Is it the thickness of the lava above the ridge, and then you somehow extrapolate, or can you explain it a little better?
Yes, so of course, this was a bit unexpected first. So yeah, as you see, those markers that we managed to track with higher correlation scores than the surrounding are very isolated, especially in this area here. So you see, even if the correlation score is only higher here, actually the ridge, you can follow it a bit on a larger scale. So yeah, overall, they will be isolated. And of course, here there is also an interpolation step in between. So it's much smooth, yeah.
So you assume that it's flat on top, or?
Yeah. So yeah, in that case, because I do a linear interpolation, it's kind of flattening the surface of the lava flow. But otherwise, I would say also that what is most affecting our measurement is the thickness on top of these ridges or of these bumps, where the lava thickness may be the lower compared to other places. So it's kind of the lower bound of this measurement, of this lava thickness measurement.
Thank you.
Okay, well, we should move on to the next talk. So the next talk will be resolving 3D deformation of Piton de la Fournaise enabled from dense multi-geometry ALOS 2 acquisitions by Delphine Spinella.
So, good morning, everyone. I'm glad to have the opportunity to present today our work that was made possible thanks to the project of cooperation between ESA and JAXA that allow us to have an exceptional dataset of ALOS 2 acquisition. So let me first present the study area. So again, Piton de la Fournaise volcano, like Arthur said, the French Kilauea. This area is very interesting because it is one of the most active basaltic volcanoes worldwide, with a variety of geologic process. So we have the volcano deformation, but we have also flank sliding, we have gravitational processes. And also, it is one of the best monitored basaltic volcanoes worldwide, thanks to the work of the IPGP OVPF Volcano Observatory. And here you have on the map the black triangles that show you the position of the GNSS station. If we go back in time, INSA is a very good method to map deformation field, but the weakness resides in the fact that it's only what you measure is the projection of your displacement in a loss. In order to have access to the in fact, Peltier collaborators in 2015 were able to access to the 3D displacement by combining enough line-of-sight geometries. The key assumption here is that all recorded deformation is sudden and syneruptive, and so that interphogram at different dates are capturing the same event and could be inverted jointly to retrieve the geometry of one single event. The limitation here is that it is restricted to single well-isolated eruptive events, so we cannot access to continuous 3D time series, and we cannot access to transient signal of subtle interior eruptive. When we speak about time series, we are doing it in line of sight. We are doing it in quasi 2D, so in fact we assume that north-south is negligible, and that because of the subpolar orbits, the north-south, the measurement of INSA is not very sensitive to the north-south displacement. Or you can have access to 3D in some very particular case by adding constraints to your inversion problem. For example, if you work on a landslide, you can assume that displacement occurs in the slope direction. You can put in the inverse problem the slope gradient, and you will be able to solve for 3D deformation. But in a volcanic context, you can have significant north-south motion, for example, when you have dike intrusion, and you have no reason to assume that displacement will occur along slope. So if you are doing what most people do when you have two loss, you could end with bias S-west and vertical displacement. In this study, we benefit from an exceptional multi-geometry ALOS2 dataset. We have more than 1,600 images that cover 4.5 years between April 2021 and December 2025. We have 22 loss geometry, right ascending, right descending, left ascending, left descending. It is spotlight, so we have high spatial resolution. It is L-band, so we keep coherence over vegetated area. And if for a single mode, a single loss, we have a return time of 14 days. But when we combine all the 22 loss geometry, we are able to have, in fact, daily acquisition. So combining all this acquisition, we are able to access the true 3D inversion thanks to the geometric redundancy with a daily temporal resolution. So let me now show you the processing workflow. So in fact, we have this incredible SciImage database, and we use Hamster to process them. The core process of Hamster is Hamster engine to do the interphogram computation. So it's quite classic. We are performing image co-registration, pair selection to go for small baseline. Then we compute the interphogram. We are doing the inwrapping using classic method like SNAFU. We detrain to solve for some residual trends. Then we geocode, and we end up with a database of differential deformation maps. What's important here is that the 22 geometry are geocoded onto a common grid so that we are able to feed the MS-BAS processor to perform time series inversion. We can perform MS-BAS in 1D, so we have the classic line-of-sight solution. We can perform it in 2D, so the classic 2D decomposition, east-west and vertical. Or we can perform the MS-BAS in 3D, and we end up with 3 data cubes, the east-west, north-south, and vertical. From those data cubes, we can derive velocity maps with standard deviation uncertainty. We can extract for pixel of interest the cumulative displacements. So what is MS-BAS? MS-BAS is in fact an invert problem. So we write it like this first equation, where the phi is correspond to the differential map, so basically your interphograms. The v correspond to the velocity you want to solve at each time, and the matrix A is what makes the link between the velocity and the displacement you measure. Of course, this problem basically is ill-posed, so you need a regularization. And what MS-BAS is doing is it implements a Tikhonov regularization to solve for this problem. So you will add to the problem a smoothing parameter lambda and the inversion order to define the matrix L, depending on your problem. If you want to minimize the displacement, if you want to minimize the velocity change from one date to another, or if you want to minimize the acceleration from one date to another. And if we analyze the matrix A for our problem, and in fact the sub-matrix A for each time in our case, we will end up with the fact that the first row here is that the rank is always 3, except for the very first date and the very last date, so that we really can access the 3D. We look at the conditioning number, and you can see with the purple dots that the conditioning number is quite stable all over the time, and the red vertical lines show you the very few number of dates where maybe the problem will be bad conditioned. But we end up with a conditioning that is quite stable over time. We are able to compute the uncertainties, and it is no surprise that the orange line that corresponds to the north-south is a bit larger than the green and blue lines that are the east-west and vertical uncertainties. And if we propagate these uncertainties to the cumulative displacement, we end up that uncertainties for north-south are 3 to 4 times larger than for east-west and up-down, but it remains pretty reasonable. So we compare here the result in 3D and the result, so the first line is east-west and up-down when we compute in 3D. The second line is east-west and vertical when we compute in 2D. So you can tell me it's not really different. But if we look at the residuals, so the residual in east-west are pretty low, and the residuals in vertical. And we now compare this residual in vertical to the north-south we extract from the 3D inversion. And the two maps are not the same order of amplitude, but are pretty similar. If we correlate on the scatter plot, if we correlate vertical versus residual on the vertical versus north-south, we can end up that there is basically 13% of the north-south signal that contaminates the vertical. So if you go for quasi-2D, you will interpret the vertical signal, in the vertical signal, something that is in fact north-south that contaminates your vertical. And the order of magnitude in our geometry is that about 13% of the north-south signal contaminates the vertical, while the east-west is pretty clean. No, we want... This is fine, but this is linear velocity maps. And in fact, we have a lot of eruption that occur, and deformation is occurring mainly in steps. Each time we have an eruption, we will have 30 to 50 centimeters of displacement. We would like to access to what happened between eruption and to isolate the long-term deformation. So we can do this by just looking at time series between the eruption, but we will have only short-term time series. What we decided to go was to, in fact, subtract the displacement, the scene eruptive displacement from all the interferogram that recorded them to reveal interruptive signal in the long-term time series. So we again have the timeline of acquisition for each eruption. So we have the red vertical lines here. We compute the interferogram for the small temporal baseline around the time of the eruption for each mode. And we perform the same as Pelletier and collaborator were doing to retrieve the 3D component displacement field for each eruption. We project this displacement field in loss, and we correct all the interferogram that record this eruption. We end with this second database of differential deformation maps. Most of the maps are the same, and the scene eruptive differential maps are corrected from the scene eruptive deformation. And we feed the MS-BAS processor with this new database. And so on the top line, you have the east-west, north-south, and vertical raw velocity maps. And on the bottom line, you have the east-west, north-south, and vertical velocity maps of the intereruptive deformation at Piton-la-Fournaise volcano. The dots represent the GNSS measurement of the OVPF. And you can see that what dominates is the eastward motion of the eastern flank of Piton-la-Fournaise, the lava flow compaction, and also here on the, what we call the cassé de la rivière de l'Est, we see a signal in the north-south component that corresponds to a geological event, a rockfall, in fact, that happened in this area. And that was still ongoing in the year after the event. Here we compare the 3D INSAR velocities with the GNSS velocities for each OVPF station. Again, first line is the raw solution, second line is the sine eruptive deformation remove solution. So we have a pretty good agreement over the whole GNSS network. The only thing we can see is that on the vertical, there is maybe an offset, but we believe that there is still some atmospheric correction we can add to the process, and that maybe will help to solve this problem. Here, if we look again at GNSS versus INSAR for 3 different stations, one is Farfield and is not moving a lot, one is the Summit station, one is the eastern flank. Again, we have the raw solution, the sine eruptive deformation. The blue line is east-west, the red line is vertical, and the red line is north-south. So you can see that north-south is pretty noisy, but on the long term, you manage to follow the trend. Yeah. And now if we go back here, you can see that when we look at one single pixel, we still have some oscillation, mainly in the vertical that is cyclic and probably seasonal. Due to atmospheric artifact. But if we look at baseline between GNSS stations, we remove all this atmospheric artifact because stations that are close are seeing the same atmosphere. And we end up with a pretty good agreement between GNSS and INSAR. The first figure shows you one specific baseline. The scatter plot on the bottom shows you the agreement between INSAR and GNSS for all components and for all the baseline we were able to compute. And the heat map shows you that for all pair of stations, it shows the scores. So when it's clear, like here, you have a pretty good agreement. When it's dark, like here, you have less well performance. So we have good performance on the summit, and basically when stations are close together, and we have baseline that degrades when they are very far one from each other, again, probably due to atmospheric perturbation. The same for the sine eruptive deformation removed. So basically we have the same things. And so we believe that this is the first 2 CD INSAR time series of the whole edifice of Piton-la-Fournaise that over 4.5 years. And it was made possible thanks to the very large diversity of geometry. We were able to remove the intrusive signal so that we will now be able to analyze the subtle long-term signal and to have a better access to the deformation of the eastern flank, trying to look for the magmatic reservoir variation. And when we go to 3D, we are able to quantify the leaking of the north-south energy into the vertical, so that, again, 13% of the north-south that contaminates the vertical in our case. And so the key is that really that we should be able in most of the study to combine diverse geometry, and the key point is to have right-looking angle, left-looking angle. So in this sense, that being able to combine Sentinel with Nissa, with later with Roselle, if the planification of acquisition is well done, we should be able to access to 3D by combining all those missions together. And for volcano, in order to monitor tropical volcanoes, Spotlight L-band really increase our capacity to have access to small features in the deformation. And one thing that is work in progress together is I told you that we are still contaminated by the atmosphere, so we decided to implement an atmospheric correction into Amster, and for our problem here, we decided that the Mango atmospheric correction that use in fact the GNSS, the installed tropospheric delay, should be the best solution for our case, because we are on a volcanic tropical island where global model usually does not perform very well. Thank you all for your attention.
I'm afraid we have to move on to the next talk. And, so thank you. The next talk is Volcano-Tectonic Signal Separation Reveals Pre-Eruptive Deformation at Mount Agung, 6 months before the eruption, the November 2017 eruption. And that is given by Denny Chi.
Good morning. My name is Danny. I'm a Year 2 PhD student from the Asian School of the Environment, Nanyang Technological University of Singapore, and today I'll be sharing about my research being carried out at Mount Agung. So Indonesia has 127 active volcanoes, more than any other country on Earth. And as someone from Singapore, this is literally in my backyard. The hazard is real, it's ongoing, and it's continuous. And my question is simple. So can we use satellite radar to detect which ones are quietly preparing to erupt months before anyone notices? And since I started my PhD 2 years ago, 10 of these volcanoes have actually erupted, and it's happening now across Indonesia. The monitoring challenge with INSA is compounded by tectonics. Along the Sumatran Arc, 48 active volcanoes sit adjacent to the Great Sumatran Fault, and 22 of them lie within 10 kilometers of it. And any INSA signal you may measure here at these volcanoes contains both volcanic deformation as well as fault-related strain. And it gets more complex at the Lesser Sunda Islands. Here, the volcanoes sit above not only one, but two major structures, the Sunda Megatrust and the Flores Backup Trust to the north. The tectonic and magmatic deformation fields are spatially inseparable with conventional INSA processing. And on top of these tectonic contamination, Southeast Asia's humid tropical atmosphere generates tropospheric noise that actually mimics volcanic deformation. This interferogram at Mount Agung in 2016 shows fringes concentrated above the summit, which is known in 2016, which is known to be a volcanically quiet year. So this actually looks like inflation, but it isn't. And distinguishing real signal from atmospheric artifacts is a persistent challenge within Southeast Asia volcanoes. And so my main research question here is, can we separate tectonic atmospheric noise as well as magmatic signals in the INSA time series to detect volcanic precursors that standard processing would miss? And to test that, I needed a volcano where I already know the answer, a well-studied eruption with independent GNSS as well as seismicity data for validation, and that is at Mount Agung in 2017. And I mainly use Sentinel-1A ascending and descending tracks from 2016 to 2018 for my main analysis, but the main method which I use in my analysis is a method called Variational Bayesian Independent Component Analysis, or VBICA. And the core idea here is signal separation. We have our observed INSAR data, matrix X, with T epochs, and each spatial map of ny by nx pixels. And then VBIC actually is able to decompose this into m independent sources, each with a spatial pattern and a temporal evolution. And VBIC can reconstruct the temporal and spatial components using matrix decomposition by when we rearrange them into 2D matrices and multiply the source with a mixing matrix and add an error term. And as we do the matrix multiplication, we can actually see that each row of the mixing matrix corresponds to the temporal evolution of one independent component, and each row of the source matrix corresponds to an independent component with each column of the mixing matrix. And in this case, the analysis was done in spatial mode. And the key assumption in this VBICA decomposition is that the sources are stationary and are mutually independent. Which brings me to my next point. When I perform the full ICA time series decomposition from 2016 to 2018, we actually see that one of the independent components picks up a mixed signal. We see a subsiding trend in 2016, followed by an inflation onset in 2017, as the magnetic signal switches on in 2017. And this spatial map actually reflects the mixture. And this is actually the stationarity problem in practice. The magnetic signal actually violates the assumption that the sources are stable through time. So actually ICA folds them into a single component rather than separating them, which motivates my next approach, which is a baseline approach where I freeze the mixing matrix and the sources based on the 2016 data only, and then project the data into 2017 forward to try to expose what the 2016 model cannot explain. So during 2016, we actually assume that the signal presence are non-magnetic and atmospheric components, and when we apply VBICA to the quiet period, we keep the stationarity assumption valid, and anything that doesn't fit the model actually shows up in the residuals in the 2017 data. But this is actually the ideal case, but in reality, atmospheric noise is epoch-specific and uncorrelated between 2016 and 2017, so the residuals still actually do contain noise. But the key still here is that genuine volcanic signal will be spatially coherent and persistent across multiple epochs, whereas the noise still remains incoherent and transient, which allows us to distinguish real signal from noise in the results. So this is the math behind the projection. Is just a simple linear least-squares inversion. And the first major result from the ICA decomposition is a spatially coherent signal across the northeastern of Bali Island. So the spatial map actually shows a broad blue lobe of line of sight displacement, and the time series at the selected pixel shows a steady decreasing trend running from 2016 to early 2017. So this spatial pattern has a steady and temporal behavior, which is consistent with interseismic deformation associated with the fluorescent back-arc thrust, which runs offshore of the island of Bali. But however, I would still remain cautious of a firm interpretation here, because the fluorescent thrust system is actually still quite poorly constrained at the west of Lombok, or in this case, north of Bali, where it actually becomes a blind fault and is primarily mapped with seismic reflection data. So the slip partitioning in this region is also not very well understood, and the literature still reflects significant uncertainty in assigning the deformation to the specific structures. But still, I can still say that this steady, spatially coherent signal in the north is consistent with the known geometry of this back-arc system, and a more definitive characterization would require a dedicated geodetic inversion beyond the scope of the current presentation. But critically, regardless of the precise tectonic origin, so the signal still occupies the same spatial footprint as the later magnetic deformation, and without separating it, any attempt to isolate a volcanic precursor would be contaminated. And because the two signals overlap in space and time, running ICA, as you saw earlier, breaks the stationarity assumption, which is why I used the approach where I looked at the baseline period in 2016. And the key assumption in this was that, 2016 represents a volcanically stable baseline period, and that the ICA model only captures non-volcanic signals in 2016. And to test this, I applied the projection using 5 different baseline periods throughout 2016, and in every case, the residuals still remain flat and spatially incoherent throughout 2016, and the magnetic anomalies only appear in 2017 once the activity begins, and this gives the confidence that the precursory signal we detect is genuinely new and not an artifact of whenever we chose the training boundary period, and it's also not present in the baseline period as well. So in the residual time series, we actually can capture the full 2017 unrest sequence in both the ascending and descending tracks. Here, the full time series for both tracks, descending on the left and ascending on the right, and each panel shows a single epoch, whereas the green bordered panel shows the training cutoff period. And as we move through 2017, we can see the residuals grow. So I'll pull out the key moments for the descending tracks on the next slide. So focusing on the descending track, with a root mean square time series of the region of interest actually shows the baseline period flat through 2016, which is what we would expect. And then on 12th of May 2017, a spatially coherent anomaly appears on the northern flank of the Mount Agung, and is localized and distinct from the noisy background, matching the inflation footprint we see in the subsequent crisis period. And this is 6 months before the November eruption, and the spatial pattern at the upper right also confirms that it's not a seen-wide atmospheric artifact where it's concentrated at the north. And critically, this onset is independently corroborated by seismicity. So Shabana et al.'s publication also document an increase in volcano tectonic earthquake rates beginning in May 2017, consistent with the timing of this anomaly in May. So this tells us that the INSA and the seismic records are telling the same story, that magmatic unrest was underway by May 2017, 6 months before anyone actually saw an eruption. While the results seem significant here, it is also important to take note that this is a retrospective study. We know that an eruption followed. So in a real-time scenario, this anomaly in May alone would be suggestive but not conclusive. It is also through the combination of the INSA signal, independent seismicity record, and subsequent evolution of the deformation through 2017 together that actually builds this confident interpretation. For a real-time monitoring scenario, this signal would need corroboration from other data streams before any operational decision can be made. When we're looking at both the ascending and descending track, actually, we still see that in the ascending residuals sort of suggests an inflation signal that may begin even earlier in February and May, 2 to 3 months before the May onset. So the spatial pattern in May also is coherent and localized to the northeast of Mount Agung, and is also consistent with the subsequent pattern seen in the crisis further later on. And also more importantly, the independent GNSS stations south of Agung also independently corroborate an inflation episode during this period. However, for the descending track, it is ambiguous over this time window. So the February epoch, actually after looking at the interferograms, it's still, I will flag it as atmospheric contamination, and because of this, we cannot confirm with both of the tracks that this earlier inflation onset will actually begin in February and March. And finally to characterize the magmatic source, I actually inverted the east-west and the vertical residual components jointly, obtained from both the ascending and descending tracks using an Okada model, a finite rectangular source in elastic half space. The top row shows the east component, observed the best fit as well as the residual of fit, and the bottom row shows the same for the vertical. So the model captures the broad uplift north of Agung reasonably well, and you can see the symmetric lobes in the east component reproduced by the Okada solution. So the best fit parameters of the give a source centroid depth of around 8.8 kilometers, dipping steeply at 75 degrees with a strike of 316 degrees, and a volume change of about 35 times 10 to the power of 6 meter cubes. The length, width, and the opening, however, are poorly constrained still, and these parameters are also consistent with Albino et al.'s independently derived solution, with giving a comparable depth, volume change, strike, and dips. And this geometry is consistent with a steeply dipping tensile source at the mid-crustal section between Mount Bato and Mount Agung. So we started with 127 volcanoes, and we questioned whether the method can work in complex tectonic and atmospheric environments of Southeast Asia. The Agung results will give us reason to think yes, the tectonic signals and the magmatic signals, as well as the atmospheric noise, appear to separate cleanly, and the precursor is recoverable. And that means we can now take this to volcanoes where we don't already know the answer. So just to conclude, the VBI-ICA projection actually is effective for separating overlapping deformation signals in complex volcanic settings. And Agung broad subsidence is likely linked to the Flores backup thrust, and is distinguished from the localized pre-eruptive magmatic inflation. This is particularly important for Indonesia, where many active volcanoes are in subduction zone settings and are strongly influenced by tectonic deformation. An advanced INSAR time series analysis can improve the detection of these subtle early magmatic signals that may be masked in standard INSAR products. And the workflow has potential for semi-real-time monitoring during evolving unrest eruption sequences when integrated with independent observations such as seismicity, gas emission, and ground-based GNSS deformation. And this approach provides a simple, robust, transferable workflow for Indonesian volcanoes and other tectonically active volcanic regions. And the next step for me will be to implement this, to test this workflow at other volcanoes in Indonesia. Yeah, my references, and thank you.
Thank you, nice talk. We have time for some questions.
I would like to ask you a question that is not scientific, but given your conclusion, do you see any stakeholder interested to support the operational monitoring of your capability, because that will have cost in terms of observation and processing? Yes. With IT power to provide this continuous measurement?
Yeah, so in the acknowledgements, one of the person I met is Park Devi. So he is the main person in charge of the crisis during the eruption in 2017, and I had actually shared the results with him here. So he did mention that with the results here, it would have been helpful at the time of the response of the crisis. So I think it's something that is definitely reasonable for us to share with the stakeholders to try to see if it's possible to develop any form of collaboration between the research that I do, and as well as the stakeholders on the ground, to see if we can lead to a more comprehensive monitoring in the situation at the different volcanoes in Southeast Asia.
Okay, I wanted to ask about your newly detected precursory signal, and could you say something about the relative magnitude of that relative to the dike intrusion signal that's been seen before?
So the magnitude
relative
of the
magnitude. How big is this new precursory signal relative to the dike intrusion?
Yeah, so in this case, the magnitude in this case is about 6 centimeters that appear, but yeah, it is much, I would say it's not about 4 centimeters, and the subsequent crisis during September, it increased up to about 6 centimeters in this case. So the precursory detection here, I would say, is not as significant as the subsequent crisis that occurred in September.
Okay, thank you.
I have one quick question as well. Regarding this, the subsidence due to the Flores thrust, do you think it'd be possible to extend your analysis to the adjacent island and somehow, if you're able to keep them on the same phase ambiguity, solve it for that same signal going to the other island? I'm curious how continuous it might be.
Yeah, yes, definitely that is something that I can test out as well, because the other island is where the subsequent Lombok earthquake happened in 2018. So it could be that these two signals and the subsequent earthquake are related. So yeah, that's a good point. It's something that is worth exploring to see, to further characterize this potential subsidence signal.
I think it's time for the next presentation that will be made by Paul Lundgren from the NASA CPL and concerning the Kamchatka volcanic observations.
Okay, so today I'm going to talk to you about the eruption at Krasheninnikov volcano that started in early August of last year, and that was followed the magnitude 8.8 Kamchatka earthquake by only a few days. So it's one that appears to be, of course, a triggered eruption and had some very interesting signals. So, so the motivation here is that, again, this eruption started a few days after the 8.8 earthquake, and it's at a volcano that had been dormant for more than 400 years. So kind of perhaps a fairly trivial question is, was the eruption triggered by the earthquake? It seems obvious at face value. And so we decided, however, to look at both the INSAR and thermal anomaly time series. And what we found is that in fact, there is no precursory or resolvable signals in either of these in the decade or decades and years before the unrest. So, and then the main kind of the guts of this talk will be talking about the kinematic source modeling of the dikes, in which we find that there's a dike that goes into the upper edifice but does not erupt, that trends to the northwest. And then there's also, that was followed by a summit eruption and a north-south dike in the summit. And so one of the questions we wanted to address is, are these dike orientations, especially the northwest trending dike that didn't erupt, is that somehow related to the coseismic stress change? This was motivated because we, as I'll show, we find that the principal compressive stress change from the earthquake is oriented in a similar direction as that dike. And then what can these dike orientations and their sequence tell us about the diking processes? And so we'll show that the coseismic stress from the earthquake, about 0.1 MPa, seems too small, depending on the competing edifice, reservoir, and tectonic stresses, and that the orientation distribution of opening suggests that the dike propagated upwards from depth in what would have been, of course, a closed system prior to the eruption. And then finally, the other thing that we didn't see, we did not detect any source deflation that was either co-eruptive or following the initial eruption. And I'll point out that the eruption is ongoing today, so it was following the initial explosive eruption. There was then, it's been effusing lava for nearly a year now. And we'll show that given the noise in the data, the atmospheric noise, and the volumes that we find for the intruded magma and the extruded magma in the first couple months, that a source deeper than 4 to 8 kilometers depth would be difficult to detect. So it's not surprising we don't see that. So those are kind of the conclusions. So let me go to, so the background here, Krasheninnikov is located in the eastern volcanic front in Kamchatka, and the earthquake was down in the southern part of this, and I'll show more on that later. And it occurred on maybe easier to see here, 3 main vents that are on this kind of fissure line that our Russian colleagues have pointed out in both imagery and in field observations, and flows that went down the northeast and northwest flanks and overflowed and filled the nested craters in the northern volcano of this kind of 2 volcano system. And then Arthur Hawk, who spoke earlier, he has done some preliminary lava thickness mapping, although that's going to be refined, and presumably if we can get some more Pleiades data, we can extend that and try to see what the volume is up till this, for this past year. So there was also a study by Liu et al. That came out in Science in February of this year, and they did a seismic analysis and found, and primarily focused on the coseismic slip shown here, but they also did some stress change pressure analysis to understand whether any of these volcanoes that appeared to have increased activity, including Shiveluch, Kuchevskoy, Krimsky, whether they were, what the pressure change was from them. Krasheninnikov was the only one that had this positive pressure change, so essentially being compressed. The others were more neutral or in the opposite sign. And however, if we look at this, is from their paper, a plot of the alert levels from the Kamchatka Observatory. And all of these systems in general, as many of you might know, Gluchevskoye is extremely active, same with Karimsky, Sheveluch, they're all very active volcanoes. And all these volcanoes, this is for the month prior to the earthquake, which is shown by the red line here, they all had various states of activity. Gluchevskoye is actively extruding lava. And even though it had an uptick in alert level and activity, clearly Krasheninnikov is the one that really had, of course it was dead for over 400 years, and then suddenly within a few days it started to erupt. So it seems obvious on face value that it was triggered. So we decided, though, to look into this by using the Tarsilo Girona's thermal anomaly time series method and using his STAR software, and that does a median filtering of MODIS data. And when we looked at the Krasheninnikov relative to various reference sites, I only show it for Kikpinich, a similar height volcano here. What we find is that those two signals from those two, as in this example, are very similar, and that the anomaly is essentially flat. So we don't see any precursory anomaly in the 18 years prior to the eruption. If we look at the INSAR time series from Sentinel-1 data for the decade prior, again we see, if we look at a pixel at the summit of Krasheninnikov relative to a stable reference point, again we find that there's no signal that stands out from the noise. So again, we don't see any precursory activity from any of these. So if we look at the interferograms that span the eruption, what we see here is that the earthquake occurred here. We have data also on the 30th that I'm not showing that's even flatter looking than this one, but we don't see anything that stands above the noise. I'll point out that the fringe rate here I'm showing is at 10 centimeters per cycle. These were unwrapped and now rewrapped for the plotting. But so we have nothing here, but when we get to the first, and the eruption occurred here later on the second, that we start to see a very nice signal. On the first, we have Sentinel-1. On the second, although it's only about 6 hours later, we have ALOS-2, so we see a growing signal here. And I'll point out that it's just by inspection, it's quite obvious that this trough here to the northwest relates to a dike that's below the surface. And that the signal out here, both the positive line of sight here, as well as the slight negative trough here, really quite, as you'll see, they really constrain the orientation and dip of the dike. And then finally, after the eruption, this now is on an ascending track, so there's differences in look direction that affect how these fringes look. But we see a very strong signal over a meter of displacement just on this lobe here. And so we'll now, I'll get into the modeling here in a second. And just to complete this, there's of course more data on more dates, the 5th, 6th, 7th, that extend to before the eruption. But if we form an interferogram from the 1st to the 7th, so starting from this date to after the eruption was ongoing, we see a signal that's, of course, quite different, and it's really related to a more north-south dike opening. And so the modeling approach we took was initially to model, in this case I'm showing you for the August 2nd ALOS-2 data. We do a Bayesian approach, and we needed to solve for two dikes, one to the northwest that's dipping, one that's north-south and near vertical. And to first order, these can fit the data quite well. But once we've done that, then what we do for each of the dates, again, this is, here I'm showing you for August 1st, is that we then, we use Poly3D to generate the dislocations. We discretize it into patches, extend each of these, the original geometries up to the surface, and we have so we can incorporate the effects of topography in case they're important. And then we solve this with regularization. And what we find is that, so on the first, we have a significant opening on this northwest trending southwest dipping dike, only a little bit beneath the summit, and some of this is probably just noise. And as we go to subsequent dates, it basically stays the same. We're still before the eruption started. This has increased a bit more, but still there's nothing much happening beneath the summit. But once we go to the third, this has remained fairly much the same, but now we've got significant opening directly beneath the summit. And now if I just quickly show you these plotted on the same scale, again, you can see this quite clearly, that once the eruption starts, of course, then you have this significant opening right beneath the summit craters where the eruption occurred, and we have an increase in intruded volume as well. And these are for other dates. The only thing I want to point out is that once you go from this August 1st to the 7th, now what you see is that all the activity is beneath the summit, with maybe a little bit towards the northwest, although that signal itself is really not completely consistent between the other ones, so it's not clear how well resolved it is. So the question now, though, is what can the orientation tell us about the dike process? How about looking at the stresses from the earthquake? If we take the coseismic displacements from the earthquake, from the Liu et al. Paper, and then using Tim Davis's cut and displace BEM code. The principal stresses are shown here. Blue is the most compressive stress. And what you see is that, curiously, this is oriented, and so this would be the direction you would expect a dike to propagate in the absence of any other stresses. And so this was curiously similar to the northwest trending dike. However, if we did some analysis looking at loading stresses after Roman and Jopin, and what we find is that when you're in the very shallowest, just beneath the edifice, of course, the loading stresses are quite significant, but even by the time you're at a kilometer depth, the tectonic stresses are now on the order of 10 MPa, and they're quite higher than the coseismic stress of 0.1 MPa. So it doesn't seem likely that would have had a significant influence on the dike orientation. Now, regarding the source depth for any volume change, so is there a missing source that we could or could not see? What we find is that, well, if we look at the Sentinel-1 data following the eruption, so this is going from in early to late August through generally through October, you lose coherence eventually because of snow. And on ascending and descending tracks, what we see is that everything looks really pretty much just like atmosphere. So there's nothing that's clearly a deflationary signal. And we did some sensitivity analysis, and I'm not going to show you the details here because of time, but basically below about 4 to, and for different volumes and depths. So if you were to do, we did synthetic tests, and you could see sources when you're up in this region, but once you got below here, and for this range of volumes, that you really couldn't detect the source above the atmospheric noise. And as I mentioned earlier, our volume change was on the order, for the intruded volume, is on the order of 35 million cubic meters. However, if you consider magma compressibility, that could easily be much smaller. So it's quite easy to have a source that's in the 4 to 8 kilometer depth range and not see it. So finally, conceptually, what do we think happened here? Well, using a diagram from Geischi et al., looking at dikes that were in the geology of a volcano in Japan, we found that depending on whether the conduit was closed or open, they tended to find that for closed conduits, you would get dikes that went from depth and went vertically to the surface, whereas open conduits, you'd be more likely to get radial dikes that propagated horizontally. So it seems that from the model that we have, that the dipping dike perhaps represents magma coming from depth, that then for the eruption where we have the shallow north-south dike, perhaps it transitioned, it was fed by magma that came in and it spread laterally and upwards at shallow depth. So perhaps we're seeing some kind of combination of what's been seen in the geologic record. So just to conclude, so again, we find no precursory signals in either thermal or INSAR. However, as my co-author Olga Jurina in Kamchatka pointed out, that the long duration of the eruption, which is still ongoing, from her perspective, suggests that the system was potentially already primed before the earthquake, so such that you would have that much magma available to erupt, and that again, dike feeding sources deeper than 48 kilometers will be difficult to detect based on our simulation analysis and atmospheric noise. The 8-point earthquake stress change seems too small to have affected the orientation of the stalled dike to the northwest. I would point out that I'm assuming that there is an extensional tectonic stress based on the kind of the tectonics of the Kamchatka Peninsula. So maybe that's wrong, but and that the eruption triggering, of course, we really can't address that, but it's probably likely due to some combination of dynamic and static stress changes, as has been explored in the literature for many other systems. And then finally, the stalling of the northwest directed dike in the shallow crust and its switch to the north-south summit dike suggests a dike propagating from depth that then transitions to perhaps more of a lateral propagation in the summit. Thank you.
Any question about the presentation? There's one question down here.
Thank you, Paul, for the presentation. So I want to follow up with the conclusion about the dynamic stress changes. So do you think that, let's say, this is beyond INSAR and geodesy, but do you think that, let's say, the way that the seismic waves interacted with the plumbing system actually triggered the eruption, for example? Or how do you see how we can advance into this question of what triggered this type of eruptions?
Right. So typically in past scenarios, there's been earthquakes, for example, a long time ago, Landers stimulating Long Valley caldera, or the Denali earthquake. There's been many examples where there's been upticks in seismicity, microseismicity at volcanoes with the passing of seismic waves. The problem here is that the Russians had no seismometers at this volcano. Everything was too far away to detect very tiny events. So we really can't address that. So this is just speculation, and as you point out, the INSAR data doesn't allow us to address that. So yeah, that's something we can only speculate on.
Thank you.
Okay.
Any other question?
Let's move on to the next.
All right, thank you very much, Paul. The next presentation starts now. And this is from University of Leeds. Good morning.
Hi, my name is Camila. I'm part of Deep Bulk, an ERC project led by Andy Hooper. And the work that I'm presenting is part of a contribution of a lot of the team members. And it's an effort to try to forecast INSAR-based volcanic deformation using deep learning methods trained in complex dynamical models. So the main aim of this project is to create tools that are useful for volcano observatories and use the knowledge of how volcanoes behave globally to automatically identify the formation locally and also try to forecast how the deformation will evolve in a volcano. And this is the topic of this talk. So the deep learning network has been trained for one side with real deformation time series, and on the other side in simulated time series. So for the real deformation time series, we are using the LIXAR system that has been developed by Comet. And here, if you see in the volcano portal, each dot represents each volcano, where the black dot shows the volcanoes where they have been processed more than 800 interferograms. So we have a lot of data. And in this same volcano, you can see time series for each one of these volcanoes, and that has been processed with 100 meters of resolution, as is shown here in the right panel. And in deep bulk, we have been advancing this automatic process, increasing the resolution of this time series to 30 meters resolution. And also in this automatic process, current automatic process, it has been, the network has been created only with the short-term interferogram connections. So in volcanoes, when we have, for example, snow cover, we are having some gaps. So what we have been doing, it has been to include also long-term interferogram connections. And then with all these interferograms, we have been automatically selecting the best one to include in the network based on coherence. And like that, we can have better networks that provides better coverage of the deformation in the volcanoes. If you want to know more about this processing, Pedro Espin, my colleague, has prepared a poster that has been shown on Thursday about this. So with this new processing, we have processed already more than 200 volcanoes, and this number is increasing all the time, and we will try to increase to the more than 1,000 volcanoes and make it this time series available for everyone. And then what we have seen from this volcano deformation is we see that there is a large diversity of deformation. We have different spatial patterns, and also we have a large diversity of temporal evolutions. For example, well, here I will focus in uplift episodes, and here are two examples where we see uplift episodes. They can last over a lot of years. And also sometimes these uplift episodes can evolve to subsidence or uplift again without an eruption, for example. So here I will focus in uplift episodes. Here I took 19 uplift episodes around the world, and you can see that the magnitude of this uplift can go from millimeters to meters, and they can last from some days, months, until some decades. All of them, they look quite different, and we were trying to see if there are some similarities in order to try to find a way with a model to forecast how this deformation is evolving. So when comparing these different uplift episodes, here I showed 3 examples. What we saw is like we can characterize them by 2 phases. We see some of these uplift start with an acceleration phase that you can see more clear in this second row, where is velocity over time. And after this acceleration, they started a phase of deceleration. And when we were comparing this deceleration period, we find that this deceleration in all these volcanoes, they look quite similar. And we were searching for a function to try to describe it. And we found that, you see here in the third row, that a logarithmic function or an exponential function can well explain what is happening in this deceleration period. And then when we are comparing the root mean square between the feet of observation with these two functions, we found that, well, both they can well explain what is happening in this deceleration period. And if you see a lot of the volcanoes, they lie in the middle of these two behaviors. Here you see all of these volcanoes are better represented by logarithmic feet, this one of exponential feet, but a lot of them, they are quite in the middle. So we were trying to find a model, so what physically can explain exponential or logarithmic. And well, searching from literature, we know that exponential functions well represent viscoelastic process, while logarithmic evolution can well represent diffusion of fluid, so will be linked to poroelastic process. And there are some studies that show that uplift episode can be simulated by these two different rheologies. So with that, we take the hypothesis that the first phase of the acceleration phase could be linked to the injection of magma, and then this deceleration phase that looks very similar over this different uplift event could be related to a poroviscoelastic relaxation that we will have in all these different volcanoes. So to model this, we were using an analytical model presented by Yan Liao in 2021. And here, basically, we are modeling an injection of mass over a short period of time. Then we stop the injection of magma, and we let the system to evolve. Basically, this fluid injected in the intrusion will propagate in this reservoir, and therefore we will see this poroviscoelastic relaxation. And we will see how it is reflected in the surface displacement. What we were expecting, because it has been proven in viscoelastic and poroelastic models, we were expecting an uplift increasing during the intrusion, and then an uplift continue afterward due to this propagation of fluids to the marsh. What we found when we explore all the parameter space is here you see in this line the end of the intrusion, so we see that uplift can continue after the intrusion ends, but also very interesting, we find that exploring the different parameters of this reservoir, you can also predict subsidence after the intrusion stop. Also, sometimes we can have uplift and subsidence, and sometimes subsidence and uplift. So it was a model very useful because it shows the different diversity of the temporal evolution that we observe in a lot of volcanoes. So then we were testing in some volcanoes. Here we see Uturuncu, where we have an uplift episode over a lot of decades. At Tomuyo, that we have uplift and then subsidence. And at Campiflegrei, for example, that we have uplift and then subsidence without eruptions. So we're thinking it's a good model to use to forecast. So we recreate a lot of simulation of different magmatic injection. We let the system evolve. So we recreate a lot of uplift and an uplift with subsidence with a different magnitude, lasting different period of time. One limitation that we had is this is an analytical model. So as I said, well, the reservoir is spherical, so we can reproduce only circular patterns at volcano, but we have a large diversity of spatial patterns. So we couple this temporal evolution with elastic models that can show different shapes as input of pressure evolving. And like that, we can have different spatial patterns and different temporal evolution. So then we were testing the deep bulk model, the deep learning model, sorry, and we were we could well forecast the formation in volcanoes as Tomuyo, where we don't have a lot of atmospheric noise, but the model was failing when we were having this seasonal pattern in the formation. Also, when we are having atmosphere, we are having different spatial patterns. So what we did to this simulation of a magmatic source, we add topographic correlated atmospheric noise. So like that, we have the spatial variety associated to the atmospheric noise and also the seasonal. So with that, we recreate all our simulations, and as you can see here, and we create 130 synthetic time series with 600 images each, that represent 10 years of observation similar to Sentinel-1, and with a 6-day sampling. And with that, we test our deep learning model. Here is a synthetic example. So here you see that our input, it was 2 years of the formation, and our aim, it was to forecast the next year. So the 2 years of the formation that are 120 images, we reduced to 25, where we have more density of image at the end, well, at the beginning of where we want to forecast, but also we record the long-term deformation. Here the forecast is in red, and in green you see the target. So the model is performing well to see, for example, when the deformation will decrease in rate, and also can well explain the temporal atmospheric noise that we see in the time series. And spatial, well, I'm showing to you the temporal results, but in a spatial pattern also it works well. So then we tested in real volcanoes. So here is the example of Socompa, where we have an uplift event, and the model is performing quite well. It's recognizing the acceleration of the uplift as well. In this case, in Tomuyo is the same. The model is forecasting very well, and in Copahue, for example, same, is well reproducing the trend of the deformation and also capture well the atmospheric noise, how it's evolving. So with that, the take-home message that I would like that you take is that we were making an effort to try to forecast global volcanic deformation through a global training strategy. So we found a model that is based on physics, and we reproduce this synthetic data that can well explain the diversity of volcanic behavior observed worldwide. And well, this deep learning model has been trained only in synthetic data and successfully forecast real volcanic deformation. So, thank you. That's all.
Yep. Go ahead, Francisco.
Thank you, Camila, for the presentation. Can you go back to the SOCOMPAS slide? Okay, and here the data itself looks quite noisy. Are those the black lines? The data?
Yes. So the
how can
blue
you be so-
points are the inputs, and the red ones are the forecast, and the green are the target.
But is there like a minimum amount of atmospheric noise that you need to have in the data for these deep learning models to work? Because this seems to be like on the very minimum noise that on the maximum noise that you can have for the model to work. Here it works fine.
Yeah, well, here also you can see that there is a lot of atmospheric noise, and it's quite well performing. We have some examples it's for that I was showing here that sometimes we have very low atmospheric noise and it's performing with noise also. So yeah, well, I suppose one of the questions that we ask us a lot is why we are incorporating atmospheric noise. The idea would be to extract it and then just to predict the magmatic source, but as the time series, a lot of time is difficult to extract the noise. We were thinking like to make a model that can reproduce.
Or adding the noise as part of the model, that would be a solution too.
Yeah, it's for that we included in the synthetic data.
Yeah. Thank you.
Hello, thank you, Camilla. I'm Mark Beemans from SkyGeo, and I wanted to ask, the examples you've shown so far are revolving around one intrusion event and the poro viscoelastic response. Do you have tested it on examples where there have been multiple intrusion events?
No, we didn't try it, but in the training, as we are simulating lots, then it can be combined, so should work quite well. One problem that we were having, because this is in process work, is like if you have sudden changes from, I don't know, the end of the deceleration and sudden acceleration, we were having issues because in the model we are not including two together, yeah.
But also if it's part of the input data set, does it take the superposition of the viscoelastic response into account?
Sorry?
If you have, let's say, two intrusion events in your input time period, would it take that superposition into account of the viscoelastic response?
No. No. We are doing single magma input and then leave it to relax. So
okay, thank you.
We could try. Yeah. Thank you.
Okay, so if there are no more, I think it's...
We have one more.
Oh, sorry.
Hi, Camila. Thank you for the nice presentation. I was wondering how would this work in more extreme environments, like you probably processing the Azores? Have you tried to see how this is behaving there?
In Azores? And there was eruption there? Or?
Well, precursors, kind of, or uplift?
Well, we try in some random volcanoes. I don't think that we try in Azores, but now we will try to see the performance globally.
So you're only trying this in volcanoes that are actually erupting?
No. It's for that I was asking. We didn't, in the simulations, we didn't include eruptions yet. We are including it now. So it's just for volcanoes that they have uplift with subsidence with uplift. That.
Thank you.
Okay, well, I think it's time for the coffee break now, and then the next session starts in half an hour at 11:10. Thank you.
supposed to start at 10? No, I did. There was a chap here earlier, and I asked him if I need to know anything, and he said, yes, everything is fine. So, well done. Yes, you can first. It's not supposed to be. Put my timer on. There's no timer. That's me. No, there's no timer. Oh, you are.
Supposed to take notes.
Yeah, today I'm going to look at my laptop. Morning. Yep. Yep. It's up there, yeah. Yes. Yes. Yeah, it is 10 past now. There's nobody here.
There's nobody here. There's coffee outside, so I get it. Yes. There you go, outside. Right, people.
Well, maybe if we just start talking, then you will realise. He's gone to hassle people. People are coming in. Something happened, and this has changed. So I think, do you want to do the intro and then I'll...
Okay, welcome everybody for Volcanoes session 2. We have a set of exciting presentations today. Wow, I already can't talk. Hopefully we have a few more people joining us, but in the meantime, our first speaker is Juliet Biggs, and she's going to talk about synergistic use of multi-mission SAR interferometry for imaging rapid deformations.
Okay, thank you very much. The first thing to say is this talk is going to be given on behalf of the postdoc Wei Yu Zheng, who wasn't able to be here today. But I'm going to present on her behalf some of the work that our group has been doing using various different SAR missions looking at the 2024-2025 Fentali-Dauphin magma intrusion. All right, so since the last Fringe, there have been several major dike intrusions, including the one we saw in the previous session, which isn't on this slide, around the world. So the two that have really made the press have been the Santorini-Colombo episode in 2025, and the Svartsengi Iceland dike intrusions. There's been a sequence of 9 intrusions over 13 months. But actually there have been 2 that have been much larger than this, both in Ethiopia, that really haven't made the news. And today I'm going to talk about the one on the left here, the Fentale-Dauphin intrusion, which intruded over a cubic kilometre of magma over 3 months. This is particularly societally significant. This intrusion is about 100 kilometres due east of Addis Ababa, and there were 75,000 people evacuated. And now, for various reasons, there's no local real-time monitoring on the ground in this area, but there is a fantastic satellite data set The intrusion is completely on land, and the 3-month duration means that we are able to capture quite a lot of aspects of the temporal and spatial behavior of dikes that we really can't see in some of these smaller and shorter-lived dike intrusions. So this is what the Sentinel-1 coverage looks like. This happened right before the launch of Sentinel-1C, so we only had Sentinel-1A. When the sequence started, it was only acquiring on one track, but ESA were extremely responsive and very quickly got both tracks turned on, so we have ascending and descending data on 12-day repeats. What you see in these images is both the long duration of the episode, but also that classic butterfly pattern that we associate with dike intrusions. We've got two lobes, one moving to the west, one moving to the east, and in between them we have a really complicated faulting zone of graben subsidence. And at the southern end there we can see point source deflation, which is the magma source that's feeding this dike intrusion. So we're also very fortunate to be working with the CEOS GViewers program that gives us access to lots and lots of different data sets. The one that we can see in the middle panel here, this is Cosmos SkyMed. We had both access to both Cosmos SkyMed first and second generation data, and ARSI were extremely responsive in both expanding the existing tasking, which really just focused on Fentali volcano itself, and also automating the delivery of these products so that which dramatically reduced the latency, and we were able to provide these in much more near real time. So this data set provides fantastic spatial and temporal resolution. And more recently, we've also been working with Kone, and now we have an L-band interferogram that spans the entire event as well. So obviously our first priority, particularly given the lack of ground-based monitoring, was to provide information as quickly as possible about what was happening. We did that through a series of COMET event response reports, which we posted online through the COMET website. But we also work very closely with our colleagues at Addis Ababa University, particularly Elias Louis, who made this really nice, simple hazard map, which shows a red zone for potential effusive eruptions along the axis of the dike, and this yellow circle suggests where there might have been explosive eruptions around Fentali volcano. And this map was actually used during that evacuation. We also work closely with the UK government via the British Geological Survey, who produced these volcano advisories to the UK FCDO. And finally, we collated all this information and published it as a data report in the Bulletin of Volcanology in October last year. And you'll see that the first author here is Lynn Way, a PhD student who was working on this at the start of her PhD. So I just wanted to say that this isn't over. This is what a long-term time series looks like here. We can actually see in the Sentinel data before the intrusion that there was some inflation. We use ICA, and we actually think there are probably two separate sources here, a shallow source that fed the intrusion and a much deeper source at something like 20 kilometers depth. Then there's subsidence at the source at Fentali during the intrusion, and it's now reinflating at a much faster rate. And this suggests that there are going to be more intrusions and perhaps eruptions over the coming years. But in the meantime, we are focusing on building some kinematic models, starting off with just looking at the Sentinel data. And we're using this really simplified geometry. We've actually masked out that region of complex faulting in the graben, just so we can get an idea of the overall plumbing system. So our geometry consists of this simple dike with a maximum opening of 7 meters, deflating source at a depth of 6 kilometers, and these are really simplified normal faults which just basically describe the broad structure of the graben. And using that, we can match all of those Sentinel ascending, descending, and also range offset observations. And we can track the volume change in the dike and the source. And the first thing to notice is that these have the same temporal histories, so they're behaving in the same way, which suggests that this is indeed the source that's feeding this dike. But also that the volume change in the dike is significantly larger than the volume change in the source. This shouldn't be surprising. This is something that we see at almost all dike intrusions, and it's because of compressibility, both of the magma itself and the magma reservoirs. This episode is a little bit unusual that the ratio is quite so high. It's as high as 7, which is larger than previously observed episodes. And we can also look because of the long duration here, we can actually look at how this changes over time, and we see this ratio actually increases with time. And there are some possible explanations: unusually high magma compressibility, a viscoelastic contribution to the deformation because we're looking over unusually long time periods, or there's a secondary source that is also feeding this. And right now we're trying to put some numbers on these scenarios, but I can speculate later if anyone really wants me to. Okay, so this is the broad picture of the magmatic plumbing system, but the access to the Cosmos SkyMed first and second generation data really gives us some unparalleled opportunities to look into this in detail at high spatial and temporal resolution. One of the nice things is that we're able to produce one-day interferograms, not every one day, but occasionally we can produce one-day interferograms. And here are a few examples which really show us that the dike opening is localized on specific sections of the dikes in different time periods. We can also look inside the caldera. This is now zoomed right in. The scale bar is completely different. That back circle is just over 1 kilometer across. We're looking inside the crater floor, and we can see there's another subsidence signal. It's very small, it's very shallow. But why it's particularly interesting is it correlates in space and time really nicely with an enormous emission of methane. So methane is not a volcanic gas. Nobody has ever detected methane coming out of a volcano with a satellite before. This is a really surprising observation. And there's a whole other story in here that is not very fringe. But once again, I'm happy to speculate about what that is later for anyone who's interested on where we think all this methane is coming from. All right, we're also able to look at the faults. As I said, the faults immediately above the dike are extremely complicated and overlapping. It's hard to pull the signals apart. So we've been focusing on this area that's about 30 kilometers north of Dauphin, where there was a sequence of earthquakes between magnitude 5 and 6. And we're able to use the Cosmos SkyMed data to actually separate out the deformation and the interseismic deformation in each of these. And what we see is repeated seismic and aseismic slip on a complex fault network. And Simon Arrego is going to talk more about the details of this in the Earthquakes and Tectonics session tomorrow. But if we really want to make the most out of this data set, we clearly need to be able to unwrap it. And that's extremely difficult. So not only do we have very large deformation gradients, we're now working at X-band, which means we have even more fringes. This is what one of the typical interferograms looks like. This is what a standard unwrapper does when you try and unwrap it. And we're just using loop closure here to illustrate just how bad this is. You can see the loop closure errors end up being tens of fringe cycles. So clearly this is a problem. Our other option is to use offset tracking. It's noisy, we know that. With such a big signal, perhaps that doesn't matter too much. But we also have a secondary issue, which is that the Cosmos SkyMed frames are actually quite small, and the deformation signal is extremely large. That means we don't have a stable reference point, and when we try and merge our frames back together, we get these nasty artifacts between the frames. So our approach here is to use offset-supported unwrapping. This is something that's increasingly being used for L-band data, sometimes for C-band data. As far as we can tell, not before an X-band data, because it's quite tricky. So what you do is you make the wrapped interferogram. You do fairly standard range offset processing, which has to be a little bit tailored for the X-band data. But then you take that, you remove the outliers, you apply a filter, you convert it to radians, and you wrap it so it looks like the original interferogram. If you subtract these two things from each other, you get left with a residual phase. Hopefully this just contains noise, but the idea is that there are fewer fringes, so your unwrapper can actually do a good job now. So this is what the unwrapped residuals look like. So you can see there is quite a lot of noise here, and you can also see in that unwrapped residual some of those discontinuities between the frames that I mentioned before. And that's actually a good thing, because it means when we add it back to the filtered offsets, we nicely get rid of those discontinuities that were bothering us before. And for the purposes of this talk, I'm now going to compare these two interferograms, and we're going to use this loop closure test to test whether we think the unwrapping is doing a good job or not. We're going to compare 4 different methods. The MCF, minimum cost flow, that's implemented in Gamma, MST, minimum spanning tree, implemented in SNAFU, and then we're going to combine with these with the offsets. This is just one example of a triplet. So the AB, BC, and AC, those are the 3 interferograms, and then the loop closure is shown in the panel on the right. And obviously white colors mean no errors. So we're looking for white answers here. So the first row is just the traditional unwrapping methods. You can see they both have pretty big problems. The bottom row shows that adding the offsets in, offset-supported unwrapping works really well in this case. Here's another example. In this case, you can see the traditional methods both have problems, particularly inside the graben area, where you have these little disconnected phase patches that it's not able to connect together very nicely. And when you add in the offsets, it improves this. MST still has some problems, but the offsets plus MCF seems to produce the smallest loop closure residuals quite consistently when we test this on case studies. So we move forward with that. We applied it to the entire data set, which is 61 interferograms, 109 triplets, and these are our results. So you can see that it dramatically reduces the loop closure errors in all three of these regions we're looking at, pretty much to zero in the west lobe and the east lobe. There are still some unwrapping errors existing in the graben, but it's a lot better than it was before. Just a little side note here that if you want to try this on X-band data, you really do need a high-resolution DEM. We've tried this by upsampling SRTM and downsampling Pleiades DEM that was acquired by our colleagues at IPGP. What we see is there's significant differences in the interferograms using these DEMs. And we really think this is the problem with the low resolution of SRTM. But we can put all of this together and we get a time series that looks like this. So here the solid lines are the offset-supported unwrapping. The dotted lines are the original unwrapping. You can see that the dotted lines really underestimate the magnitude of the deformation. And there's also some nasty things, particularly where we have these one-day interferograms that really illustrate that the results are not consistent, not internally consistent. And one of the most significant things that we see here actually is that inside the graben, which is that green point there, the original result showed that this part of the graben was uplifting. Now that's not physically plausible. Our offset-supported unwrapping results actually show subsidence in this region, which gives us a lot of confidence that we're actually now doing much better. So here's a comparison of the three different data sets. X-band, C-band, and L-band. They all have slightly different incidence angles, but broadly speaking, they show the same overall pattern. So far, C-band is the CSK data is the only one where we can actually reliably have nice unwrapping results inside that graben, and actually working with this data to understand what this time series of graben displacement means is our next goal. And here are my conclusions. And as always, I've gone way too fast. So here is the summary. So this intrusion was 50 kilometers long. It affected a large area. 75,000 people were evacuated. The total displacement was 3 meters, and it lasted 60 days. And really to get a detailed understanding of what happened in such a complex and large-scale event as this, and long-lived event, we need to use all three of these different data sets. The C-band Sentinel has been fantastic for the regular regional coverage and the large-scale modeling of this magmatic system. The X-band high spatial resolution enables us to see things like this deformation source inside the caldera and what's happening on individual fault systems. And we're really excited what we can do with these one-day interferograms. But if we really want to use it properly, we can't just use the standard approaches, but offset-supported unwrapping seems to be the way forward, and will produce is already producing a really nice data set that we need to interrogate a little bit further. And then the SAOCOM constraints, the L-band data gives us an independent constraint on large deformation. We were really hoping that this would help us unwrap inside that graben area, but actually it doesn't seem to be doing that at the moment. Okay, thank you. And a time for lots of questions.
Thank you very much. We have time for questions. Do you have anybody with? Yes.
Thank you. Nice talk. The one-day interferograms seem to have amazing coherence. Is the baseline also really small as well as being one day?
Yeah, so that's something that I should mention. We also have to adapt the processing strategy because a lot of these CSK data do have extremely large baselines, but those ones are okay. There's quite a lot more one-day interferograms we can make. Some of them have larger baselines, so I've kind of cherry-picked the nice ones there. But hopefully, once we put a little bit more work into it, particularly building cross-interferograms between CSK and CSG, which is possible, but a little tricky. Once we've got all of those, we should have a much nicer time series of those one-day interferograms. So they were just some nice examples.
Lots of hands. Who's next?
Oh, just a quick follow-on. Yeah, so the one-day ones which allowed you to get that fill in the graben. So I guess the question I have is, presumably if you had, in such a scenario, if you had NISAR with L-band at 12 days, you might overcome some of that in terms of the fringes and you might maintain coherence there. But I guess the question is was there such dynamic behavior that you'd be, of course, integrating multiple events over 12 days versus, in other words, did the CSK also with one day give you much better sampling of dynamic processes?
Yeah, so I think the NISAR might look quite a lot like the Sentinel, which is also 12 days. We don't have a lot of problems with vegetation, although there is one quite densely vegetated patch. There's a river running down the middle of this, so there is one area that's agricultural, and that might be somewhere where NISAR would improve the coherence over the Sentinel. But the biggest problem with the Sentinel is there's just surface offsets everywhere in that zone, and it's just really, really complicated. And I think that would probably affect NISAR. Maybe the longer wavelength would help.
Are you also suffering from aliasing of fringes because there's too much?
Yeah.
L-band would help with that.
Yes. Yeah, so those one-day interferograms we can unwrap without using the offset supported unwrapping. But to make a time series, we have to combine the one-day ones with the seven-day ones. And we need it for the seven-day ones. Yeah.
Maybe one final question before we move on.
So you've used the closure loop as a metric to determine how well the unwrapping works. Have you just used that to correct your unwrapping, and then presumably all of the schemes would work perfectly?
Yes, I guess we could have done that, but we have the offset, so that seems like a good place to start, yes. Certainly if you use the Lixbas approach, which is mostly to exclude those, you just don't end up with anything. Yeah.
Thank you very much. I think let's move on to the next presentation. Thank you. The next presentation is by Elliot Eaton, and it's on understanding ground deformation close to growing lava domes.
Hi everyone, so my name is Elliot Eaton. I've been studying at the University of Leeds, looking into how we can investigate lava domes with SAR and INSAR and try to understand the core processes responsible by interpreting the ground deformation and using COMSOL finite element modeling. So, as lava domes grow, the hazard associated with these can be put into two sections. So, the total volume of the dome gives you an indication of how much mass can actually collapse. And the ascent rate, the rate that the magma comes to the surface, can give you an indication of how well this magma can degas and outgas from the conduit, and that has an indication of its explosivity. So when interpreting the ground deformation associated with this, we separate this into two different sections. So one is looking at the shear stress and excess pressure that's associated with the ascent of magma in the conduit. And the second is the loading that we see from this new extruded material. So new mass at the surface causes the loading effects close to these proximal domes. And these two signals are occurring over the same spatial area, all of which very close to the dome. So we need high resolution INSAR. And to do this, we look at the Dinosaur TerraSAR X mission, as I've heard it called a few times this week. So quick overview of the talk. We're going to look at some of the challenges of monitoring these lava dome building volcanoes, then go from SAR to INSAR to the modeling, and then follow this up with 3 examples, and then the implications for both volcanic processes and monitoring. So the three case studies we're going to be looking at are Volcan de Colima in Mexico, La Soufrière in the Caribbean, St. Vincent, and also Mount Sinabung in Indonesia. All three of these eruptions had quite varying behavior, but a consistent parameter is that they all went through phases of having extrusion and maybe quite passive dome growth, but also could transition to quite hazardous behavior quite quickly over short timescales. And these eruptions all lasted quite long time, some of which decades. So these become real monitoring challenges and difficult to, not always simple yes or no answers, I guess. So the framework for a lot of this study is based upon ground-based monitoring. So a lot of our previous research on terms of ground deformation comes from tilt meters. These are extremely sensitive, but also extremely difficult to maintain. When you've got large dome building eruptions that last for long periods of time, and you've also got dome collapse events and pyroclastic flows, maintaining equipment within a few hundred meters from these growing domes becomes ridiculously difficult. And you're never really going to be able to match that spatial resolution that we were able to achieve with satellite observations. But the challenge with satellite observations is that these processes occurring at lava domes happen very quickly. So once we've sampled every 12 days, we're going to face temporal aliasing problems, and that's even if we can meet the magnitude of deformation required to detect these signals. So it's always worth considering that when we're processing these INSAR time series, that these processes are happening a lot faster than we're currently detecting, but maybe with more one-day stuff, we might do a bit better of a job. But the challenge of using INSAR to detect lava dome targets is, well, they're quite hard. The signals can be small and very proximal to these growing domes. The deformation signals are transient. They might last hours, days, or weeks. They're hard to observe because of the interactions between steep topography, craters, domes, and they're also hard to preserve because coherence is frequently lost close to this new lava domes, pyroclastic density currents, ash and rockfall. And as a result of this, deformation signals associated with these growing lava domes are largely missing from the global database of catalogues when it comes to INSAR measurements. And this is maybe because C-L-band SAR with larger temporal baselines are missing these processes that are most relevant to dome growth. So because of this, I show a nice animation from Edna's paper where we move from using SAR to track the surface changes that are occurring at the surface in the vent. We're using INSAR to track what changes, how the edifice is responding to this stress, and we need modeling to try to understand these deformation signals that are occurring proximally to these growing domes. Because when you've got different line of sight viewing geometries, these signals can get rather complicated and they're not always easy up and downs. We've got very complex interactions between 3D displacement fields and the observed deformation and line of sight. So a quick example where SAR intensity images alone have been quite significantly important for monitoring efforts. Merapi in 2010, where they observed a rapid increase in dome growth volume, which contributed towards the evacuation of thousands of people and has been attributed to saving thousands of lives. So to go from this, we really need to, what can we do more than just using SAR intensity? And it's to move from intensity to deformation, where we're looking at the edifice response, and then go into source models to try to understand the core processes behind this deformation. So to do this, we choose to use FEMs, and this is because analytical source models often violate different assumptions once we're moving to the very shallow subsurface. And we're also looking at complex deformation sources, such as fluid descent when we're modeling magmas, and there's also significant topography. So our first example that we're going to look at was from Volcan de Colima in 2015. This is an eruption that, again, has a large local population and went on for well over a decade and goes through various phases of dome growth and dome collapse. So looking at the largest collapse from this long event, or long eruption period, in early May 2015, there's a new phase of slow dome growth, followed by a SAR acquisition. Between the two SAR acquisitions, we have a rapid increase in magma ascent rate. Then we have another SAR acquisition, And following this, we have a large dome collapse event. So we're trying to really understand what deformation we could see prior to this dome collapse event. And when we take the interferogram between these two dates, we see concentrated deformation within 100 meters from the vent with largest amplitude, but we also see a typical pressure source where you have movement towards the satellite on one side of the volcano and movement away from the satellite on the other side of the volcano. Probably worth mentioning that red, in our case, is towards the satellite. So to model this, we model the complexities of magma ascent using a fluid dynamic model, and we combine this using the shear stress and excess pressure at the conduit walls to try and understand the edifice response. We don't match the data perfectly because there's too many unconstrained parameters in our magma ascent model, but what we try to highlight is that the shear stress component matches the deformation close to the vent well, and the pressure component gives you that more typical movement towards and away the satellite once projected into line of sight. Our conclusion from this is that we highlight the contributions of both excess pressure and shear stress. But one of our biggest unknowns in these kind of models is how the edifice is responding to stress at the appropriate length scales. So we have to assume a Young's modulus. And I'm going to come back to this later on as a parameter that we can try constrain. So our next eruption example is at Mount Sinabung in Indonesia, which had its first Holocene eruption back in 2010 and then again had over a decade's worth of dome growth. And another example where you have a large local population within proximity to the volcano, and again a volcano whose behavior can change very rapidly corresponding to these dome growth rates. So I have a couple of pictures of the dome, and I'm again going to walk through this time series. So in early August, you have a phreatic explosion that ignites a new phase of dome growth. We have continued growth for a few months, and then we have a series of collapse and pyroclastic density current events, followed by continued growth, followed by continued collapse. So for those of you who have got your eye into SAR dome images, you're going to see a dome growth, but you will also see a series of collapses where the radar shadow width increases. So in this animation, we have dome growth beginning, growth of this new dome, and then once the increase in radar shadow occurs, that's signifying collapse now, and then we have a new phase of dome growth, followed by another collapse event. And the interesting point of view from a deformation side of things is during this dome growth phase, we see movement away from the satellite that we want to test to see if it fits with a hypothesis of loading. And when we calculate the time series using Terrace X combined with LixBAS, we see a relatively linear loading signal. But when we have these dome collapse events, we see somewhat of an elastic response, so recovery of strain, following the loss of mass at the vent, and then renewed extrusion again afterwards. But unfortunately, we struggle to maintain coherence following more collapse events close to the vent. So from this, we get some evidence that the edifice is behaving elastically. And what we want to see is if we can use this elastic behavior of the edifice to try constrain a Young's modulus that's appropriate for these shallow edifice and conduit studies. So we do that by estimating a volume of the dome, inferring a mass from that volume, modeling this mass of new loaded material, and then trying to match the observed deformation throughout time. So we first do this using differences in width and radar shadow to give us a change in height of the dome. And using drops in intensity along range lines, we use simple trigonometry to calculate differences in height. Using these differences in height, we simulate SAR images in a forward modeling approach to match the intensity images from the Sinabung eruption. And using this forward approach can be useful because if we have future scenarios of dome growth, you can do this before you've got any dome growth. You can do this preemptively. So if you have different scenarios of different magma viscosity models, you can try simulate these SAR images preemptively. It's not something you need to do afterwards. When doing this, we use a maximum and minimum estimate of dome volume at each date, and then we calculate the best fitting Young's modulus to match the loading deformation at each date. So at each date, we have a minimum and maximum volume, and that gives us upper and lower estimates for dome mass, and we use that to solve for a best fitting Young's modulus, which remains quite consistent through time. The significance of this is that this elastic moduli that we find is relatively low compared to just measuring individual rock samples in a lab. So it maybe gives us a more appropriate elastic moduli for these sorts of studies. Our final example is from La Soufrière in the St. Vincent, which went through, in 1979, grew a dome without significant collapse events and eruption, which left, once the 2021 dome event occurred, the new dome grew around the old dome. So again, in our time series, we used estimates calculated from Edna's paper to show that there was dome growth at a steady rate for about a 4-month period, followed by a rapid increase in dome growth rate prior to the next explosive phase of the eruption, but we also have some SAR images in between. The reason that this case study is particularly valuable is that Old Dome provides an excellent coherent surface for INSAR studies. So essentially, this is it's the closest we're able to observe deformation to a grown dome out of any of the examples that I've studied. So we also have 4 different high-resolution line of sights that we're able to process with INSAR data, and we see a range of complex signals associated with this phase of dome growth, but the one I'm going to focus in mostly is where we see movement away from the satellite most close to the growing dome. And when we model this in COMSOL, we find the data is relatively well fit by loading of new dome material, but there are other components of the signal in there that we're hoping to study further. So the implications for volcanic processes is that these highly localized and transient deformation signals can give us an idea of changes in magma ascent rate, but these observations aren't common. And the modeling highlights components of both shear stress and pressure source. And when it comes to loading, the loading is given as an indication of the cumulative deformation with dome mass and volume, and the reversals following dome collapse give us indication that the edifice is responding elastically. We use this to constrain elastic moduli, which is significantly lower than individual rock samples. And here I compare the observed deformation signals to the ground infrastructure that was in place during each eruption. Not all of this infrastructure could be maintained once the eruption started, but it shows that we're seeing signals that we're not really able to capture with these ground-based instruments. So the high-resolution SAR and INSAR is able to identify the spatial distribution of deformation, and we hope this can guide the future deployment of ground instruments. The satellite observation cannot replace ground instruments. These changes occur too rapidly and often occur between acquisitions. And the best monitoring strategy is to combine frequent X-band SAR from multiple viewing geometries with the continuous ground-based geodetic and seismic data. But currently, small baseline X-band SAR is critical for monitoring these lava dome building eruptions. And I'll leave data availability for how this X-band data has been made available to us as scientific researchers. And it's been the continuation of the CEOS Volcano Pilot Project and the Volcano Demonstrator Project, which has now led to the G-Viewers Project, which aims to form permanent partnerships between space agencies, researchers, and volcano observatories to coordinate the acquisition, access, and utilization of this high-resolution SAR data. Thank you.
Hi, thank you, Elliot. That was a great talk. Do we have any questions? Yes, Sang Ho. Oh, I think there's one at the back first.
Yes, you might have said it. The Terratar X, was it Spotlight or is it Strip Map?
We have a range of different, it's unique for each volcano. At some volcanoes we have more than one. Sometimes it's staring spotlight, sometimes it's spotlight. So the pixel sizes we're mostly using a sub-meter.
Okay, so strip map is not good enough.
I didn't have none of the volcanoes had strip map, but I would say that when we multi-look these spotlight data by a factor of 5, we lose these signals really quickly. So that gives us an indication that maybe future missions like Sentinel-1 Next Generation or NICER with 5 by 5 meters are still going to be too big.
Okay, fantastic. Sang-Hong?
Thank you, Elliot. The elastic response of 2 centimeters seems a bit large. Of course, I haven't done any calculation. Is there a possibility that may not be totally elastic, but removing the overloading mass, that equilibrium is broken so that the underlying thrust can push further, so it's not purely elastic? Is that a possibility?
We have considered different types of not elastic, as in compaction, but the reversal of that signal gives us some indication that it's not all compaction. In terms of driving force from a conduit, we just don't see the evidence for it, and we don't also,
Thank you.
Okay, I think we'll move on to the next presentation. Thank you, Elliot. Which is given by Franz Meyer, who's going to talk about Volksobservatory.
Yes, I'm very proud of that acronym, by the way. So if you mock it, you have to take it on with me. No, that is actually coined by Ronnie Grappentine, so all credit to him. So this is really not as interesting from a scientific perspective. It's much more operational in nature, this talk. We've been working with the USGS in the United States to help them operationalize INSAR services as part of their monitoring program. And so Volksobservatory was a project funded by NASA, is a project funded by NASA, where we work directly with the USGS on this integration. And so the motivation is clear. The USGS, through the Volcano Hazards Program and the Volcano Science Center, they are responsible for monitoring volcanoes in the United States across their volcano observatory that they maintain. But as you know, many of these volcanoes are not permanently monitored, and so INSAR is an essential component of their activities. And VSC is actually doing some INSAR processing currently, mostly relying on data sets that we just saw, higher resolution Cosmos, SkyMed, and TerraSAR data sets for volcanoes that are active. But there isn't a broad operational sort of background monitoring activity that is going on currently at the VSC that would be consistent across the different observatories. So the goal here was to supplement the work that's going on by building a service that does operational background monitoring for all these volcanoes at the choosing of the volcano observatories, and predominantly using Sentinel-1 and NICER for that background service. And so, as mentioned, it's a partnership between ASF and the University of Alaska Fairbanks, where the data sets are located, and some of the cloud computing that we using it here are located. And then the Volcano Observatory, so we have AVO, the Alaska Volcano Observatory, is sort of our prototyping grounds, and then the overall VO, the Volcano Observatory, and the Volcano Science Center at USGS with the partners that are listed here. Okay, so what are we building? We ended up building a cloud-based platform that's mostly needed, especially when you think of NICER, where the data volumes that we have to handle across sort of the entire domain are fairly substantial. So we tried to build something that sits essentially right next to the archive, so we don't have to move data around, and we are as computationally efficient as we can be. And the goal is in the end to connect the data that you see on the left-hand side, ooh, a fancy laser pointer, with basically the decision support systems that the volcano observatories are maintaining. So this one shows the one from the Alaska Volcano Observatory. They have a platform where they integrate displacements that you may get from INSAR with GNSS observations and seismic data in a single platform for their hazard analysis. And so the goal is to connect those two, and the kinds of data we'll be using are shown on this on the left-hand side here. So we, of course, use Sentinel-1 SOCs for INSAR analysis. We have NICER, which provides next neighbor interferograms operationally, but we also work on supplementing these with on-demand processed additional interferograms. And then there are some operational products that we can use out of the box. And so we're also using the Opera service and forwarding the Opera data to the platforms that the Volcano Science Center is using. So the simple work is the work for Opera, where we basically just, based on AOIs that the end user is defining, grabbing data sets, forwarding them on for integration into the platform. And then for all of the rest, we have a cloud-based service that we use for the scene selection, burst selection, interferogram calculation, and time series analysis, and delivery of the products. And so most of the stuff that I'm going to talk about is this middle piece. But before I get there, most people know this by now, the Opera project funded by the Satellite Needs Working Group and executed and operated by JPL, they have created a bunch of higher-level data products from SAR and optical data that are much easier to use by the community. And the important ones for this particular project is the surface displacement product. This is a line of sight data set at this current stage that's currently available for Sentinel-1 for large parts of North America and will soon be available also for NISAR. And additionally, in the future, there will be a vertical land motion product, which is decomposed product similar to what you find on the European ground motion service. One maybe difference that makes it really interesting for this particular application is that in maybe contrast to the ground motion service, which doesn't get regularly updated, the Opera displacements are updated every time a pass comes over. So you always have the latest and greatest data sets available, which makes this data set quite useful for sort of more operational monitoring applications. Data are free and open. And so the good thing is that the team has tried to design the workflow in a way that it covers various climate zones and various terrain features. But of course, it's not optimized for an individual edifice. So the USGS was interested in having a more customizable service available in addition to the Opera service. But for now, we just basically grab the Opera data that exists and make it available to the USGS. Oh, and if you want to find the data in the portal where you can find it, this QR code gets you there. And if you're a QR code fan, there's going to be a few of those throughout the slide deck, so you can prepare your phones. Okay, so now for Sentinel-1. So for Sentinel-1, we've developed an operational service that includes all of the features that are shown here. So it's an adaptive burst-based service. So the components that are included, again, it's fully cloud-based for just computational efficiency. And instead of operating on a frame basis, we operate fully on bursts. So we have a multi-burst INSAR workflow where we automatically identify the bursts that are needed for processing, stitch them, and create consistent multi-burst interferograms. And then we have full automation of the service, anything including monitoring for new data, burst selection, automatic INSAR partner selection, using some coherence predictions, then fully automatic INSAR time series workflows, GNSS calibration, and delivery of data. That being said, all of it is customizable, so we expose a bunch of parameters to the end users that they can modify to, if they don't like the default settings, to customize it to a particular target. And I should say, everything's fully open source. That's the reason for all the QR codes you're going to see. All of the individual components that we've developed in Python, they're exposed on GitHub, and you might be interested in one or the other. If you forget to snap a QR code, I'm here, and Joe Kennedy, are you here? Is here, so he's waving. And so you can ask questions about those later. And again, reminder, everything we do on the heavy end processing is implemented in AWS, in Amazon Web Services, right next to the archive. It uses these kinds of components here that I'm going to walk you through here in the next slides. So first, again, reminder, everything's burst-based. The first question that we need to answer is, when do we actually need to do any processing? And there's two ways how the system knows when to process new data. One of them is if a new AOI is defined. So if say, Marco or Mike Poland is uploading a new bounding box, we'll automatically start a processing run for all the interferograms that we haven't created already. And I'm not sure if you see it on the right-hand side. The blue boxes here are the AOIs. If we already have an existing processing run, Then we developed what we call a CMR notifier or an SNS topic that watches for new acquisitions that hit the archive. So this could be a really interesting thing for you to utilize if you want to build your own operational service. Behind this QR code or the URL, you find codes that to utilize the CMR notifier. So that would tell you every time a new data set hits the archive, which we then compare to the bounding box information to find the frames that are relevant for us for processing. Once we found the new frame, we do a first step. We identify which bursts we need, we identify partner images, and then do pairwise insert processing. And so this is, in essence, a three-step process. The first one is we've refined an AOI. So if we have an AOI existing on the bottom row, what we do is we take the original AOI, we intersect it with landmass. A lot of the volcanoes we have are islands. We then identify all the overlapping bursts, and then we down-select to the bursts that have the best coverage in time and space, and we identify a multi-burst set. So these three red bursts would be our multi-burst set in this case. Then once we have the set, we then find all the interferometric partners that we want to create. In order to do that more or less automatically, what we utilize is a coherence, a global coherence mosaic set that was created through some funding through the Surface Deformation and Change study in the United States. So it was funded by JPL and run to create seasonally specific coherence mosaics for the globe that cover 12-day, 24-day, 36-day time spans. And we can use that to predict what the coherences should look like, and based on that, automatically select which pairs we want to calculate for an AOI. And that's super useful, especially in places like Alaska, where you have seasonal coherence variations, etc. Once we have all of those, we submit them all for processing. We use our HYPE service at ASF to scale in the cloud to create these data sets really quickly. If you want to know more about HYPE, this QR code gets you to the documentation for the service we provide there. Okay, so now we get, say, 1,000 interferograms. Once we have them all, we use MinPy, which is an SPAS type time series service, to then do the time series analysis. We have a set of settings that sort of default settings that we use here, but we expose some that users can change to optimize the processing. So here's the QR code to the MinPy container. So this is the container that is scalable, a Docker container that you can scale in the cloud for processing. We tend to typically still process everything in one fell swoop, even though we update every time. For now, we have enough computational resources to process the entire time series, but you may want to, at some point, break it up into subsets. So we have an implementation in place where you can break it into 2-year subsets with 1-year overlap to reduce the computational burden, and then we stitch those overlap regions together. And so we have this running right now for several volcano sites. The goal currently is to test it for different kinds of settings. With the USGS, they do their own boutique processing for comparison, and we sort of try to fine-tune some of the parameter settings there. This is one site that's running at OCMOC, which automatically is referenced to OKFG if you know the GNSS station. So this one's running operationally every time the satellite pass is coming over. And you see here a sample of the GNSS time series in the INSAR time series down here. And if we would stitch, again, usually we run the dark blue line, which is everything at once. But if you wanted to stitch, overall, the approach seems to work roughly okay to stitch the time series together. Just some other ones, we run Kilauea because just to sort of understand in that site how the atmospheric correction is working, we see that so we intentionally place the reference point far away from the site to sort of understand a little bit the noise we accumulate. We do still get, some residual phases in places, but this is also running operationally for test purposes. One thing that I have on here that I didn't mention earlier, we actually provide 2 times of time series for every site. One of them is a time series we call the scientific time series, which only uses the the best interferograms, the ones you would use for a publication. We also run a time series where for the last year we use all interferograms. That's on request by USGS. They want to not miss the deformation, even if it's sort of lower coherence. So for sort of an early alerting reason, we have a separate time series where the final year uses all available interferograms. Another site that we have, so we looked at Iceland, looking at this cooling lava flow, just to sort of understand different sites and different conditions. Here, we actually ended up selecting all the interferograms and sort of following the cooling and compaction of this recently in place lava flow. So as a sneak peek, NISAR data will become available soon, so stay tuned for that. Mid of July, you should see a full forward processed release of NISAR. And NISAR does provide these fully unwrapped geocoded interferograms that are already immediately useful for volcano monitoring. And so first data are available now, and so the interferogram data set is called GunW down here, and this is sort of one of those samples. You can discover them all through the ASF interface, both through Vertex, which is the graphical user interface, but also through our Python search clients if you are looking for programmatic search. But in addition to that, there's the RSLCs and the GSLCs available that you can use to create additional interferograms. We are implementing a workflow based on the radar-coded SLCs because we want to do the ionospheric correction, which we need for many of the volcanoes in Alaska. So we've developed a workflow to create additional on-demand GunW interferograms from sort of an arbitrary pairing of RSLCs that we want. And so we are currently evaluating this. So this is a comparison for our own GunW with one that NISAR is operationally producing. And they look very good in places where the coherence is decent. Where there's no coherence, we get, of course, sometimes differences based on unwrapping. And so this is powered by ICE3. And if you haven't played with ICE3 yet, this QR code gets you to the software. And I think that's sort of it. So we put together this tech stack. It has a fairly modular set. So there might be one or the other piece that you might be interested in for your own service. If there's any questions you have, please talk to me or talk to Joe after the session. We do multi-burst processing, which I think is really useful for at least volcano targets, which are usually sort of limited in extent, where full-frame processing might be a waste of resources. And we have this automatic setup for doing automatic SPAS. Currently, so the workflows are already available for the USGS for testing. So Marco is running them and comparing them to his own handcrafted processing. And we are currently working with the USGS on transitioning the whole cloud setup to the USGS, who are also in Amazon Web Services for them to maintain the service long term. Oh, and very last thing, if you have grad students that you are interested in working with NISAR data, it might be worth pointing out this course to them, the 2026 EarthScope INSAR course run by Gareth and myself with a lot of instructors, Paul Rosen, Eric Fielding, Haresh Fatahi, all of these folks will present. And it's specifically focusing on ICE3 this year, which is the software package behind NISAR. So it might be interesting for some of the grad students to register for this course or apply for the course and attend. And with that, I thank you.
All right, thank you, Franz. Does anyone have any quick questions? Yeah, Francisco?
Thank you, Franz, for the presentation. Can you go back to the Kilauea example?
Can I?
Yes.
I should, right?
I think so.
Oh, here we go. Button is not very good.
Okay,
oh, here we go. Yeah.
That's fine. I assume that these products are not masked for unwrapping errors because the eastern part of the big Hawaiian island is tropical rainforest. It doesn't have coherence, and there was actually a dike intrusion in that region, and the dike intrusion is nowhere to be seen on this data set. So I assume that the mask is absent.
Yeah, so this is still under evaluation, and there's no masking done at the current stage. Do you know Mario Angarita?
Yes.
Yeah, so he's working on it, and you can also talk to him directly, so he might contact you anyway.
Great, thank you.
Okay, and I think Volk had one as well.
Yeah, so in Alaska, of course, you have lots of snow, and these volcanoes are having different elevation. You have a high, the high parts have lots of snow. At the lower elevation, you have longer time periods where you have coherence. Are you taking advantage of that in any way, or how are you dealing with it? Or do you have any, well, you said you're just using the coherence. Is it taking that into account to some extent?
Yeah, so right now we use the average coherence across the AOI, which I think may run the risk of us throwing out some data sets that might still be useful at lower elevations, if that's what you mean. We don't currently have like an elevation-based way of selecting the interferograms we want to keep. So right now we basically, for the AOI we pick, we grab the coherence information, calculate the average coherence, and use that as a razor to either throw out or not throw out certain interferograms, or create and not create certain interferograms. Yeah, so yes. So, I mean, it picks automatically the seasons based on the coherence information.
But so if the volcano is snow covered, even in summer at the peak, so it's going to somehow spoil into a, well, it looks like a good coherence, but it may not be.
You mean you get good coherence but not useful phase? Is that your question? So if the coherence is gone, we would not create that interferogram for the scientific workflow. For the other one, which uses all the interferograms, we would create the interferograms. So we have both runs available, the one that selects interferograms based on coherence and the other one that uses all of them.
Thank you. We should move on to the next talk. Thank you, Franz. The next talk is Francisco, who's going to be talking about abnormally large magma flux does not lead to eruption in subduction zone calderas.
Should I need to do anything here?
No, I think it should do it for you.
Get your slides.
How does this work? Huh? There.
This is forward and backwards.
Okay,
Don't
great.
press the black button if there's one. There's none.
Okay. Okay. Good morning, everybody. Thank you for being here. So I will keep working in Alaska, so following up with Franz's work. But this focus is on an episode of unrest at a large caldera that's called Aniakchak, located in there. So this is stuff that is published at GRL in a paper that came out earlier this year. So this presentation is mostly a summary of what I put together in the paper, that you can check it out. So as an introduction, I would like to highlight that sometimes we get overblown by the multiple SAR missions that are continuously launched. Yesterday, we were hearing about ROSE-L, Sentinel second generation, and so on. We acquire tens of hundreds or even thousands of images per year. We have multiple AI algorithms, ChatGPT, Claude, and so on. So we wonder if we can still do science like we were doing it from a few decades with just a few interferograms and a MOGI model. This might look like a stupid question, but actually the answer is yes. And it's yes because despite 3 decades of INSAR, there are still many regions on Earth where volcanoes located on middle and high latitude still lack good quality INSAR observations. And this is unfortunate because if we are trying to address one of the relevant questions on volcano science, which is what triggers eruptions, and this has been highlighted by several studies by multiple groups in the past decades who have proposed different models, all of them agree to the point that magma recharge is the primary driver of magma reservoir pressurization. So we need to have a way to track more systematically changes in the magma pressure, in the magma overpressure, and we can easily do that under a lot of assumption, but we can do that with geodetic data, and particularly with INSAR. There are other mechanisms, for example, that have been commonly addressed in the literature, like, let's say, eruptions triggered by second boiling, hydrothermal pressurization, and so on, but there has never been enough unambiguous data to actually prove that without ambiguities. So despite the complexity and the structure of plumbing systems in volcanoes, we are still left with very simple mechanisms to address if ground deformation results in eruptions. And we can actually try, and the idea of this presentation is to address if we can use these simple models of magma reservoir pressurization to actually predict, say something about how eruptions are triggered. And usually in many volcanoes, particularly in basaltic calderas, we do observe this nice predictive pattern of exponential deflation followed by exponential inflation between eruptions. So where should we test these models on a general case? I propose that we should do it in the volcanoes that have erupted in regions where we have had many BI4 eruptions, and this is a compilation I made the past year, where I took another compilation by Galeto and collaborators, who calculated the erupted mass over all the subduction zones on Earth. And I also extended it to an INSAR compilation to assess that the best volcanoes on Earth where we have had this kind of eruptions with INSAR-related ground deformation are located in high latitudes, Kamchatka, Alaska, Southern Andes, and in the Southeast Asia. And for INSAR, the best targets are located in Kamchatka, Alaska, and the Southern Andes. In Southeast Asia, volcanoes have their own other problems with coherence and strong tropospheric delays that we have already heard earlier on this session. So I will focus on a volcano called Aniakchak, located in Alaska, which is the most productive arc after the southern volcanic zone in the southern Chile and Kamchatka, and we exclude for that comparison the outlier of the Pinatubo eruption in 1991. So blue triangles are observations made with INSAR, and green triangles are observations made with other geodetic data such as GNSS or EDM baselines. So what's cool about Aniakchak? As an a priori, it's a basaltic andesitic caldera, nothing special about that in Alaska. It had, as shown in this figure, a large seismic swarm that occurred at the end of 2022. Seismic swarms occur regularly at volcanoes, so a seismic swarm by itself, there is nothing particularly new about that. But when we were looking at data from SAOCOM, when I was working on the calibration and validation of this mission, I came across this 1-year-long interferogram from July 22 to June 23 that shows, in addition to a massive ionospheric orbital ramp, a lot of fringes, of L-band fringes located in the middle of the caldera. And this is quite abnormal for those who are familiar with subduction zones. It's very rare to detect in a single interferogram so many L-band fringes. At the beginning, I thought that there was a processing issue with SAOCOM because this is a mission that was never designed for INSAR, and it turned out to be actually quite good for INSAR. So when I calibrated, so working with other data, like ALOS2 SCANSAR, which is an awesome data, finally available at ASF, we can cover every frame is 350 kilometers wide, and we observe here, and again, multiple fringes of L-band deformation just located in the middle of Aniakchak crater. No other volcano, which are the white triangles, shows clear evidence of ground deformation during this almost 1-year period. And this, by pairwise logic, shows that the data that we recorded, that the observation that I made in the SAOCOM interferogram is real ground deformation because it is another satellite from a different orbit recording essentially the same pattern of uplift. So I decided to put together a study to assess what was going on at Aniakchak. So when we compare more on detail SAOCOM with Sentinel, these are 1-year-long interferograms that span more or less the same time. Grab and grab, we can see that the Sentinel, it looks awful because of the high galliasing of the fringes. There are coherence losses. Still, you can ungrab it, not without ungrabbing errors, but it's much better to work with the L-band data because it clearly shows a nice uplift pattern that reaches up to 75 centimeters recorded in less than 1 year. So the focus of this presentation is mostly on L-band data despite its low temporal resolution. So SAOCOM is quite an outstanding data set for tracking unrest at volcanoes in high and middle latitudes. So what do the different L-band data shows? SAOCOM descending, ALOS2 ascending SCANSAR, ALOS2 ascending SCANSAR, ALOS2 ascending stream map, and all of them show essentially the same pattern of uplift with reaching a total of about 75 centimeters. This spans 11 months, this spans 11 months, this spans 2 years, and this spans also 11 months. So the signal is real. It's not an artifact of the processing, as I suspected originally with the SAOCOM interferogram. But the problem working with all these L-band datasets is that the temporal resolution is quite low. So here is the location for a time series in the SAOCOM data, here for the ALOS2 strip map, and here the time series, and we can clearly see that the volcano uplifted a total of almost 80 centimeters, lasting less than 1 year. Sentinel only recorded, could only record the last bit of uplift before the winter of 23-24, and then the volcano turned to subsidence. This was not tracked by a GNSS station. A GNSS station was deployed by the Alaska Volcano Observatory, here in this location, AMBM, and it's not well collocated with the maximum location of the formation, but you can still see that the volcano is going down. For Sentinel, there was only a single interferogram that could sustain coherence during the winter over a time period of only 12 days, where I suspect that the electric properties of the snow remain kind of constant. A little bit of uplift at the beginning of the episode, and then the volcano is currently subsiding since mid-2023, and this is ongoing as of September of the past year. So uplift and then deflation. So the signal looks relatively simple. So I did a simple MOGI model. There is nothing fancy about a MOGI model nowadays. A grad student can do this. But the shocking thing is that despite of the large amount of deformation reaching 75 centimeters, your MOGI model, your data, predictions of the MOGI model and the residuals, plus the chi-square contours for the calculating the uncertainties, can explain the model reasonably good. But the weird thing is that the volume change that this implies is extremely large, and this results from the large amount of deformation. It's 35 millions of cubic meters, which converted to a flux, a yearly flux, it reaches 1.7 cubic meters per second, which is closer to the flux that you measure at volcanoes in places like Iceland. So I thought, okay, there could be another alternative to explain this deformation signal. This is a caldera. An ECHAC is a caldera. It's filled with weak materials, so probably injections of magma in the deeper plumbing system can get amplified, result in ground deformation, and the weak infilling materials can amplify the weak the deformation. So I designed a simple COMSOL multiphysics finite element model where I extrapolated the MOGI source to make it compatible with the analytical solution of MOGI, but I said the weak material has a very low Young modulus, so this could result in an extreme amplification of the ground deformation with respect to the case where the elastic properties, the Young modulus of the medium, is relatively constant. So here are the predictions of the finite element for the finite element model. Red and black are the MOGI and the synthetics for the finite element model. The finite element model, the MOGI source is slightly larger than the minimum, it's for a radius of source ratio to depth of 0.4, so that's why it doesn't completely match the predictions of the analytical solution, but it's fine. And here I present the model that has a weak caldera infill, and you can clearly see that this kind of amplifies the ground deformation, and it ends abruptly when at the caldera limit where the elastic model it reaches the same value than the elastic model. For the vertical displacement, it's the one calculated by the blue dots. It looks kind of like that of a MOGI model, but you can take the predictions of a MOGI model, of a MOGI model in here with the blue line, and you can scale it to sort of match the predictions of the model without a caldera infill. This model, when you project it into the individual interferograms, can also explain the data, but the residuals are slightly larger compared with those of the MOGI model. So the implication is just, for this extreme example of ground deformation, a single pressurized source can explain relatively well the deformation data. So what does this lead us to? What does this all mean? So we had to make a comparison on a global scale. So what I did here is I took comparisons of magma flux for pressure sources, not dikes, only pressure sources in subduction zones. This is mostly for the Americas, because in the Americas is where we have the largest compilation of deformation sources. I assume magma to be an incompressible fluid. I am neglecting all sorts of viscoelastic, poroelastic, or whatever more complex rheology. Just take the source models, make them simple, and plot the average magma flux that results from the source models as a function of time for multiple eruptions. This is the rupture criteria of Galeto that tell us that if magma flux is large enough, more than 100 million cubic meters per year, and lasting longer than 1 year, you will get an eruption at a caldera. And here is Aniak-Chak, and we see that Aniak-Chak is just on the upper top of volcano examples where the magma flux was very large, but the episode duration was short enough, so it did not lead to an eruption. In general, the compilation is also showing that in many cases, that includes volcanoes, for example, Copagua in South America, Tungurahua in South America, Cordoncauye, Westdahl, Three Sisters, Sewam, Atka, and so on, many volcanoes in America. The formation by itself is no longer an indication of an eruption. These are volcanoes that erupted. The ones that are in orange, the ones that are in blue are volcanoes that did not erupt. So what we are observing here is that in many of these cases, inflation, the pressurization that results in ground deformation, is no longer by itself an indicative of eruptions. And this also implies that if eruptions are actually triggered by increases in magma pressure, the pressure increase must be episodic and lasting for many decades before triggering an eruption. So Aniak-Chak is quite an extreme case on a global scale, and it's only surpassed only Ambrim caldera in Vanuatu and Cordoncauye volcano in southern Chile are where we have recorded so far episodes with very large magma fluxes that have lasted for time periods which are of similar magnitude compared with those of Aniak-Chak. But for the rest, volume fluxes rarely reach these huge numbers. So getting on a more, and trying to wrap up the presentation, getting on a global perspective, what does it mean for tracking episodes like this on a global scale? I will not focus on tropical volcanoes just because they have their own issues which are outside of this presentation, but let's focus in Kamchatka, Alaska, and the Southern Andes, where we have issues with seasonal coherence. So I've been working with ALOS4 data. I have a patch developed for the ICE2 software that I can distribute if someone is interested on that. And interference acquired during the boreal winter, 14-day long, 56-day long, 42-day long, seems to sustain coherence over certain periods of time in the caldera itself. Here is, for comparison, one of the original Salcombe interferograms, 64-day long. You can see fringes. Believe me, this is real. I mean, you can see the formation. This is real. The fringes are in the original unfiltered interferogram, but this cannot be used for time series. These other interferograms for ALOS2, they are disconnected data sets. They cannot be used for time series, and that's unfortunate because the acquisition program of ALOS4 is just too sparse, and it's acquiring at most 7 SLCs per track in 1 year. But at least we have the technology right now to track these episodes of unrest that can occur in the winter during episodes of ground deformation in these high-latitude volcanoes. So more on a global scale. Can we track this all year long using the global constellation of satellites? With Sentinel, no, we can't, because unless you have an exceptional good quality interferogram like this 12-day pair, where the electrical properties of the snow did not change, that rarely happens. And I recall looking at all the Sentinel data, and there was like no other good interferogram. NISAR, I don't know, because the data that JPL has released at ASF, it's only spanning 6 12-day long interferogram. This is just too few data to draw any kind of conclusion. ALOS2 is not acquiring data during the boreal winter, so we don't know. ALOS4, some interferograms are good, some interferograms are not, so still the data is just too sparse to draw a strong conclusion. For Salcombe, some interferograms are okay, most of them are low quality, just like that of ALOS4. Ludan 1 from China, I don't know, because I don't have access to this data, and I have not seen volcano examples data from this Chinese constellation. Biomass is not acquiring data in North America because of the military applications of P-band, so no P-band data over North America. So the short answer is that despite all these missions, we do not know if we can systematically track episodes of unrest like this that occur during the winter in these high-latitude volcanoes. But I hope that NISAR will provide us the answer in the future. So, to conclude, episodes like this, like that of Aniakchak, 75 centimeters in less than 1 year, are rare on a global scale. They are not something that you are likely to observe very frequently. And that's because these high magma fluxes are episodic and short-lived. They rarely last long enough to trigger an eruption. So even if you detect something like this, the most likely situation is that it will not lead to an eruption unless something abnormal happens. We don't really have a lot of comparable cases. Ambrim in Vanuatu, I could say, is the only one, but in here, this eruption in 22 was triggered by a nearly continuous magma flux that reached the crater of Galeto. For Cordoncauye, this is work I did 10 years ago, but this is refilling of the plumbing system after a VEI4 eruption, and then the uplift decreased by the pressure gradient. Laguna del Maule might be another example. This is located in central Chile, 5 hours away from where I live. Right now, it's going up with a rate of almost half a meter per year, so it's a lot. I can talk about that later if someone is interested. But on the technical side, we need more relevant data than what we are really acquiring. And the good thing is that this seems to be an issue of coordination and not a technical problem because we have so many missions, the technology exists, it's just that we are not acquiring the right data at the right places where these episodes of unrest occur. So thank you very much to the Space Agency that gave me the data. Thank you.
All right, thank you very much, Francisco. We have time for one very quick question, if someone wants to ask something really quickly. Yeah, there's one here, and then we'll move.
It's more of a comment. So the NISAR data, you mentioned that will come in the future. The future is actually upcoming. We're planning to release the data in July. That's the current plan. That's the forward data. So you'll have to wait a little bit for the time series to build. And then we will reprocess likely towards the end of this year the previous data, which you mentioned, the one in February. And
Great. I mean, I would love to try NISAR data in here and to actually be able to answer if it works during the winter systematically in this region.
Thank you.
Okay, thank you. We'll move on to the next speaker then. This is Siwan Zhao, the interactions between the 2018 Lombok earthquake sequence in Indonesia and the unrest at Rinjani volcanic complex.
Hello everyone. My name is Siwan. I'm a research fellow from the University of Leeds. Today my topic is the interactions between the 2018 Lombok earthquake sequence in Indonesia and the unrest Rinjani Samanas volcanic complex. So the study area, the Lombok Island, is located at the east Indonesia, tectonically bounded by the Flores-Beca Trust and the Sanda Megatrust. The highly active Rinjani volcano is located at the northern Lombok Island, which is the second largest volcano in Indonesia. We can see it has a big caldera and the two volcano cones. The Barijari cone, which is located in the middle, in the center of the caldera, and the old Rinjani cone, which is located at the eastern part of the caldera. In 2018, 4 deadly earthquakes struck north coast of Lombok Island, causing thousands of casualties. The focal mechanism of the 3 main shocks are plotted in the right figure here, and we can see they are quite close to the active volcano, with the shortest distance only 12 kilometers. So the proximity of the earthquake sequence to the volcano, coupled with the stress changes, raises the questions of how the earthquake sequence influenced the volcano deformations, whether it accelerates next eruption or not. It's definitely a question worth investigating. So this big caldera formed in 1257. A big eruption occurred on the former Mount Samalas, leading to this caldera collapse. And after that, most of the volcano activities shifted from the Rinjani cone to the newly formed Barry Jericho. Nowadays, this caldera was filled with water. We call it the Sagara Anak Lake. It is a very big lake with an area about 11 kilometers square, which is one of the largest hot volcanic lakes in the world. Now let's look at some significant events in the last 10 years. So in 2015, a series of eruptions occurred from October to December, along with pyroclastic, lava flow, and ash plume. And in 2016, a similar eruption occurred in August, following small-scale explosive activity occurred in September 2016. And in 2018, the earthquake sequence occurred, characterized by an irregular shaped seismogenetic fault and a long persistent after sleep, which derived from our previous studies. So in order to figure out how the earthquake sequence influenced the volcano activity pattern, we need to understand the volcano status before and after the earthquakes. Therefore, we perform a long-term time series analysis. So in this study, over 1,200 descending and 1,500 ascending sentinel-1 interferograms are used to build up the time series over 10 years deformation. And we use LIXA to process the sentinel-1 dataset. And we use the Comet developing version LIXBus to process for the time series analysis, which means we use the re-unwrapping and the lutification approaches to keep more useful pixels. Now this is the INSA time series results. And we divide this time series into 3 distinct temporary phases. The eruption period, pre-earthquake period, which is 1 year before the earthquake sequence happened, and the core and post-seismic period. From this time series plot, we can observe 2 deformation patterns. First pattern indicates the localized subsidence up to 47 millimeters per year on the northern and eastern flank of the Barry Jericho, which is represented by point D here. Based on the location and the occurring time of this deformation, we believe this is due to the cooling of the lava flow. And the second deformation pattern is represented by the point A, B, and C, located inside in the caldera. And we can observe a deflation happen during the eruption period, and then a rapid uplift, or 1 year before the earthquakes. This kind of deformation ceased following the earthquake sequence, leading to a relatively stable post-seismic period. So this deformation pattern raises 2 questions. So why the volcanic unrest ceased, and why there is an uplift before the earthquakes? In the INSA time velocity map, we can see some, we know that this kind of deformation is inside the caldera, but from the INSA velocity map, this kind of deformation is very subtle. Therefore, we perform the time series again, but specifically focus on the caldera. And in this time, we decrease the multi-looking factor to make the ground deformation pixel 20 meters times 20 meters. And we also replace the 30 meters STRM digital elevation model to the higher resolution 12 meters tandem X digital elevation model to reduce the topographic effect. And the cumulative displacement for the pre-earthquake period are shown here. So we can see it indicates that uplift was focused within the caldera, encompassing the Barry Jericho. This localized scale of the deformation suggests the probable unrest of the hydrothermal system. However, only based on the ground deformation, it's very hard for us to deduce how this uplift happened and if this hydrothermal unrest is related with the magma behavior or not. Therefore, in order to figure out that, we also need to look at the other unrest mechanisms. We know both hydrothermal and magma-related unrest may lead to the degassing, lake surface temperature changes, and ground deformation. And sometimes these focal mechanisms will influence each other as well. For example, when the magma transforms from the deeper part to the shallow part, the transferred heat will increase the temperature of the lake. In the meantime, the chemical components of the subaqueous fumarose will change as well, which is going to lead to the color change of the lake. So focusing on a single unrest indicator can easily lead to fragmented and inaccurate understanding of the interactions. In this study, except using the SAR satellite, we also use 6 optical satellites to analyze other 4 indicators, including the sub-area SO2, water color and turbidity changes, which can reflect the subaqueous volcanic gas change, and the lake surface temperatures. So we compare the spatial temperature changes of these indicators with INSA time series to find the clues under the interactions between the tectonic earthquakes, hydrothermal, and magma systems. Now let me introduce some of the indicators. So first of all is the sub-area volcanic gas. So SO2 is the primary gas species for estimating the volcanic gas flags because its strong UV absorption features allow for detections by satellite sensor. In this study, we calculate the SO2 flags by integrating the measurements from the OMPAS and the Tropomi Sentinel-5P using the spatial average method, which is also known as the disk method. However, due to the dense distribution of the active volcanoes in Indonesia, the calculated passive SO2 flags is easily influenced by the eruption SO2 plumes from other volcanoes. For example, if we look at this plot here, we can observe a very high value in February 2021. But actually, this big significant value is not because of the activity in Rinjani volcano, it's because of the eruption happened on the Merapi volcano here. So to isolate the passive degassing from the Rinjani and mitigate the influence of other highly active volcanoes, we do some improvement. So first of all, in addition to the Tropomi L2 products, we also use more sensitive Tropomi Cobra datasets, which is capable of detecting lower column concentration than the standard L2 products, thereby improving both flux quantification and noise estimation. And also, we filtered the datasets based on the ERA wind azimuth. So we excluded the datasets with the azimuth angle between 60 to 120 degrees to prevent the SO2 plume from the more active western side volcanoes. So from the updated plots here, we can see the peak value of the SO2 in the last 10 years is in the last 6 years is in July 2018, which is exactly the month that earthquake sequence happened, and then it decreases. In terms of the subaqueous volcanic gas, we try to quantify them by detecting the lake color and the turbidity change. So the water color can be defined by calculate the Aula index, which provides a standardized measurement of water color, and it can be calculated from satellite reflectance according to the band setting of different spectrometers. So in this study, we combined both Landsat 8 and the Sentinel-2 satellite products. And from the spatial temperature distribution of the FUI values here, we can see this color change actually began before the earthquake sequence happened and spreading across nearly entire lake in 2018, and then gradually reverting. Because the chemical complexity of the volcanic gas causes varied color reflections, so analyze individual FUI values is kind of difficult. So to simplify this quantification, we define a change ratio based on the area of dominant and uniformly distributed color versus the area of other colors. So the time series plot here actually shows the change ratio of the color, and it tells us, gives us a trend of a significant color change occurred after the eruption in 2016, and then starting returning to the baseline green of the pre-eruption color during the post-seismic period. And we do the very similar analysis for lake turbidity change, which is because we know that the optical satellite is easily to be influenced by the clouds. So we use the cloud-independent sub-backscatter to analyze the turbidity changes caused by the colloidal sulfur particles, and we compare this turbidity time series with the color time series. I also want to mention a little bit about the further analysis for the ground deformation. We try to model the source based on the cumulative displacement, and we also try to make this modeling simple, which is because the coherence of the Sentinel-1 interferogram in the Rinjani caldera is quite low, which is meaning because of the dense distribution of the vegetation surrounding the outer caldera. So in this case, we meaning test two fixed radius scenarios of 2.5 kilometers and 6.0 kilometers, representing the approximate spatial extent of the caldera lake and the border of volcanic edifas, respectively. Then we perform the grid search to solve for coarse depth solution and invert for the pressure changes. So the optimum depth for the smaller 2.5 radius was found to be 5.4 kilometers. But if we increase the radius to 6.0 kilometers, then the estimated depth is only 100 meters, which is even shallower than the barometric depth of the crater lake. So which means if the shadow hydrothermal system is the primary volumetric driver, it should extend beyond the boundary of the crater lake with the radius larger than 2.5 kilometers. After we got all the information, we can summarize and deduce the interaction. And so during the eruption period, we can observe a rapid increase in SO2 flux following the eruption and observe a very high lake temperature. The floating yellow sulfur leading to a red hue in the lake color, which has been captured by the Sentinel-2 satellites here. And with the fumarolic temperature increase, the gas composition becomes SO2 dominant, increased green color component of the lake. And we can also observe a very high lake water turbidity reaches the peak, which is because of the substantial elemental sulfur and the lifting sediments related with the eruption traumas. And during the pre-seismic period, the SO2 decreased rapidly and then increased into the earthquake happened. So, and we can also observe a significant decrease on the temperature, lake temperature here. So as the temperature decreased, the proportion of the SO2 in the subaqueous degassing increased. The reaction between the SO2 and H2S formed a very fine colloidal sulfur, which increased the blue component of the lake color, and that's the reason we can observe a significant increase in the color change here. Typically, long-term post-eruptive inflation is attributed to the continuous supply of magma from a deeper mantle source recharging to a shadow crustal chamber. However, in this case, the inflation was only focused on the caldera region and coincident with a significant decrease in lake temperature, implying that deformation was predominantly driven by a shadow hydrothermal system rather than direct magma chamber recharge. When the previous eruption failed to adequately release the pore pressure within the hydrothermal system, the shallow inflation can persist continuously during the post-eruption period. During the post-seismic period, the lake surface temperature increased, and the water color returned to the baseline green, driven by the shift back to an SO2 dominant gas composition. As the post-seismic ground deformation remained flat, as we show in the previous slides, this thermal and chemical recovery was not likely caused by a volumetric ascent of new magma. Instead, we believe that the earthquake-induced fracturing increased the permeability of the edifas, allowing deep source magmatic heat and SO2-rich fluids to continuously vent into lake, maintaining high thermal flux while preventing the buildup of the mechanical strain. We also calculate the volumetric strain changes based on the co-seismic and post-seismic rupture model derived from our previous study. And we can see that the earthquake sequence induced compression at the deep magma source, and a dilatation happened in the shadow crust, which increased the pore space within the hydrothermal layer and directly caused a drop in pore pressure. And this decrease in hydrothermal pore pressure could seize the ongoing uplift independent of magma movement. So this mechanism is consistent with the flattening of the deformation curve we can observe in the inside time series. Now, to save time, I just list all the phenomena we can observe in different stages here, and also list the interpretations about the interactions between each mechanisms here as well, so you can have a look. I just want to emphasize one point, that is, rather than triggering a volcanic eruption, the 2018 tectonic earthquake actually ceased the volcanic unrest, so it will not accelerate next eruption. Thank you very much.
Okay, thank you. We do have time for a quick question.
For the lake observations, so how small a lake can you look at?
How small the lake can I look at?
Well, this is a relatively big lake, but would it work for small? I mean, it's great to see that, to use the lake observations for the interpretation. So how small lakes can we look at with these?
Well, here the lake's area is 11 kilometers squares, and it totally depends on the resolution of the Landsat-8 and the Sentinel-2 data sites. And because the Sentinel-2 data size has a higher resolution than the Landsat-8, so it works for this case. But we also, I cannot remember I can say the specific values of how small the lake could be, but we do try the same method on some other crater lakes, which is much smaller than this one, but it's not work very well. So it should be at least this large, I think. Yeah, thank you.
Thank you.
Hello, thank you for your presentation. I'm just wondering if you know whether the weather can be affecting the color or turbidity of the lake?
Yes, that's a good question. So the reason we give away, as I said, one of the reasons is because we need to find more indicators that can improve our interpretation. And the other thing is all this method has its own limitations. So we need more and more data sets to compare with each other to get more accurate results. And for the case about the weather, yes, the weather is easily influenced the optical satellites, especially the clouds. Although we applied a lot of like the cloud cloud effect reducing algorithms, but it still has some influence. So that's the reason, first of all, we use the star backscatter to support. And the other thing is that, the other reason is because not only the weather, but also because the elemental sulfur in the lake is also white. So it can be treated as the clouds sometimes when we calculate the optical time series. So that's also one of the reasons. Yeah.
Yeah, but I guess it's not just the clouds, right? I think the turbidity can be affected by increased rainfall in the area of the lake. So I wonder if it's something worth considering if the observations are affected by the weather.
Yeah, I think, well, the most effect based on the weather, I think, is the clouds. So when the cloud is a lot, it will influence the result. But the star backscatter is cloud independent. So I think it will not be influenced as much as the optical satellites.
Okay, thank you.
Yeah.
Okay, well, thank you very much. This closes this second volcano session. Please remember tonight, this afternoon, after the coffee break, there is a discussion section on both of those sessions for feedback back to ESA. So please show up to that later today, and otherwise have a good lunch. Thank you all for your questions.
Good evening, everybody. I think we should slowly start. I hope you had good lunch and you will not fall to sleep. Let's introduce ourselves.
I'm Barbara Wittheim from BGEOS in Austria.
I'm Zbigniew Perski from Polish Geological Institute, National Research Institute. And let's, Barbara, introduce the first speaker.
Our first speaker is Giovanni Costa, and he's talking about estimation of soil moisture anomalies.
Okay, so good afternoon, everybody. I'm Giovanni Costa from Radar Imaging and Digital Earth Laboratory at Polytechnic of Milan. And after lunch, we will discuss about estimating soil moisture anomalies via temporal SKP decomposition. So this is the outline of this speech. Let's start from the introduction, that is the motivation of our work. So if you assume to observe a piece of terrain through a SAR system, you can recognize in each resolution cell at least two scattering mechanisms that are acting together. We will call this scattering mechanism the ground scattering mechanism, that is modeling the above ground scatters that are more temporarily unstable, and the latent one, that is instead modeling the below ground scatters, so the moisture-related contribution that are more temporarily stable. So the main idea is leveraging on the expected different temporal behavior and on the expected different polarimetric behavior, we should be able to, in principle, decompose the ground and latent contribution. So the method we propose takes as input a Polinsar dataset. It firstly estimates the MPMT, that stands for multipolarimetric multitemporal covariance matrix. Then these metrics pass through the temporal sum of Kronecker product decomposition. The temporal sum of Kronecker product decomposition gives as output the ground and latent decomposed contribution that are described by their own R and C matrices, that are the structural and polarimetric signature matrices, respectively. And to the latent contribution is also associated, of course, the local soil moisture anomalies estimates. In the case of large dataset, all the local SMA estimates are then stitched together to provide the final unique estimated time series. So this is the workflow of the algorithm that is called Aqua SMA. So let's go a bit into the details of these actors. First of all, we have a polarimetric Polinsar dataset. We organize the data in a multi-polarimetric, multi-temporal matrix, so tiling the acquisition along the polarimetric channel. We estimate the MPMT covariance matrix, WK, where K is the number of scattering mechanisms. So intuitively, what is telling us this matrix is the story about how the mixture of scattering mechanisms are behaving in a polarimetric and temporal domain. So here is the magic of the approach, the core engine, that is, given this composite matrix, let's try to decompose, to factorize it as a sum of K Kronecker products between simpler matrices, which are C, polarimetric signature matrix, that is describing the polarimetric behavior of the decomposed scattering mechanism. R is instead the structure matrix, that is describing the temporal behavior of the decomposed mechanism. So, of course, the decomposition is not forced to give always a solution, because we have to ensure physically admissibility of the solution. So both matrices must be Hermitian semi-positive definite. Now, how many K do we need? 2, ground and latent contribution, and as you understood, the solution is not unique of the decomposition, so we have to find a criterion to choose what is the best solution that we need. In the case of two scattering mechanisms, Stefano Tebaldini provided a closed form of the solution that depends on two real parameters, A and B, that are automatically regressed by the algorithm. So the idea is that among all the possible A and B pairs, we need the ground contribution that must act as a phase calibrator. So the ground contribution is, in the end, the one that is minimizing the phase residues. The latent contribution must maximize the similarity between between what we are decomposing and observing and the moisture-related, a theoretical moisture-related effects on latent interferometric features. So let's focus a bit on the latent contribution selection, keeping in mind that the structure matrix is in the end the covariance matrix of the moisture-related effects. So among all the possible physically admissible structure matrices, let's call them R2, RL is defined through exhaustive search as the one that is minimizing, in an L1 norm sense, the error between all the elements inside R2 and the theoretical moisture model effects onto the interferometric features described and depicted in the slide that follows, the one proposed by Francesco De Zan. Then, once the latent structure matrix is selected, is clearly associated the differential soil moisture matrix that is used to invert our soil moisture values through iterative reweighted least square. Of course, this system is rank deficient, meaning that we need to impose a datum. Our datum is the zero mean condition, meaning that our solution is defined up to an additive constant. And the domain of the solution is called soil moisture anomaly. So let's say is in a pseudo-volumetric units. What I want to stress here is that even if our solution is defined up to an additive constant, the anomaly domain is inherently informative because we can study and monitor the trend, the dynamics, and also understand the relative range of variation of soil moisture. So no panic, because we are after lunch. Here you have some graph about performance analysis, but the keynotes are that Aqua SMA effectiveness depends on the temporal and polarimetric diversity of the scattering mechanism, and the effectiveness is much more related to the number of loops over which the MPMT covariance matrix is estimated. We need at least 100 number of looks rather than the number of acquisition over which we are estimating the matrix. So what happens in the case of a large data set? We can scan the data set opening temporal windows of size BW, then we store locally the SMA estimates, and then we stitch together to provide a unique time series. What about the optimal window size? It ranges from 4 to 12. Of course, the smaller, the better. And what happens in the case of a large data set, a very large data set, so 10 times the temporal window? You can apply Aqua twice, one on the full temporal resolution dataset, the other on the subsample version of the dataset, and this helps us first to recover a long-term trend of soil moisture, and also, as we will see, to mitigate the vegetation-induced divergences. So, take-home messages: Aqua SMA consists of temporal SKP decomposition, exhaustive search, 2 linear system inversion, and that's it, basically. It does not use phase closures and triplets, but it directly inspects the decomposed complex coherences, and the estimates are defined up to an additive constant, and the anomaly domain of definition is inherently informative. Let's go analyzing real data results. In the Hydrodrone project with HISA, I applied this algorithm onto the hydrosoil campaign that uses a C-band fully polarimetric ground-based radar to continuously monitor, mimic Hydroterra Plus mission, agricultural field. We have 2 main campaigns, the barley one and the corn one. For the sake of time, we will discuss just the results about the barley campaign. About the processing procedure, Aqua was applied considering the entire field as a unique resolution cell because of the small size, and scanning the dataset with 6 acquisitions, so a temporal span of 1 hour. Moreover, multi-temporal synthesis has been applied considering 10 minutes, so full temporal resolution dataset, and the subsample version in 24 hours. Before going into the analysis of the results, I want to keep your attention on the depth, the different sensing depth of our measurements and the probes, because the probes are 15, 20 centimeters deep. Instead, our radar measurements are practically superficial, so we have to expect advanced in our estimates with respect to the probe. So, okay, let's see some SMA time series, Barley campaign, as I told you, birth soil stage, so you have the picture on the of the phenological state. You see on the x-axis of the graph the temporal acquisitions, on the black y-axis, the one on the left, the absolute soil moisture, just to track the values of the probes. On the right one, the blue one, the soil moisture anomaly, so our domain of definition. This is just to demonstrate to you the effectiveness of the domain, even if we are not in the absolute one. You see that there are two reinitialization points that are the green squares. What means reinitialization points? Temporal SKP didn't find a physically admissible solution, so a single scattering mechanism and dominant scattering mechanism has been recognized, and this information is passed through the stitching procedure to reinitialize the stitching. So these two reinitialization events correspond to rainfall. And what I want to underline here is the very high capability of both recovering high and low frequency variation of soil moisture, and also the effective range of variation. If we move in May, so mid-May, you see that the barley was more or less 15-20 centimeter height. Even in this graph, you see the capability of estimating high and low frequency variation, and here is clear what we were saying so far. We are experiencing an advance in our measurements. So what we did up to now is to analyze the temporal behavior of the estimates. So in the end, the temporal capability of describing of aqua, of describing soil moisture variation. But what about the information in each polarimetric channel? If we do a quick step back, we said that each scattering mechanism is described in a polarimetric and we can say interferometric way. So if we take the polarimetric signature matrices, the CL and CG matrix, the one of the latent and the one of the ground, we can effectively try to understand what's going on inside the polarimetric channel. And to do so, we propose the calculation of the latent to ground ratio, that is the ratio between the main diagonal elements of the latent contribution and the main diagonal elements of the ground contribution. So let's look into the results. You see the top graph, the crop height of the barley along the campaign. In the bottom graph, the latent to ground ratio. In particular, the blue curve is the VV channel, the purple is the HV channel, and the red is the HA channel. What's happening is that it's clear to see a correlation of HV and VV latent to ground ratio with the vegetation growth. And how this impacts our estimates, if we look into the last month of estimates, despite the reinitialization point, you see in the light blue curve, the one that is dashed, this guy here, you see that if you consider just the 10 minutes estimates, so the full temporal resolution estimates, a divergence is present with respect to the signal, that is the measurements taken by the probe, that are correlating with the vegetation growth. Instead, by combining multi-temporal estimates, we are able to mitigate these effects. This just because the vegetation can be considered mostly decorrelated after 24 hours. So that's what I was saying in the very introduction. So, perfect, I'm on time. Let's conclude. I present AquaSMA, that is a novel polarimetric framework for soil moisture anomaly retrieval. The core engine is the temporal SKP decomposition. Key insight, definition of the soil moisture in the anomaly domain, and I demonstrated that it's effectively a domain that from which it is possible to recover and to understand effectively the dynamics and monitor the moisture. The multi-temporal synthesis helps to mitigate divergences induced by the vegetation growth, and the estimated time series looks show a good match with available probe measurements. Moreover, I want to stress this concept, the polarimetric information that can be studied through latent to ground ratio analysis is providing additional information and very meaningful physical insight about what's going on into the estimates. Limitation, EV rain or irrigation, so in case of EV hydrological innovation of the soil, temporal SKP recognize a single dominant scattering mechanism and no decomposition is performed. About outlooks, testing aqua on other datasets, so different frequencies, different crop types, investigate dual pole adaptation of aqua to see if it can work also in dual pole. I'm quite confident. And journal paper is in the final preparation stage. So I enjoyed a lot. I hope you too, and thank you for the attention.
We have time for a couple of questions.
If not, I have one. In your test area, it's flat, but in real world, we have changes in elevation. What you expect kind of effect or difficultness if you have mountain terrains, for example?
Okay, in this case, we have no baseline, first of all. So even if we have no normal baseline between acquisition. I tested it on airborne-based campaign and it works. Of course, there's an impact of normal baseline. If I go back to the synthetic performance, I'm trying to go back to the synthetic performance analysis. I stressed a bit. Okay, you see here, for example, okay, where a baseline decorrelation is present, and you see that effectively the performance gets worse. But most of interest is that in the end, it's more the effectiveness is more tailored to the effective temporal diversity of the scattering mechanism. So you have an uncertainty that is increasing if you have topographic, so you have baseline and you are sensitive to topography. But in the end, the most impactful characteristic is the temporal behavior. Because if you, for example, if you do not have the temporal diversity, it's raining, so both ground and latent are decorrelating, okay, a single scattering mechanism is recognized. This does not happen in the case of geometric or topographic diversity, actually.
Are there any other questions? Yeah, Stefano?
Thank you. So now my question, request for a comment maybe. Yesterday there was a lot of talks about the phase closures and the triplets for soil moisture, and so it seems like everything was inside this phase closure. So can you comment on how this work relates to the phase closures?
Yes, I can comment. The idea, we are not directly using phase closures because in the end, when ground solution is taken, we are applying phase linking. So we are recovering the phase residues, and then the part of the phase residues, so the signal that is not closing, that is not triangular, is passed to the latent contribution. The idea is that phase closures are somehow ambiguous, and in the end, I think the most powerful tool of this approach is directly exploiting the interferometric pair, not free interferograms. That's how it relates.
Are there any other questions or comments? If not, let's go to the next speaker, is Barbara Wilton. And she will talk about seasonal deformation rate obtained from Sentinel-1 insert analysis across Arctic lowland permafrost region, reflect soil moisture gradients.
Yes. So basically, we want to derive soil moisture gradients for Arctic lowland permafrost regions by using seasonal deformation rates. So Arctic permafrost regions are characterized by 3 thaw cycles, which happen in the active layer. This layer is the layer above the permafrost, which seasonally thaws in summer. And through this, we get subsidence, which can then be counted by frost heave in winter. And it's especially a considerable surface displacements, especially for ice-rich permafrost regions. And this happens due to the phase change of ground ice to liquid water. And the amount of ice or water in the ground, therefore, also is linked to the amount of surface displacement. And we want to make use of this linkage in order to derive a general soil moisture patterns. So there exists a couple of remote sensing techniques in order to derive near-surface soil moisture, using a couple of different sensor types. For instance, optical or thermal infrared can provide high spatial resolution by using reflectance indices or the thermal inertia. However, for the Arctic regions, they often can't be applied due to the frequent cloud coverage. So microwave sensors have the advantage to penetrate clouds and possibly can then provide high temporal resolution. Both passive and active microwave sensors make use of the dielectric properties of liquid water compared to the other soil materials. The products of passive microwave sensors, however, have only a low spatial resolution, which makes their applicability for the Arctic regions also very limited, because these regions are very heterogeneous, and we do need higher spatial resolution products. And furthermore, it has been shown in previous studies that microwave products for soil moisture show only low reliability in Arctic regions, often with substantial biases. So we therefore want to take a different approach in order to derive soil moisture from microwave sensors. And we are looking into this thaw season subsidence rates. For this one, we see this example is of the Chersky region in the northeastern Siberia. And we can see next to these lakes and this partially drained lake, we see that we have higher seasonal deformations, and we expect these regions also to be of higher soil moisture. So in our study, we primarily focused initially on 2 study sites, on the Yamal region in northwestern Siberia and the Inuvik region in northwestern Canada. For both sites, we have in situ data. For the Yamal site, we do have subsidence measurements, which are measured at the calm grid, which is an active layer monitoring site. For both sites, for the Yamal and the Inuvik site, we do have in situ soil moisture measurements. For Yamal, these were collected in 2015. We measured at each calm grid point, which are 121 points, and at 7 transects and some additional points. For the Inuvik site, we did measurements in 2023. Unfortunately, this was a drought year, so we do have drought conditions here, which we have to consider in the further analysis. And here we measured also at several transects and additional points. All these are indicated on these maps. So our workflow, we used Sentinel-1 data, which has a repeat cycle of 12 days for most Arctic regions. We processed our interferograms in series, meaning from one date to the next. Longer time steps were unfortunately often not possible due to the quick loss of coherence. We derived then the per pixel deformation time series. And in previous studies, it has been shown that there's a linear relationship between the seasonal subsidence and the cumulative degree de thaw, or DDT, which is a measure of seasonal heating. And this is similar between the years, contrary when using, for instance, the day of year. This is depicted here on the right. We therefore then derived the DDT from era 5 temperatures and calculated the per pixel linear regression of these seasonal deformations with the DDT values, and derived the regression slope, which gives us the deformation rate in DDT domain, which we from now on refer to as alpha DDT. We calculated these alpha DDT maps for multiple years and derived the median from these years. And these median maps were then compared to the in situ data in order to derive general soil moisture patterns. So, but first we compared our INSA results to the in situ subsidence measurements that were conducted on Yamal. There the yearly subsidence was measured by inserting metal rods, L-shaped metal rods into the ground through plywood plates until they got fixed at the end, at the base of the active layer. And in winter, through the heave, this plate and the metal rod gets pushed up, while the plate subsides with the ground during the thawing season, and the increment between the end of the rod and the plate is then taken as ground motion. We see for this comparison to our INSA results that we have lower INSA subsidence values compared to in situ values, which has been also noticed in other studies in the Arctic. And this can be attributed to a couple of reasons. For one, the in situ measurements are point measurements, and our medium scale INSA measurements may therefore underestimate the true displacements due to spatial averaging. Furthermore, we can't fully rule out that our reference point that we selected also experiences some kind of deformation. We furthermore might also underestimate the subsidence values during the unmonitored beginning of the thawing season, which we couldn't monitor due to low coherence values. And furthermore, soil moisture variations have to be considered because soil drying leads to an uplift signal and therefore also lower INSA subsidence values. So we then compared our alpha DDT values to the in situ soil moisture measurements here on the left. In blue, we see the results for Yamal, where we see that, in fact, we have higher soil moisture values for greater subsidence values. However, for the Inuvik site, where we had drought conditions, we naturally see that there are lower in situ values, but also the relationship that we found for Yamal is not that clear, only for values below 50% volumetric moisture content. We see that there are lower in situ values for lower alpha DDT values. Then we did some comparison to other moisture indices to the topographic wetness index derived from the Arctic DEM with 2-meter resolution, and to the normalized difference moisture index derived from Landsat 8. For the topographic wetness index, we see that we again have for Yamal higher soil moisture values for higher topographic wetness index values. However, for Inuvik, this relationship is again not consistent for values below 30% volumetric moisture content. And for the NDMI values, we have no stringent relationship, while for Yamal, there tend to be higher soil moisture values for higher NDMI values, and the opposite is, however, observed for the Inuvik region. So in order to calibrate our data, we've now focused only on the Yamal dataset, because there we had typical moisture conditions compared to the Inuvik site where we had drought conditions. And we separated our in situ data in a calibration and validation dataset. And due to the high heterogeneity of soil moisture patterns and differences in geolocation and spatial scale between in situ values and INSA values, we binned our in situ values into increments of 10% volumetric moisture content and calculated for these bins the median values of alpha DDT. And for this, we derived now this linear relationship, for which we derived a coefficient of determination of about 70%. This shows now the validation data set, where we got a root mean square error of 14% volumetric moisture content. So in order to derive maps of general soil moisture conditions, it would, for instance, be suggested to only derive, for instance, 3 soil moisture classes. And a map of this is shown here for the Yamal study site. To see now how this compares to other soil moisture products, we now also made use of the Arctic Boreal CO2 flux database, which was previously available, and has also some in situ soil moisture data as auxiliary data. For this, we see here again the Yamal study site with also in situ data from the AVC flux database. And we compared it to the soil moisture products of CCI, as well as to the radiometer products of SMAP and SMOS, and to the reanalysis data of ERA5. And we see, again, like for other Arctic regions, where we have that the coastal resolution satellite product deviates from the in situ measurements, showing significant biases. Only the ERA5 soil moisture data has a better agreement than the coast-scale satellite products. But we now did this comparison also for 2 other sites, again Inuvik and Tuczersky, which are both more transition zones to a more boreal region. And here we see that the results are quite varied, and it's hard to draw general conclusions to say which product performs best. Also, our INSA results show a quite substantial spread here. And now this shows for the whole Yamal Peninsula how this INSA result that we derived compares to these other solutions. And it gets visible that, in fact, it would be very beneficial to have a high-resolution product of soil moisture for Arctic regions, because the information gets lost in the coast-scale products. And some other applications of seasonal deformations for the Arctic regions. Here on the left, we see from the paper of Ivanova that it can, as seasonal subsidence can be used for upscaling methane fluxes. And it showed a higher correlation than other tested parameters. So it is an indication that seasonal ground displacement has some information about water availability in these regions. Also then another paper by Barch et al. In 2026 showing that that the seasonal subsidence is increased in drained lake basins, which also tend to be of higher soil moisture, and we see higher seasonal subsidence also in areas close to infrastructure, which also often show thawing features. So to conclude, I showed a novel approach for deriving soil and soil moisture index of general or predominant moisture conditions for Arctic permafrost regions based on seasonal subsidence signal rates. We had higher surface subsidence rates for wetter regions and could derive spatial patterns of wet and dry areas, which are linked to methane fluxes, for instance. And for our calibration validation site of Yamal, there was a better match with in situ values compared to coarse scale data sets. However, these results were very varied between the regions. Thank you for your attention.
Thank you very much, Barbara. Any questions from the audience? Maybe comments? Yes, we have one.
Yeah. Did you only try with C-band data? Or
With C-band data?
Yes.
Have you used Sentinel-1?
Yeah. You may expect different behavior with different wavelengths.
So if you want to, for instance, I mean, if we want to use L-band data, for instance, we could use, for instance, pulsar data, but we found that there are not that frequent acquisitions during the season, so that is a bit of an issue there. But we have not yet tested other bands, no.
Any other questions? Yes.
Thank you for the presentation. I wonder, how did you collect the in-situ measurements of soil moisture? What is the strategy, and is it gravimetric or like TDR measurement?
We used a handheld device, the Theta T probe. So we measured in the uppermost 5 centimeters, which may be also an issue correlating it to the INSA values, because they might rather represent not only the top layer, but on the whole active layer information.
Thank you. Any other questions or comments? Maybe I have one. Did you consider maybe also include in your research, especially in situ data from Svalbard? Because I believe there are many groups working also on similar subjects.
Yeah, I think Lynn Royer also did some correlations with some areas that are considered wetter or drier, and also found some kind of correlation there. But we ourselves did not do INSA measurements there, so yeah.
Okay, thank you very much. So let's go to the next talk. Who will be given by Małgorzata Małych-Szak with a team from Adam Mickiewicz University in Poznań. And she will be talking about detecting forest leaf-out from Sentinel-1, interferometric coherence, evidence of structural reorganization in early spring.
Yes, thank you so much. So hello, everyone. I'm going to be talking about something that a lot of you refer to as a noise, which is vegetation. And I'm going to show how radar metrics can be used to investigate the development of the vegetation. So firstly, let's start with the spring phenology of deciduous forest. So the forest can be constructed with different layers. At the bottom, there is a forest floor, Then there can be understory plants that are reaching from half of the meter to 5 meters. And then there are the main canopy big trees that are much larger. And the thing is that all of these layers green up with a sequence. So with the early spring, when everything is still dormant and there's more sunlight coming to the bottom of the forest, and when the temperatures are rising, the forest floor starts to green up first. Then the understory plants follow up, and then eventually the canopy also leaf out. Those kind of changes can be very rapid. Here, within 1 week of a difference, you can see that from a forest that looks like there is nothing happening there, a lot of new scatters develop during a week. Although here, small leaves are already there, but you cannot see it as probably in the picture. But spring development does not only change the color of the forest, but it also changes its physical structure, introducing a large number of new scatters. And here on the right, we see that the canopy is still largely open, where on the left, the understory started already to develop, modifying the distribution of the radar scatters. And as I mentioned at the beginning, spring development does not start in the canopy. It starts at the bottom of the forest, and the layers green up from the bottom up. Here at this image, you see that the canopy remains still dormant, but the middle part, the understory plants, already develop, and they introduce a lot of new leaves that are substantial structural change within the forest volume. And also, eventually, as the canopy will also start to green up, and it will add even more potential scatters to the forest volume. But why does it matter at all? Why does the day of the spring onset matter? So it triggers the web of a lot of different interactions. Firstly, the timing of spring onset influences the length of the growing season and overall forest productivity. It also marks the beginning of the active photosynthetic period. It shapes the interactions between the land and the atmosphere. Also, many species rely on the timing of spring development to synchronize their feeding, reproduction, and migration processes. And last but not least, it is a very good indicator of climate change. So there are several ways to detect spring onset. The most traditional one is from the ground observations. Those kind of observations are usually very accurate and detailed, but they are very local and labor intensive. To meet up this disadvantage, we can use the Sentinel-2, for example, optical data that work on much larger scale. However, they're usually very influenced by cloud cover. And for example, in Poland, during early spring, in March and April, there is a lot of scenes that are fully covered by clouds, so we have no data. And also, NDVI will tell us about the greenness, but it will not tell us about the structure of the forest. And we can also use the radar data. In a lot of literature, they use the backscatter that already meets the disadvantage of the clouds because it's all-weather working. However, in our primary results, it was strongly affected by rainfall, and we couldn't isolate the vegetation effect itself. So we wanted to see if it's possible to use coherence and phase information to detect the spring onset, and also are SAR data more sensitive to early spring development than optical data. So to do that, we used the information from 4 different data sets. Firstly, we collected the ground observations in 2025 and 2026, which provide the reference to leaf-out dates. Then we used the Sentinel-2 imagery to derive NDVI time series. We also used Sentinel-1 interferometric observation, and it extracted both coherence and resultant length. And also we included TerraSAR for 2026 year. And from this, we smoothed the data and we calculated the start of the season. And then at the end, we compared the ground observation with satellite observation. And in addition to this, we also compared coherence and resultant length from TerraStar and Sentinel-1 with the time series of growing degree days. And this is a meteorological identifier of accumulated heat that is available for the plant development. So the study area is located in Poland, and according to Forest National Data Bank, it's fully covered by one main tree species, which is Betula pendula. This is a bird tree. I'm sure all of you saw it because it's very characteristic with the white bark, but it's not important now. Let's see the first result. So to better understand the biological meaning of the radar signal, let's look at the coherence results against growing degree days. So across all data sets, coherence generally decreases as growing degree days increases. So you see the decrease with growing degree days increase. And the strongest changes happen at the relatively low growing degree days values, corresponding to the period of rapid spring development. And as the temperature accumulates with growing degree days, the forest undergoes structural reorganization associated with understory development and leaf emergence. And here one important point is that until March 2025, we could only use the interferograms of 12 days. So to compare it better with 2026, we also created the same data set. And here the drop of the results is not so significant. So the 6 days interferograms exhibit better results. And similar to this, we also observe the same for resultant length. There is a big drop at the beginning of the cumulative growing degree days. And if we compare it also with 12 days interferograms in March from 2026, the result is worse than with the 6 days interferograms. And for TerraStar, just to show you and to compare, the drop is more steady, but it also drops, like the mean coherence and resultant length values drop with the accumulation of the heat. And now those are the results of like raw mean data. So, okay, here's a mistake. It should be WH polarization. But for all of these results, not all, okay, for TerraStar, you can't really see the fluctuations because the scale here is very large. But for Sentinel, you see that there is a rise of the values with the beginning of March. The low values in the winter months are because of snow. But with March, the snow cover was gone, and the coherence values could rise. And then we see the drop of the coherence values in March and April. And the same we see for resultant length results. There is even more pronounced rise for Sentinel-1 in 2025, and also for TerraStar X. There's also a mistake here, should be VH. But you see that in all of these data sets, there is a rise in March, April, and then the values go down. So let's see how it will look if we smooth the data and try to calculate the start of the season. So I will jump now to Sentinel-2 for a bit. So here are the available dates with observation and the dates that we could use in the study that were clouds-free. And as you see, it's very low amount of the data that was possible to use. However, we did take those data and we calculated the phenological curves using the gum smoothing method. And based on that, we set a threshold of 20%. That's usually how it's used in the phenological studies. And this 20% of threshold between minimum and maximum, we assume as a start of a season. And there's also an inflection point, which is the point where the curve increases at the fastest rate. And it can be correlated with vegetation, that when the vegetation greens up the most rapidly. If we do the same for coherence and R results, that's how it will look for the year 2025. There's also a curve. However, the values do not rise, they drop. But for each acquisition and each year, no, this is 25, but for each polarization, you see that there is a peak of the values in the beginning of March, and then the values drop. And using the same threshold of 20%, we calculate the start of the season. Here, it's the same for year 2026, and also for Terasar. And we see that even for Terasar, in those first results, the plot was more steady, but here with better resolution of the scale, you see that the values are not actually steady. There's also a drop of the values. And let's see how it will look if we compare these dates with the dates from the ground. So here I put all of the dates on the axis. They indicate the timeline. And here at the top are chosen dates from ground observation when we observe that something happened. So on the 10th of March, we observed that the forest floor, the most bottom part of the forest, already started to green up. However, the understory plant and the canopy was still dormant. Then on the 22nd of March, the forest floor increased its green up, and the understory started to emerge leaves. And then on the 6th of April, only the canopy started to green up. However, the forest floor and the understory had already much developed parts of the plant. And if we compare these dates with the satellite dates, you see that from the NDVI, we get the closest value to the date when the canopy started to develop, which means that it stays quite, like, it doesn't see these earlier changes. And then for all the other results from radar data and the metrics, we see that those start of the season days are much closer to the actual dates that happen in the forest. Here I also put the inflection point that was calculated for NDVI, but they do not seem to have biological meaning, since I think it's mostly because the curve flattens very quickly. So perhaps there would be another method to calculate the most rapid development of the forest, but for a start of the season, this method seems to have very good result. So one more thing. If we remember this date of 5th of April or 6th of April, when the canopy started to emerge leaf, we would ignore these changes that happen in the forest much earlier, like on the 26th of March or on the 2nd of April, when there was already a lot happening there. So to conclude, the spring phenology develops over a very short time window, so it highlights the importance of frequent observations. As we saw for Sentinel from 2026, we got better results than for 2025, or more pronounced. Also, coherence and resultant length reveal clear spring transition in both Sentinel and Terasar datasets. Similar start of the season estimates were obtained across all the radar sensors, frequencies, and metrics. And radar-derived start of the season occurred earlier than NDVI-based start of the season. And last but not least, this earlier response can suggest that SAR observation actually do capture the structural changes associated with early spring development before the strong canopy greening becomes visible in the optical data. Okay, thank you so much for your attention.
Thank you very much. Are there any questions?
Thank you for your presentation. I was wondering how you decided, how is the threshold of 20% of the increase decided?
It's based on the literature. It's usually used 20% or 10%, but it's only like 1 or 2 days maybe difference, maybe, but that's like based on the literature. That's how it's usually done. So we just put this threshold, and here, as we compare it with the ground observation, it corresponded to the main canopy development. If we put it earlier, but the same was done for the radar, also 20%. So probably then radar would show a little bit earlier results.
Okay, thank you.
Any other comments or questions?
Hi, thank you for a great presentation. I'm working on phenology a bit, but with Sentinel-2, and I'm wondering, how do you address the resolution of satellite images and your ground observations? So you are just analyzing single trees, right? And there is this, or like an entire stand, because you said that you have like silver birch stand. And second question is if you plan or maybe you try to analyze the GDT relationship with the start of the season.
Thank you so much for your question. So to answer the first one, yes, I am analyzing the whole stand, but it's very labor intensive and sometimes very complicated to like monitor each tree separately. So I go to the forest, I go through some paths, and I try to like get the general picture out of it. So there is sometimes I'm having like observation of like, okay, 20% of the trees started to leave out. But yeah, it's never very precise, but all of these measurements have the drawbacks and the advantages. So, and to answer the second question, what was GT? Okay, I didn't compare it with start of the season yet, but that's the plan. Thank you.
Any more questions?
Thank you very much for your presentation. I just have a question, methodological question. Did you plan to use some meteorological data or some kind of station inside the forest so that you can estimate somehow the moisture of the ground and the air? And second, why don't you use simple camera to just monitor in real time the vegetation growing during the same period, so you can have some time series during the acquisition, satellite acquisition, and just try to figure out why you have sometimes big divergence between your point and your model? Perhaps this is just a correction about some moisture parameter or humidity parameters.
Okay, I will answer the first question. So there are some meteorological data from the stations nearby. However, they are just like the precipitation data, so I don't know if it will be enough to do the soil moisture analysis. I'm not an expert, so you might answer me if you know. But I didn't understand the second question, I'm sorry.
It's just a suggestion. You are trying to monitor the growing of the ground and the median. I don't know exactly the exact term, but the canopy and the ground between the two. If you have a camera, you can just see if the leaf and the plants are growing inside the forest. You have a camera and you see if there is some green appearing. You can characterize the state of your forest just using a camera. And from that, using a camera, just to see, to compare in your forest test. Not clear, perhaps. Just using a camera.
Yeah. Okay. So
to
I will
see
that.
at what stage the forest is in this growing. So you can compare it with your data and see if it can correspond with your double curve and match if it will match.
Thank you. Thank you for the idea. Okay.
No? Okay.
Thank you very much. I think there is no time for the next questions, so let's continue the discussion during the coffee break. Thank you very much.
So our next presentation is given by Valentine Schnell, and she's talking about seasonal variations in persistent scatter density.
Yeah, thank you for the introduction. I'm not Valentine Schnell, I'm Madeleine Evers. Valentine is my bachelor student, and I'm going to present his work today, which is on seasonal variations observed in persistent scatter density while we experimented with different strategies to process a SAR image data stream for long continuous monitoring tasks. Yes, as I already said, this observation was made during some experiments concerning processing strategies, and our main concern, why we wanted to test different processing strategies, was we wanted to always have a sufficient persistent scatterer coverage and also high frequency for the updates and of course processing efficiency. We tested 3 different strategies which are visualized here in the plot, and I will go more into detail on these in the other following slides. These 3 different strategies were tested on a data set of 300 Sentinel-1 images, which were then subdivided into temporal subsets to simulate an incoming SAR image data stream. And the first strategy is, I think we could call it the classical strategy, to always use the entire data set which is available. So meaning with every new image, the entire time series is reprocessed. The advantage here is that we have timely updates, but on the other hand, with the increase in the time series, you have a decrease in the persistent scatter density and also an increase in the processing time. 2 things which we don't want. The second and third strategy were to process the incoming data in subsets. For strategy B, these subsets were non-overlapping, so you had a set number of SAR images in each subset, and once one subset was processed, you had to wait until enough new images were acquired to update the dataset. Here, the PS density remains relatively constant, as well as the processing time, but we had long waiting times for each update, and also the reference image had to be changed with each subset, which hindered the continuous evaluation of the persistent scatterer results. The third strategy was to have the subsets overlapping, meaning with each new incoming image, one image was discarded and a new subset was processed. This combines the advantages of strategy A and B, meaning we have a relatively constant PS density and processing time, but also timely reprocessing is possible. The reference image does not need to be changed with for each subset, and the results can be evaluated continuously. We favor strategy C. And I had a poster yesterday going more into detail how this could be implemented. However, the work of Valentine concentrated mainly on strategy B, because in strategy B we observed high variations in the persistent scatterer density between the different subsets. And these subsets for strategy B always covered half a year. So we had half-year slices for the summer half-year and for winter half-year, meaning once from November to April and from May to October. And in the plot here, you can see that we have some peaks and kind of a periodic signal, and which is not marked down in this plot, but the even number of subsets are always the summer half-year. So for each summer half year, we have a peak and a drop in the persistent scatter density for the winter half year, with the exception of subset number 7, and also quite obviously, subset number 8 is an extreme outlier with the overall most persistent scatter density. So we wanted to know what influences this variation in the persistent scatter density. And with the seasonality, which became apparent in the last plot, we thought that this is concerning to environmental factors. And here it comes into play, there we are actually. So the area of interest is located in southern Greece on the Peloponnese Peninsula, right here. And it covers mainly the city of Patras and some suburbs and some rural areas here in the mountainous region. And for the Peloponnese Peninsula, we have a climate type called Mediterranean hot summer, which means we have hot, dry summers, mild, wet winters, strong seasonality and precipitation. And concerning the topography, we have, it's also quite diverse. We have flat areas here at the coastlines, then steep foothills and high mountains here more to the eastern border of the area of interest. And what Valentin did is he acquired data concerning these different land cover types within the area of interest. At first, he took a look at the OpenStreetMap data, which you can see in the image right here, which is an excerpt for the area of interest. And the advantage of OpenStreetMap is that you have a high spatial resolution and it's constantly updated. So it's always quite up to date. But you can also see here that there are big wide areas where we have no label for the land cover. So we have poor coverage in rural areas, which is why Valentin also took into consideration the Korean land cover map, which is mainly based on Sentinel-2 data and some Landsat-8 images, and covers the time period between 2017 and 2018, which is smack in the middle of the ZAR time series which we used, which extends from 2016 to 2021. Here we have a lower spatial resolution, as you can see in the image down here, but we have a good coverage for the rural areas. And what he had to do was to combine these two data sets. So therefore, he had to first find common land cover class types, because both data sets were quite detailed in the different land cover labels, up to 40 different labels, which is a measure of detail which we didn't need. He decided for these different land cover classes, urban fabric, industrial, mine dump construction, artificial green, arable land, permanent crops, pastures, forests, scrubs, open spaces, and water objects, as well as highways. For water objects, I have to say, these are not meant that there are PS on top of the water, so it's PS due to objects which are close to the coastal areas, such as here in the harbor area. In addition to that, he had polygons for each of these land cover types, which he had to intersect, especially in those areas where the OpenStreetMap data and the Korean map data overlapped. And he had to decide according to the ZAR geometry which different land cover types took precedent. For example, if we were in an urban area, it was more likely that the persistent scatter belonged to a building than, let's say, a park area. After he combined all these data and intersected the new polygons for the land cover types with the persistent scatterer results of each subset, we had these time series here, which gives you the persistent scatter density for each land cover type for each subset. And we can see here that each land cover class is affected by this variation, but we can also already see that some classes are more affected than others. which becomes more evident if we are not looking at the persistent scatterer density, but towards the deviation of the mean persistent scatterer density for each land cover class type. Here you can see that, for example, the class urban fabric is not as affected by these variations as, for example, permanent crops. You can see that the more anthropogenic, the land cover type classes characterized by anthropogenic structures are less affected than those characterized by vegetation, which is quite intuitive. And therefore, we further divided or further combined these land cover type classes into a class characterized by anthropogenic infrastructure, for example, which would be urban fabric industry, but also highways, and one which is mainly characterized by vegetation, which would be arable lands or forests. If you combine these two, you would come out with this map, and of course you would see that the city area of Patras is more anthropogenic and the suburbs are more characterized by vegetation. And if you then intersect this again with the persistent scatterer density, again with the persistent scatterer results, you get again two lines for the point density, and you can see here again that both categories are affected. But if you take a look at the deviation of the mean, you can see very clearly that the vegetation characterized land covers are more affected by the seasonal variation, which led for us to the belief that this is influenced by environmental factors, which is why we in the next step took a look to environmental factors such as precipitation, which is here marked as the blue bars. This is the sum for the entire time span of a subset. And in red, the temperature, which is the mean temperature for each subset. And the soil moisture is also the mean value for each subset. And you can nicely see that for each peak in the persistent scatterer density, we have a peak in the temperature, but we also have a low value for the soil moisture and the precipitation. And you can also see that even the outliers make sense in this context, because the outlier subset 7, which should have a lower persistent scatterer density than subset 6, since it's the winter half of the year, but it doesn't, is because if you take a look at the environmental parameters, you can see here that both the precipitation and the soil moisture are way lower than in all of the other winter half years. And the second outlier, subset 8, is a similar story. Here again, the precipitation and the soil moisture is way lower than it was in other summer half years, leading to this extremely high persistent scatterer number. And therefore, we conclude that soil moisture and persistent scatterer in vegetation characterized areas has a high influence on the achievable number of persistent scatterer. And if you want to analyze a longer time series, not just half a year, it might be advantageous to drop those images which were acquired during these periods of high soil moisture and high precipitation. So to sum it up, we observed seasonal variations in the number of identified persistent scatterers in case an incoming image SAR stream was processed in semi-annual slices, and these persistent scatterer results were intersected with data concerning different land cover types. And we could observe that anthropogenic land cover classes are less affected by these variations than land cover classes characterized by vegetation. And these variations coincide with variations in precipitation, soil moisture, and temperature. And therefore, we would recommend to drop SAR images recorded during these times. However, in this study, the time spans which would be dropped would be half years, which is quite a large data gaps. So therefore, we would like to narrow this time span down to only a couple of images. And also, we would like to test this for other climate zones. As I said in the beginning, we were in the Mediterranean area, and it's probably going to look quite differently in Scandinavia or Germany, for example. So thank you for your attention. If you have any questions or comments, please don't hesitate to ask.
Thanks for the presentation. Are there any questions? Maybe I have one.
Yes.
Did you see any differences in quality of your results compared to your time steps, if you use overlapping time steps or the whole time series?
So yeah, the main reason to do either overlapping or non-overlapping was to find a good strategy for monitoring tasks more concerning deformation. This was the talk here was more of a observation which we didn't expect to make during those tests. And the quality of the results in those cases is kind of similar. It was more about processing efficiency and having a good enough update frequency and persistent scatter coverage.
So thank you for your presentation. I only have one question about, we don't usually pick persistent scatters in croplands. So based on your results, do you recommend taking only the season that has the summer, pick some PS and try to do time series with it? Because whenever we are processing an entire year, we don't get PS.
Yes, yeah, this is basically the thought behind it, to see which images could be excluded. So here the time spans were quite large, so hopefully it would be very narrow, maybe just a month or two instead of half a year. But yeah, that would be the idea, to exclude those images.
Did you try to do it?
Not yet.
Okay.
Not yet.
Thank you.
Thank you very much. Do you think you could use these methods to look at environmental changes after an event, such as a flood or a fire or an earthquake, or do you think that it's better to use things like coherence, which people usually use, from what I know?
So you mean if you would, instead of process an entire time series, you would divide it and then see, for example, a sudden drop in persistent scatter density? I mean, maybe, we haven't tried this yet, but it could be an avenue.
Thanks.
So if there are no further questions, thank you again.
Thanks.
So the next talk, the last in the session, but not least, will be done by Marcello De Michele, and he will talk about unwrapping the face of the single-focused SAR image application to sea level anomaly.
Thank you, Mr. Chairman, Mr. Chairwoman, for giving me the opportunity to talk about this topic today, and for the nice pronunciation of my name. I am working at the French Geological Survey, BRGM, and since more or less 10 years, I've been working on this topic with my co-authors presented here. And I was at a point where I needed actually to show the results to the INSAR community. So I'm basically here to ask more questions than answer, than give answer, actually. As you know, the phase of a single SLC, single look complex, so apparently if I press next, I go there, is classically assumed to be stochastic noise when we attend the course of radar interferometry or SAR, synthetic aperture radar. The phase of a SLC is classically assumed to be stochastic noise. And so I could be giving this kind of a topic where I say that we are the best in the world because we come out with a measuring finally the lengthening or shortening of the optical path from a single Sentinel-1 acquisition. And the method might enable to use SAR archive for sea level measurements since 1999, where observations are lacking. But I think I'm going to give the other talk, which is this one, actually within a single focused SLC. There are a number of physical information that are not fully exploited yet. My question is, can we assess them? How we can assess them? How we can be sure that there is a geophysical signal behind this information? When actually we learn at school that the phase of a single SLC is stochastic noise. And as I said, we are at a point of our research where we feel that we have to open our results to the community and discuss with you, I hope. So what I'm talking about, because not everybody here is from really maybe the INSAR or exploiting the phase of the SAR phase, of the SAR image. As you know, the SAR signal is acquired with an amplitude and a phase. Actually, it's the real part and the imaginary part, and you can recompute into the amplitude and the phase of the signal. We focus on the Indian Ocean, on La Réunion Island, because within the French Geological Survey, we deal with a natural risk, and this island has a volcano, has landslide, has also a cyclonic threat to the coast, so coastal risk. So actually, as an research institute, we focus a lot on this region. So we have already a number of Sentinel-1 dataset. Here I'm using the strip map mode. It's one of the modes of Sentinel-1 that it's particularly acquired over islands. So here you have the amplitude of the image. And this is actually the phase of this SAR image. It's not a random model that I use here. It is the phase. So as you see, it is unexploitable if you look at it like that. But we know already, and the oceanography community knows it very well, that if we do a Fourier transform in the azimuth direction, we can assess a residual phase that was not compensated during the focusing that is actually proportional to ocean currents. And it's the Doppler frequency, a residual Doppler frequency, so from this phase. What I would like to say is that before measuring a Doppler frequency, if we analyze the Doppler history, the residual Doppler history in the azimuth, we can access an angle, which is actually the squint angle during the radar acquisition, the residual of the squint angle. What is not used by the community is the derivative in the range direction of this image. So you'll be surprised by the next slide. So from the phase that we saw before, if you apply the derivative in the azimuth direction, which is the direction of the orbit of the satellite, and we do the multi-look, then we multiply this by the pulse repetition frequency, we have what they call, in space oceanography, they call it radial velocity, RVL. But if we do the derivative in the range direction, basically we exploit the phase of the autocorrelation function, arg r tau. We access to an angle in the range direction, and we get this kind of results over the ocean. So that's my point was, what is this? What is this? It's in the ocean, looks like a DM of the ocean, and it's in radians. So the argument of the autocorrelation function in the radial direction measure an angle, a phase angle. So I can stop my presentation here and ask you, what is it? We know the radial velocity, it's also a product by the European Space Agency. You can access the ocean product of Sentinel-1. But this is unknown. I switched date, 12 days after, 22 December 2016. Again, we have the amplitude. Number 2, it's the radial velocity, which is proportional to the ocean currents. But not only, because as I said before, the derivative in the azimuth direction, multi-looked, is proportional actually to the squint angle, which means if the SAR was not focused, the SAR image was not focused to 0 Doppler, it stays a residual in the azimuth direction, which is proportional to object motion during the focusing. The ocean is moving during the focusing, but also to the slope of a surface along the path of the satellite. So here, in the what we call radial velocity, it's actually the ocean currents plus a surface that can be assimilated to a squinted SAR, actually. It's like if the satellite was on another squinted orbit, but no, actually it's the surface of the ocean that is tilted. In the range direction, same thing, I thought, because we see some ondulation on the sea surface, but it is physically impossible to measure a current or a velocity, because in the range direction, the distance between 2 pixels, this is the phase, it's a phase derivative, so it's not an amplitude product, it is the phase. If we subtract the phase from 2 adjacent pixels, the time between 2 pixels is proportional to the speed of light, so it's impossible to measure a velocity by measuring the phase distance. So what is it? Again, I don't know. So I do another test. We go to 3 January 2017, so 12 days after, and I get these results. I said, maybe it's a problem during the focusing with the matching filter, so what I see, it's actually kind of back engineering the focusing processor, but actually this phenomenon is changing with time. So I compare with the radial velocity in figure 2 all the time, just to show you that we don't see the same thing. So the two phenomenon might be related, but not spatially, but not correlated directly. So I said, okay, I actually measure the optical path, the phase lengthening and shortening in the range direction, which is the optical path. So if I integrate the optical path, I basically unwrap the phase of a single SLC, the phase of a single SLC. So this is what I did. I first transformed the argument of the autocorrelation function, which is an angle, in a distance, dr2. We are in the range direction, and I obtain an extra optical path of the radar wave in the range direction from one single acquisition. Then here I make the exercise of integrating the signal in the range direction using a Fourier approach, but actually I could have used another approach by counting the pixel and making the sum, and I get this kind of results. So to me, visually, I'm not a physical oceanographer, but Rémi Asselot, which is co-author, really looks like a DEM of the surface of the ocean. So I said I could stop here and end the presentation. Very nice. But I said, okay, let's try to see if this is a real physical and geophysical signal. How can I benchmark this with another observation, independent observation, made in open ocean at the same time of the acquisition of Sentinel-1 strip map mode, given that we are in the line of sight direction, so this is not ocean topography, It's a hint maybe for ocean topography, but it's in the line of sight direction. We are in radar geometry, even though I flipped the image in a kind of geocoded fashion just to show you in a way you could recognize La Réunion Island. I compared with, I came up with this geometrical model. What do we do in the azimuth direction when we calculate the gamma angle? We do the derivative in the azimuth, we multi-look, and the gamma angle is what actually it is used to do the focusing, and it's the squint angle. So the squint angle, it was what I said before. It could be the satellite that is squinted, but it could be the surface also that is tilted if the satellite is not squinted. So this is a way also to measure in the azimuth direction the slope of the surface. And when we transform this into the radial velocity by multiplying the argument of the autocorrelation function in azimuth into the radial velocity, actually there is a bias in the radial velocity given by the surface, the slope of the ocean. I do rather that in range. So I try to transform this geometrical model into the range direction. So I said, what's the equivalent of the gamma angle in azimuth? It might be alpha, I call it alpha, very, I'm not very, say, original here, which is basically an offset from the incident, the nominal incident angle, not the look angle, the nominal incident angle. We can measure the slope of a surface within a certain amount of precision by doing the range derivative and multi-looking. If this is correct, we are in the interpretation phase. Before I show you a signal, if you do the same thing with the same data set, you will obtain exactly the same results. Here I'm trying to interpret. So I discovered that actually Sentinel-1 is focused. During the focusing procedure, ESA is using a DEM on land and the mean sea surface height on the ocean. So what I see actually is the offset between the path lengthening of the SAR signal and the reference surface that here is represented by the JETA 30 DM, which represent the mean sea surface height. So what I measure in my integram, I called, it's the sea level anomaly, which is the discrepancy between the instantaneous sea level and the mean sea surface, which is the geoid, basically. So I do profiling in different images, A to B, C to D. I haven't done it in the middle. I have done it, but I'm not presented here. And I transform actually my phase signal into a line of sight in meters. So I unwrap the phase of a single SLC and I make a measurement that is in meters line of sight. And I compare it with altimeter data. You have the sea level anomaly from Aviso service provided by CNES that is also implemented in the Copernicus Marine and Land Cover and Marine Monitoring Service. This is in orange is the altimeter sea level anomaly. In gray, you have my measurement that is especially very detailed. So you see the bumps in the ocean. And in blue, I actually down-sampled the integram, my measurement, up to the altimeter resolution, which is 25 kilometers, whereas I have 166 meters of resolution. So you can see that when I downsample the integram, I can actually see a pattern that is pretty convincing and similar to the one measured by the altimeter, even though we don't see the same thing. So it's a difficult comparison. Of course, the data are difficult to co-register. I'm almost done. So I did that in 16th of November, 28th of November, 8th of April, 20th of April, 26th May, 7th June, 18th of August, 11th of October, 4th of November, 15th January, we may. And this is basically the method. I did on purpose to leave this at the end so that you don't have time to take the pictures, because the paper is submitted but not accepted yet. Basically, the question is, what is the signal that we see in the ocean? I'm opening the question to the community here. And what we use, it's the pulse pair algorithm that has been already published for the range direction in a number of cases, from 68 up to yesterday. But I do it in the range direction. So this is the model that I propose. This is the integram, so I integrate the phase of a single SLC, which is a kind of unwrapping. I think there are many applications that are possible in the field of, for people that work in displacement of the Earth's surface, possibilities to link the extra optical path to the atmospheric delay from a single star image. And I have finished my presentation here. Thank you, and sorry if I'm a little bit late. I just would like to thank you, ESA and the Copernicus program for Sentinel-1 data, and Alessandro Ferretti and Pierre Bayol for the positive feedback they gave me to this presentation.
Thank you very much for a very interesting talk about completely novel thing. I believe there are many questions for that.
Thank you, Marcello. Very interesting. So the first question that comes is really linked to the uncertainty here. So of your technique linked to the sea surface height, because in ESA we have Sentinel-3, Sentinel-6, and we have requirements on this product, sea surface height. So here you're introducing this technique, but did you also look into the uncertainties, so the sources of errors that in your estimate?
That's a very interesting question. Thanks a lot. Do you mean intrinsic error in the...
Yes, yeah.
It's true, I haven't put any error bar in my... because the error bar is within actually the dot, the orange dot. There are many ways of measuring the error, but the best for me is to compare to another methodology and have an idea of the difference between the two. So when I do this, these profiles give you an idea. Actually, the distance between the altimeter, the red dot and the blue dot, it's the error in the cross comparison between two methodologies that come from two different sensors that cannot be co-located. One is an IDR altimeter, the other one is a side-looking angle. So it's just a try to understand the signal. Else, the measurement that I do, it's the one in gray. It's spatially very correlated, that you see it here. That it is noisy. I can calculate the standard deviation, classical standard deviation. I have done it. I don't show it here, but I don't know if I'm answering to this question. And maybe you can help me in how I can compare these results to another methodology that can give me the same kind of results, and so I get an idea of the error.
Yeah, let's talk.
Else is the precision of the methodology.
Okay, thank you very much. I think it's a time for coffee break because we are already running out of time. There's another question?
There are two more questions.
Okay, let's consume some time from coffee break.
Thank you so much. Thank you, Marcello. Very nice presentation. My question is very quick. I see that you tried this over a specific area, but have you also tried this methodology on other areas?
Yeah. In 10 years, I tried in a number of other areas, sure. And we tried also on the interferometric wide swath mode of Sentinel. And the results are very encouraging.
So they're comparable to what you're showing in this presentation?
It is really comparable. Okay. Then what we are doing now is try to understand what we see and how we can benchmark it with other methodology, other measurements, because in open ocean, it's pretty difficult. But yeah, we tried elsewhere, sure.
Okay, thanks.
You're welcome.
So thank you very much. And,
thank you.
Let's continue that discussion for the coffee break, because I also have a couple of questions. And so that's the end of the session. Please enjoy your coffee break, and do not forget to come to the second part of this session. And also later on there will be a roundtable discussion. Thank you very much.
Hello, good afternoon, everyone. Welcome to this session, the thematic mapping 2. So we can start the session. Maybe we can just jump to the first presentation. Here, I can invite Federico to present his papers, which is cross-continental Bayesian INSAR forest height estimation. Yeah.
Yes. Thank you. Thank you, first of all, and welcome, everybody. Now we are changing the topic of the thematic mapping, going for the forest, our huge green carpet on Earth. Well, actually, forests are not like a huge carpet, but because they are not flat, they have three-dimensional structure. And today we are interested in the height, the vertical dimension, because it gives us a first window into the biomass, the carbon storage, and if tracked over the time, it can also give us insights on the ecosystem dynamic. Well, so today's goal is to understand how we can monitor forest height in an accurate and reliable way. Well, of course, the most easiest solution would be just go there, wherever there is, and measure the height. And this is what actually is done with airborne LiDAR sensors, such as the NASA land vegetation and ice sensor, and also with the in-situ measurements today, which are today, let's say, our golden standard. But actually, if we take a closer look on how this sensor works, such as the Elvis, again, which flies attached on a plane and basically scan roughly a 20-meter footprint, circular footprint on the ground, sending pulses and registering the profile of the energy coming back, as shown here in the slides, from which we can identify, let's say, the huge peak of energy as the ground and setting up our own definition of height, such as the 99th percentile of the return energy. And from the two value, we can define the tree height. Then we can understand that with a 20-meter footprint, this would be impossible to scale on a global scale. That's why, since forests are changing over time, we need a global and a cost-effective solution to enable the forest monitoring. That's why in our story we have to move from, let's say, the sky to the space with our Tandem X twins being the next characters for us. I won't spend too much words on them because they are flying since 20 years almost. But they enable global coverage. It's a German mission with enable global coverage, shorter visit intervals, and thanks to the SAR technology, also weather independent and, let's say, acquisitions and high resolution ones. But of course, there is a catch. Since the microwave tree interaction is pretty complex, and this complex interaction is often failed to be modeled by physics-based models, which, let's say, need to rely on simplifying assumption. And to overcome, let's say, this issue, we want to address the problem thanks to deep neural networks, because deep neural networks enable to understand or should understand this tricky link directly from real-world examples. And yeah, the features, or let's say the information we are providing to the networks, of course, has to include the signal itself in its amplitude and phase information. From, let's say, right to left, we have the backscatter as recorded by the master satellites. Then we have the sine and the cosine of the interferometric phase. And this is really important to give the sine and the cosine to the network because it gives the network the opportunity to understand where the phase is growing and decreasing, kind of unwrapping the phase. Then since we have, let's say, the twin satellites, they are acquiring together in a bistatic mode, then we can compute the total coherence, which is kind of not affected by temporal decorrelation. And the coherence, for the ones who don't know it, it's just a cross correlation between two images. And we can isolate the volumetric decorrelation happening because of volumetric target on ground, such as the trees. And finally, we provide the network the local incidence angle, which is an information how the echo bounces back to the satellite because of the topography on ground, and the height of ambiguity, which brings into the problem the acquisition geometry itself as the satellite separation, because it's inversely proportional to it. And all the features are provided at 25-meter resolution to the network. Well, and here we go with the Bayesian setup. It's a Bayesian deep learning framework, meaning that we try to model the network itself with, let's say, not with fixed weight, but with distribution. And to do so, let's say the most easiest way to do so is just relying on multiple trainings and consider each of those as a Dirac delta in the distribution of the weights. But that's like a different story, and it's too long to explain like in detail. So we are relying on 5 networks, independently trained networks, everyone guessing on the same input data on the same method and giving its own opinion, let's say, on the problem. And each of those is actually a fully convolutional neural network, pretty easy, which keeps, let's say, the resolution because it's not going down and up as, let's say, encoder and decoder do. And as each network has 2 heads, each one is predicting height, the height value, and its own uncertainty, pixel-wise. To understand this, let's take the 2 of them, and let's say we should not see them as 2 different tasks for the network, because the network is predicting its own uncertainty at each pixel. But we should see them together. And together they define, are the 2 defining parameter of a Gaussian distribution, which is our target for, let's say, our prediction in the network. So pixel-wise, we have we have the height estimate as a Gaussian distribution for which we have the mean, which is the most likely height value, and the variance, which is the uncertainty of the network, or it's proportional to it. Here we have the full product as comes out of the network. This is an image acquired in Gabon in 2011, on which we applied, let's say, the framework. And this comes with its own, let's say, uncertainty. So the map here plotted the standard deviation to keep, let's say, the scale. And of course, we can validate the network as everyone does, let's say, in dividing, let's say, keeping some area outside of the training and the validation framework and testing on them. And we can actually come up with state-of-the-art results with the root mean square error of 5.64 meter and, let's say, almost a negligible bias. And I mean, you see that the trend is pretty there. I'm going to comment on the 2 last metrics, the root mean variance over root mean square error. This is needed because we are in a Bayesian setup and we want to trust the uncertainty estimate. And what we want to is that the network is on average and on an overall scale predicting the same, let's say, its uncertainty overall, it's proportional to the error it's doing. And the closer to 1, the better it is. Here it's way closer to 1. And then we have the ECE, which is the expected calibration error, which is trying to compute the metrics on, let's say, uncertainty range, because we want not only to be like robust or, let's say, accurate overall in our prediction of the uncertainty, but also like on different, let's say, on a smaller scale. And the closer to 0, the better it is. So, well, we have a framework that works on a, let's say, on a country setup. We want to have we want to go to global scale because in the end, what we want to do is a monitoring over, let's say, the entire globe. The most obvious solution and the things that actually we can find in literature and, let's say, nowadays also good, let's say, big companies, big tech companies are doing it, is just enlarge the training data set and the testing one as well. This works well. Results are pretty fine, but the problem is that the larger the training data set, the more the rare case fade into it. And of course, they are fading both in the training and the testing. So we won't, I mean, the network won't be robust to those cases, but we have some difficulties in assessing like when it's failing actually, because they're also rare in the test data set. What we are proposing here is like to try to do things step by step. Firstly, understand if what we are doing and the features we are using are suitable for generalizing somewhere else. And this is called domain generalization, in which, let's say, the goal is to have like a set of transferable features on unseen regions, which are not, again, closer to the testing region, because this is an easy task. One example is here. Before, I told you that we are bringing the phase into the problem, or the interferometric phase, then to the sine and cosine of it. This is actually something new, because before we were bringing into the problem thanks to the digital elevation model as acquired, or coming out, let's say, from the acquisition itself. And the two of them brings, let's say, to the network the same kind of information, because in the end, the digital elevation model comes out of the interferometric phase, but it spans a range of value that is way larger, and this leads the network to be out of distribution even within, let's say, Gabon itself. Indeed, with the sine and the cosine of the phase, we just range from -1 to 1. We are able actually to, and let's say in a more random, let's say, way. Random, it's not the correct word, but I think you get the point. We can have like a more robust set of features to bring inside the problem, let's say, the recorded signal in its phase component. So let's see what happens when we fix the testing data set, because of course we want, let's say, a fair evaluation performance, and we scale on a different continent. Here we are performing the training in French Guiana, South America, and testing, let's say, in Gabon, where we were before, Africa. And results are pretty nice, with the network training French Guiana on the right side for you, which is, let's say, of course, with the performance degradation, which it's not like, it's something which is there roughly of 20–30%, but still regression works pretty well. And we can spot it from the scatter plot now, which plots, let's say, the cross, where the point, each prediction stands from the true value with respect to the predicted one. And we can actually do the opposite task just to be sure of what we're doing, and things again worked pretty fine. One thing to note here, this is the test done in French Guiana, so let's say closer to the Amazonas setup, that the performance here is pretty worse, with the root mean square error of 6.88 meters, roughly 2.5 meters worse than before. And this can be understood by the fact that in French Guiana, and actually over all Amazonas, the canopy is way closer. It's way more dense, let's say. And this prevents or limits the penetration of the X-band data there, with respect to the Gabon setup. And one thing I want to show also, it's like, if you take like the French Guiana setup and you look like on the top left corner of the uncertainty, you can spot actually one river as a height or spike in the uncertainty. And this is something you cannot see from the prediction. This is like something which is really interesting to me. Okay. Another things I want to show is that if we split and we take a close look to, let's say, different categories of trees here, let's say the global, let's say the inland cover and the mangrove, what we can see is that in French Guiana, the mangroves are way less in absolute number, typically on the, let's say, ocean coast, and also like shorter in height. And this drives a huge negative bias when we apply the model trained in French Guiana to Gabon. This is, let's say, the main motivation to let's say, test another scenario in which we try to combine both, let's say, the high mangroves from Gabon and the French Guiana closer canopy to provide, let's say, the network with two different, let's say, and complementary information. And this time we won't test, let's say, again in Gabon and French Guiana, because we will end up, let's say, again in an in-country scenario or two-country scenario, but we're going in Amazon to test the network. One thing we have to solve before is that Elvis did not fly there in Amazon, and we have to rely on local campaigns, which are typically providing point cloud data, which are way different from the ones like of Elvis, because they are just point there. And to have, let's say, this is something, I mean, a challenge in the end we have to deal with, when we scale to larger scale, because in the end, we cannot expect that one sensor flew wherever in the world. But even if the sensor changed, the target should not for the network, because otherwise we won't be able to access the real performance. And the idea here is to take each point of the point cloud and spread its energy on, let's say, the vertical axis, so the height axis, with a Gaussian shape, which is linked to the pulse, the pulse that Elvis sends on ground, and then doing the cumulative sum from 0 to here, 75 meters. And then again, we can come up with the definition of the height we had in the Elvis setup. And again, here is the result of the model jointly trained in Gabon and French Guiana and tested in Amazon, which again has only a 5.6 meter of RMSE and, let's say, an uncertainty which is well calibrated. Root mean variance over root mean square error is just 1.03. And of course, taking advantage of let's say, this larger setup for training, also the performance in Gabon and French Guiana are better. But this is just because, I mean, we are exploiting complementary information and adding more training samples to the dataset. So what we did in this experiment, in this, let's say, study, was in a sense to, let's say, set a lower bound for our generalization performance. Of course, if we scale globally, we can always take advantage of more and more data, but always keeping one testing data set apart, which is huge and, let's say, geographically separated, in a sense defines a lower bound which we can expect on performance. And let's say, of course, there are many more data out there, and we're working on the tandem X-band topical canopy height map, which will take advantage of data not only in Amazon, but also on the east side of the world, in Malaysia, in Indonesia, and many more. So this is the end of the presentation, and thank you for being here, and I hope you have questions for me.
Thank you, Federico, for your presentation. I think we have time for one or maybe two short questions. Yes. Yes, please.
Great presentation. A quick question. Did you test your solution where there's no canopy to see what your model would actually predict then? Because I'm a little bit confused how your model's actually evaluating or learning that is the canopy height. So that kind of test would be interesting for me.
Well, yes, it's not shown here. During my master thesis, I worked in Norway. And there we can take advantage of more like cropland and, let's say, fields, open fields and bare area. The point is that every deep learning approach here, it's trying, in the end, it's gonna converge, let's say, to the mean of the average of the data set. So you can have an overestimation, a slightly overestimation on the shorter canopies or no canopies, and you have like a underestimation of taller canopies, and you have a kind of like a trend which set up the mean bias in zero, or let's say where you have more training data set. But yeah, in this case, we will mask out, let's say, let's say we want to be firstly give out a let's say a forest product. So we are mainly focused on trees so far. But of course, let's say the challenge can be solved just training a model on let's say low vegetation, right? And also you have a problem because in the end, if you have like croplands, they grow and they are like cutted. Think about like crops area, and you have like 2 meters things, and then they are cut. So you have really to be close in time with your reference data. It's not always possible. But yeah, and also like when you move to Amazonas, then you have deforestation there, which again, it's another problem. But in the end, if you mask out those areas, those are the performance. The performance include also like I did not mask out like I just mask out deforestation. To be fair, croplands and things are there, but just they are not there. because there are no there.
Okay, thank you. Any other very quick question?
Hello. Am I right? Your study uses a deep ensemble of 5 independently trained networks to approximate the epistemic uncertainty, right?
True.
Yeah. So what are the operational trade-offs of this approach when scaling up to a global data sets?
Can you repeat, please? The last part.
Yeah. With your trained network, what are the operational trade-off when this approach scaled up to global data sets?
Okay. Well, in the end, you have just each network is trained on the same data. It just that you have, let's say, a first random initialization in the network. You have like the way the network is getting the data during its learning, it's just random. So the network just converges to different weights. So there is, I mean, for sure the network to manage a larger amount of data should have more parameter, probably. This is something we did not investigate it yet. But I mean, the procedure to scale globally from a methodological perspective won't change.
Okay. And you explicitly also model both the aleatoric and, sorry.
Okay, go on.
Just one last question. And epistemic uncertainty to support your the large-scale forest monitoring, right? So why is it critical to separate those two two components in SAR-based retrieval?
Yeah, the uncertainty estimate, the aleatoric uncertainty is way larger than the epistemic one. And I don't believe that the two can be separated as in literature it's done, like straightforward. You have to have a more reasoning behind. But yeah.
Thank you very much. Thank you for this presentation and your answers to the question. We're moving to the next paper, which has to do with the mangrove canopy height retrieval from multi-baseline tandem X in observations. It will be presented by Yeyun Lee.
So hello, good afternoon. I'm Jae Lee from Busan National University, South Korea. Today I present about mangrove canopy height retrieval, especially by applying the RVOG model with the multi-baseline approaches. So let's first talk about why mangrove is important. Mangroves are representative blue carbon ecosystem found along tropical and subtropical coastline, and they are one of the most blue carbon dense systems on Earth. As shown in this figure, they protect the coastline from erosion, provide habitat for diverse species, and store large amount of carbon. Although the mangrove carbon is stored below the ground, above-ground biomass derived from canopy height is the best available proxy for carbon stock assessment. So this is why mangrove is important and why we need to conduct the mangrove canopy study. Now, as you can see here, various approaches have been used to monitoring mangrove canopy height. Field survey and UAV LiDAR provide accurate canopy height estimation. However, this method is difficult to apply continuously over large area. To overcome this limitation, synthetic aperture radar has been widely used as it provides high spatial resolution with large coverage. Looking at the previous study from left to right, the three-stage RVOG model was proposed to separate volume and ground scattering using polarimetric IMSA data, and this concept formed the foundation of our study. And following the two studies demonstrate canopy height retrieval using single polarimetric tandem X without an external DEM. While the canopy height retrieval is estimated successfully in these two studies, the sensitivity of single baseline observation may depend on canopy height and acquisition geometry. And the last one proposed a multi-baseline inversion approach. This approach used canopy height information derived from an external DEM and to select suitable baseline for height retrieval. Building on this contribution, this study aimed to estimate mangrove canopy height in the Southern Everglades using tandem X INSA data with 3 objectives. First, we estimate canopy height without any external DEM. Second, we apply RV-OJ mode inversion using volume decreation of the single polarimetric tandem X data. And third, we performed multi-baseline analysis to reduce vertical ambiguity and improve estimation accuracy. And this slide explains how I estimate canopy height. As shown in the left figure, the laser signal penetrates into the vegetation layer, so the observed page represents the scattering page centered inside the canopy, not the true top of the canopy height. The vertical distribution of this scatter causes volume decorrelation, which we modeled using the random volume over ground framework. As shown in the middle figure, RV-OJ model assumes 2 layers, a volume layer with randomly distributed scattering and a ground layer. The right figure shows how the vertical distribution scatter is mostly concentrated near the top of the canopy. By modeling this distribution, we can invert the observed coherence to retrieve canopy height. This study focused on the mangrove forest of the Everglades in Florida, USA, one of the most important mangrove forests in the world. In 2017, Hurricane Irma caused substantial damage to mangrove canopy, and just this year, a large wildfire occurred in the Big Cypress area in February, further highlighting the need for continuously monitoring. And the yellow box in the left image indicates our study area. We use tandem X persist monostatic stream map data acquired from December 2014 to February 2015. Within each pair, the 2 satellites observed the same area, only about 10 seconds apart, so temporal decorrelation is considered negligible, and it makes this mode highly suitable for analyzing volume decorrelation by the vegetation layer. As shown in the table, the 3 pairs have perpendicular baseline approximately 174, 257, and 344 meters, providing height of ambiguity 29, 21, and 40 meters respectively. HOA represents the height difference corresponding to a 2-pi page cycle and the vertical wave number capacity, which represent height sensitivity range from approximately 0.2 to 0.4 radian per meter. So now let me explain the method. The observed interferometric coherence consists of multiple components, including volume, range spectral, SNL, and temporal decorrelation. Since tandem X data are acquired only about 10 seconds apart, as I mentioned before, temporal decorrelation is assumed almost 0. So we applied common band filtering to reduce spectral decorrelation and modeled SNR decorrelation using the noise information from the metadata. And then to isolate the volume-only coherence, we need to estimate and remove the ground page. External DEM can remove topographic page, but in case of our study area, but the tidal chains make them inaccurate for mangrove ground level. Also, since our data are single baseline polarization, so we cannot separate the volume coherence and ground coherence using polarimetric information. So instead, following the previous study, we used coherence double bound scatter at the wattle and mangrove boundary to estimate the ground page without the external DEM. Mangrove grow directly in water, so we treat the water surface as the ground level. At the water and non-water boundary, double bound scattering occurred between the water surface and the mangrove trunk, and the interferometric page of these pixels represented the underlying topographic page. By removing this ground page from the entire image, we can isolate the volume-only coherence component. Once the volume-only coherence is extracted, we apply the volume coherence. We apply the RVOG model following the previous study to retrieve canopy height. As shown in the equation, capacity and local incidence angle are known value from the observation geometry. The extinction coefficient sigma, ranging from 0 to 2 decibel per meter, describe how radar signals are attenuated within the canopy and is treated the candidate range. The extinction coefficient sigma show the vertical for each candidate sigma values, modeling the vertical distribution F. The F is modeled as shown in the right figure from the uniform distribution at low sigma and strongly top-weighted at high sigma. Then for each pixel, we find the canopy height HV that best matches the observed volume-only coherence. This makes canopy height retrieval possible even with the single polarimetric data. Now let me introduce the proposed multi-baseline RVOG inversion. As shown in this diagram, the process consists of two main ideas. Let's say we have 3 acquisitions with different baselines. In the first step, each acquisition independently searches over all height and sigma pair to find the best fit F model with minimum residual. Since each acquisition has different HOA and capacity, they each have different height sensitivity. For example, some performed better at lower height, while others are more reliable at higher height canopy. In the second step, for each pixel, we compare the model residual from our acquisition and select the one with the smallest residual. For example, here acquisition 2 shows the smallest residual of 0.04, so the final estimated height of 7 meters is assigned to that pixel. This per pixel selection is the key idea of our proposed method. By always choosing the best fitting result for each pixel, we can cover a wider height range most reliably without being limited by the sensitivity of any single baseline. The map of the right shows which acquisition was selected for each pixel in the final canopy height map. Now here is the result. The top left image is the retrieved reference global mangrove canopy height map derived from the tandem X, and others are single baseline RVOG inversion result for each acquisition. Overall, all 3 results show similar height distribution consist with the reference ranging from 0 to 20 meters. However, pixels with volume declination below 0.4 were masked out, resulting in the data gap across in the image. Then this scatter plot showed the quantitatively comparison between our estimate result using single baseline and the reference. Also, results show high correlation with R-scale value ranging from 0.83 to 0.87. However, looking more carefully at the scatter distribution, we can see that the estimation characteristics differ depending on the HOA condition. While the mid-range HOA show, the blue one show relatively stable performance across the full height range, the larger HOA, the black scatter tends toward overestimate, and the small HOA, the red scattered, show points concentrated in the lower height range. This research confirmed that canopy height retrieval performance is highly dependent on the observation geometry. Let's take a closer look at the limitation of single baseline inversion. The left figure shows RMSE for each height bin, and the right figure shows the number of high coherence pixels per height bin. Note that the gray area of the right graph represents the validation data distribution. And as you can see, the gray area, higher canopy heights are naturally less common in this area. And again, as you can see the left image, each baseline shows different performance pattern depending on the height range. The larger HOA show consistently higher RMSE across the most height range. The mid-range HOA provide the most stable estimation overall, and the smaller HOA performed well at the lower height but lost valid pixels rapidly at a higher range bin. This is clearly visible in the right figure. The number of height coherence pixels for the smaller HOA drops rapidly above 6 to 8 meters. This demonstrates that each baseline has a limited effective height range, and this motivates us to apply the proposed multi-baseline. Now let me show the result of proposed multi-baseline approach. The canopy height map on the left has fewer masked pixels compared to any single baseline result, and the scatter plot shows also a scale of 0.9, a clear improvement over a single baseline result. The scatter distribution is also more evenly spread across the full height bin, indicating that the proposed approach reduced both overestimation and saturation. Looking at the RMS by the height bin on the right, the multi-baseline results show consistently low and stable RMSE across all height bin. And this demonstrated that by selecting the best fitting result per pixel, the proposed multi-baseline approach enables reliable canopy height estimation across a wider height range. To summarize, this study estimated mangrove canopy height in Everglades by applying multi-baseline of RVOG inversion without an external DEM. Single baseline results show that estimation performance very depends on HOA, with each baseline showing limited sensitivity within a specific height range. By applying multi-baseline inversion, vertical ambiguity and observation-dependent bias were reduced. This finding suggests that multi-baseline RVOG inversion can improve the accuracy of canopy height estimation across the wider height range, and this approach demonstrates the potential of INSA application for mangrove monitoring. And finally, as future work, we plan to extend this research using P-band biomass for polarimetric data. Longer wavelengths allow deeper penetration into the canopy, enabling more effective retrieval of ground scattering and multi-layer canopy structure. Combining biomass for polarimetric data with the proposed multi-baseline approach is expected to enable more accurate canopy height and biomass estimation. As a preliminary step, we applied the process analysis, the Pauli decomposition as the right left image to biomass data acquired over the Sundarbans mangrove forest in Bangladesh. Is also one of the most large mangrove forests in the world. And in this area, as shown on the right graph, various baselines are available ranging from about 800 to 5 kilometers with a temporal baseline of 3 to 21 days. And we expect utilizing a wider range of baseline configuration will further improve canopy height retrieval in future work. So that concludes my presentation. Thank you for your attention.
Okay, we have time for some questions. If there are some. I may have maybe one. Can you go back to your transparent number, don't know, 12 or something like this, where you explain one before, please. Yeah, here you are fitting a random volume of a ground model for each baseline.
Yeah.
And after you get 3 different estimates.
Yeah.
Which is what everybody expects. Okay. So how do you compute the final? You select the best one.
Yeah.
Okay. But the best according to which criterion?
With the minimum residual as the stable, sorry. And if I choosing the best pixel, there are 3 different estimation and 3 different model, and there have the
minimum residual.
Yeah, minimum residual.
Okay, because here you did all the work. I mean, you very cleverly compensated the ground phase by looking at the double bounds. Okay, yeah. This I really appreciate. But why don't you combine the correlation? I mean, the coherence you could combine and do tomography, no?
Yeah, yeah.
Why not? You did all the job until then?
Actually, this is the initial stage for this study.
I think
so
you
yeah,
could.
Maybe I will conduct
great
this.
potential, because if your phase compensation is accurate, you could try to do it. Any other questions? Thank you very much.
So I think we can move to the next presentation. Still is far side estimation, still on X-band, but this time with the tomography. Yes. The presentation given by Go Bing Zhang, which is international collaboration, I assume.
Okay. Thank you. Hi everyone, I'm Guo Bing from Nanyang Technology University, Singapore. Today my topic is high-resolution forest time mapping using Hong-2-1 multistatic X-band tomosar. So forest is a core structural variable for biomass, carbon, and ecosystem monitoring. So the gap is not accuracy alone, it's the accuracy plus the spatial completeness. So with LiDAR, specific LiDAR like Jedi and I said, so we can have a very direct measurements, but the samples are very sparse. So with optical sensors like Sentinel-2 or Landsat, we have what-to, but indirect measurements of the forest. So with tomosar, we can have continuous direct 3D structural measurements. Right now, the current tomosar realization are mostly realized by a repeat pass system. So which give us 2 major questions, 2 major problems: temporal decorrelation and the atmospheric phase delay. So that's where multistatic tomosar comes in. And so Hong-2-1 is a multistatic SAR system that can simultaneously collect multi-baseline images. So it has one transmitter in the center of the constellation and 4 receivers, so we can receive like 4 images at one time, which we can do Thomas R. And most importantly, it can solve the temporal decorrelation and atmospheric phase delay problems. So in this study, we select like 6 test sites, mostly boreal and temperate forest sites in like 4 countries in the world, like Sweden, Russia, China. They have like single date acquisition, and we have like repeated acquisition over Alaska and Minnesota in the United States. And we use ISAT2 for the site-specific offset calibration, and the airborne LiDAR are reserved for independent validation when available. And JEDI and the end product are used as external benchmarks. So here's our retrieval framework from the radar scattering center to the canopy top equivalent height. First, we start with one-to-one multi-static data stack, and first we calibrate the phase errors induced by like, baseline errors. And we use carbon spectrum to do entropy mask to distinguish between forest and non-forest areas. Then we use the music 2-layer inversions to identify air ground and peak to derive the tree height. And we do some terrain correction, and finally we use DISET to calibrate this offset between the canopy top and the scattering center. So which give us 2 different products with different meanings. First one is uncalibrated Thomas R scattering center height, which is an effective X-band canopy scattering center height product. Can be used for physical interpretation and temporal analysis. And second one is our calibrated canopy top equivalent height, which is a LiDAR-like height product after a site-specific offset calibration for the forest height mapping. So here I'll give you 2 examples on entropy masking to distinguish the non-forest areas. On the first one, you can see that in the forest areas, the entropy is relatively higher than the non-forest areas. So by setting a proper threshold, we can distinguish between the forest and non-forest areas. On the second row, we show like the tomogram along the transect A with 3 different beamformers. First one is Fourier beamformer, and second one Kaplan beamforming. And with music, we can see more clear 2-layer peaks, but at the expense of radiometric accuracy. So I also show you some representative tomograms over other test sites, which also reveals better resolution of the 2-layer music algorithm. This is Minnesota and Gunho, in Alaska, Vologota, in Crackland, Sweden. So we also study the behavior of the offset between the Thomas R canopy scattering height and the LiDAR canopy top height, where the delta H means the reference LiDAR canopy minus the Thomas R scattering center height. And we can see clearly that this offset increased linearly with the canopy height, and the fitted slope and intercepts are site dependent, which implies that we have to do site dependent offset calibration, and a global bias correction is not enough if we want to get final canopy top equivalent product. Here's the result of a forest height mapping result of the 6th test site we select. And it reveals wall-to-wall, but not just sparse samples like JEDI and ISAT2. We also select 1 AOIs to compare with JEDI ISAT2 and a state-of-the-art JEDI plus Sentinel-2 and AI method. We can see that compared to the JEDI and ISAT2 product, our product is much more spatial continuous. And compared to the state-of-the-art JEDI plus AI method, we have much better agreement with the ground truth. And the ground truth is a high-resolution airborne LiDAR product. So after calibration, we evaluate the performance of our forest height product, which achieves the RMSE like from 3.2 3.4 to 5.6 meters at a 10 meters grade across all the 6 test sites. So Thomas R is not always the best point-wise dataset, but is consistently among the top performers. So, and the main added value is the competitive accuracy with far greater spatial completeness. And we also study the temporal shifts in the X-band scattering centers in Alaska and Minnesota. In Alaska, we have like 2 different acquisitions, one in September and one in May. So these 2 reveals nearly the same scattering center height, so there's no change. But in Minnesota, we have like, there's a pronounced V-shaped shift in the 3 acquisitions we acquired. Like in January, like the center is like this, and then in March, the center drops like 3 meters to here, and then in April, the scattering center like rise like 6 meters to this level. So it's a V-shaped shift we detected. And this V-shaped shift is also captured by Kaplan beamformers. We use Kaplan beamformer with just different quantities. The shape is the same with music method. And we provide a slow state interpretation for this V-shape. So in January, there's like minus 20 degrees. The cold and frozen canopy resulting in a near transparent canopy volume scattering. And in March, the temperature is above like 0 degree, so resulting in a warming and ablation of canopy ice and snow. So the canopy scattering shifts like downwards, like the 3 meters, as we revealed previously. And in April, there's a like fresh snow event before our image acquisition. In April the 3rd, there's a like, you can see the slow accumulation data. There's a very obvious fresh snow event. So this like upshaped the scattering center like 6 meters. Here's our just the interpretation on the V-shape result. So implications for the forest structure mapping. What does the multistatic X-band tomosar add? First is the wall-to-wall high-resolution forest head mapping with competitive accuracy. And second, the radar-derived canopy scattering center is sensitive to short-term canopy snow scattering state changes. And what cautions are needed? The 2-layer model we constrain is just a retrieval constraint. It's not a realized, it's not a real full forest model of the scattering. So that's the one. And the second one is the site-specific LiDAR calibrations are required if we want to get the canopy top equivalent product. And third, we haven't tested our dataset and method in tropical forests, so we need furthermore testing on tropical forests. So the take-home message is Home-to-One multistatic X-band tomosar produce spatial continuous higher resolution forest height maps across the 6 test sites with competitive accuracy ranging from 3.4 to 5.6 meters. Before calibration, we should know that the tomosar height should be interpreted as only the X-band canopy center height, not directly canopy top. And the repeated acquisition show that this scattering center shift can be like several meters under snow-affected seasonal conditions. That's all. Thank you.
Thank you very much for the presentation. We have time for a few questions. Yeah.
Thank you for a very interesting presentation. With the same data set, you could also use interferometry to get a forest, a top of the forest or forest scatter center height, and maybe you could gain additional knowledge, or you can compare the different methods, at least in in areas where the forest is small, so you can compare it with the height outside, or in areas where you have gaps in the forest and see the ground height as well. Did you do any work in this direction?
You mean I use the multi-static data to generate the DSM? And
Yes, yes.
I haven't, but you know, there's a tandem max. Sorry, can I change this? There's a very sorry. There's a tandem X profile along this, so we can see this. But this is all X band, so maybe tandem X is the same with our multi-static DSM. So the white dashed line is the tandem X profile. Maybe if I do this DSM generation, that will be the same result.
Yes, I meant if you take the HOG2 data and you do both the tomography as well as interferometry with the multiple baselines, it's quite easy to do it and to get. It's not the actual forest height; it's again the height of this X-band scatter center, of course, where you get the.
Yeah, but this scattering center is the average of the ground and the volume. It's
yes,
like
exactly. So you need gaps in the forest or small forests that you have this reference. So that's an advantage, of course, for the tomographic technique. But still, to compare would be quite interesting, I think.
Okay, thank you. Thank you for such suggestion.
Any other question?
Maybe just one comment. It's interesting to see that still at X-band we are still confronted to this penetration bias inside the canopy, which is obvious at P-band biomass. But you still have this problem at X-band when performing tomography. I mean, you need to compensate the actual elevation inside the canopy. You need to compensate it to the true tree height.
Yeah, this offset is like linearly correlated with the true top height.
Probably an indication that the exponential model that we were using in the past doesn't represent, because it is supposed to start at the top of the tree, the peak, and then it may be a way to compensate the bias, but does not explain the physics.
Okay. Thank you.
Following on Lauren's questions, I would like to hear how you compensate this one. So you mainly shift the canopy phase center in the tomograph with respect to the LiDAR view time, right? But how this is done? Just a simple shift?
I use the linear fit to predict the offset. I use LiDAR to calibrate this. I fit this slope and intercept, and I use this to shift transfer the scattering center to the canopy top. Yes, that's mostly 8 meters.
2 meters. Maybe okay, something like 4 or 5 meters.
You can reach as high as 10 meters.
It may vary with the density of the forest. It depends on.
Yeah, it varies with the true height, the true top height.
Okay, thank you very much.
Okay, thank you.
So we're moving to the next paper, which will be presented by Hossein, I guess. And there will be about forest height retrieval under zero baseline INSAR.
Yes, I think this presentation can also be given by my co-author, Yao Guimont, who has done a great job with implementation, but at the end, I will be presented here. So I will be talking still on forest height estimation. I think this is a long-standing topic, so if we look at the literature, we have several techniques. Maybe the most standard technique is either Pol-INSAR or tomography you see in the previous presentation also. Both some result from tomography and also Pol-INSAR or RVOG model. And in the past, I think we were quite limited in terms of the data. And most of it is experimented with airborne data, but now you can see some experimentation with, of course, a spaceborne and satellite data set. So currently we have Sentinel NISAR is launched. We have biomass data set. A few missions are planning to launch. So maybe the key or important point is that what method should be used for each of these satellites, or even more important is that what is the synergic use of this all satellite and information. So if you have the biomass data set, so of course maybe the first things that comes to our mind is the tomography. You can of course implement or collect the stack data of the biomass and implement this the tomography to reconstruct the tomogram. And then if you like, you can also separate ground and canopy with decomposition techniques. With the biomass dataset, of course, we can also implement Pauling star, assuming that the temporal decorrelation is negligible. With this Pauling star, we have a known techniques, which is RVOG, or random volume over ground. And I will be focusing in this study, or we will be focusing in the study in this Pauling star techniques, or the two-layer forest scattering model. But we want to analyze how this can be, what is the strategy to implement this technique, with this Pauling star technique, with image like from the NISAR or Sentinel-like acquisitions, which of course gives us the small baseline. Let me shortly overview this two-layer model. So this is nothing more than this simple equation. You have which links the coherency, interferometric coherency, as a function of ground phase, ground volume ratio, and forest parameter, which H is the forest height. So in case of biomass, of course, you have full pole data set, large baseline, and then if you ignore the temporal decorrelation, so you can, with the fully polarimetric data, you have almost same number of the observation and unknown. So you can get the forest height or unknown parameters. But moving to the Sentinel, or even NISAR or Roselle situation, then what's happening? The baseline is small. And then you do not have the full polarimetric data set, and the acquisition is a repeat path. So you have definitely temporal decorrelation. Now, we want, in this situation, I think this baseline issue with the Sentinel or even NISAR is already non-topic, but I would like to show this image. So you see here a point is the center of the Sentinel image. In our previous work, we collected over 1,800 Sentinel image, single baseline with a constant temporal baseline of 12 days, but distributed across global forest region. And then if you look at the histogram on the right, you see the top is the baseline. So usually the Sentinel baseline, as you see here, I think is a non-topic, but doesn't exceed 150 meters. And this gives us very small KZ, or geometric decorrelation. So with if you consider this volume coherency with some things like forest height of about 20 meters, and if you assume the KZ value for a Sentinel would be something 0.05, and in this case the volume coherency you can achieve is like 0.96. So even with the shorter forest, this approach completely to 1. So it means that you do not have geometric decorrelation, and all observed by Sentinel is, of course, is temporal decorrelation. And given this situation, we can assume, of course, that the interferometric coherency with the Sentinel is nothing more than temporal decorrelation, and we can use this temporal decorrelation as is done with this paper. So we assume that the temporal decorrelation arises from the motion of the scatterers, the Gaussian motion of the scatterers, either on the ground or canopy layer. So at the end, you can have this noun equation, which is it's called random motion over ground, and very similar to the random volume over ground. This is a bit simplified version of the random motion over ground, because we assume that at the ground level there is no decorrelation or there is no motion at the ground layer. So you can see that the temporal decorrelation or temporal coherency that in the Sentinel or repeat path acquisition in general is linked to several parameters like ground volume ratio, then forest height, signal attenuation, still you have several unknowns, like 5 unknowns with 2 observations if you have a dual polarimetric. So it's quite ill-posed problem. And with this a bit long introduction, I want to say what is the possible pathway or direction to solve these unknown parameters, and what we did in our works here. So the first thing we did is mainly building on this paper, which what we do is here, we try to perform polarization optimization to find the 2 coherency, which is, of course, one of them is maximum contribution from the canopy. Then you can assume that there is no ground contribution there, which just to stick to this reference, I call it gamma max. And in this case, you can get rid of ground volume ratio, so you don't need to estimate. So this boils down your number of unknown to be estimated from 5 into 3. So you can simply stop working on this optimization. You can try to solve this optimization problem and get the forest height. But what we did here, we just introduced a bit of a 2-step implementation of this scenario. In the first step, considering that some of these unknown parameters are kind of slow varying parameter, means that from one pixel to another pixel, you don't expect that much of variation. So we can perform this optimization or solve this equation in kind of a patch base, and then move it to the pixel base and update the forest height. So this is the first strategy we try to solve it and implement it. And then the second approach is reduced order, or maybe even better title would be simplified RMOG. So you can consider this equation. This is the main equation of the RMOG given, proposed by Marco Lavalle. So then if you start to simplify the exponential term with the Taylor series, then you end up with this beautiful polynomial and very simple equations where here you boil the number of non-parameters into 2 parameters, alpha and beta, which is the kind of combination of the all parameters into these 2 alpha and beta parameters. And yeah, this is our second strategy. So similar to the previous one, again in 2 stage, we try to solve an alpha and beta this time, and of course H, and minimize this optimization problem. So let me move to some results. Our study area is in South Finland. It's a boreal forest, so we have a high-resolution LiDAR data set, like 1 meter by 1 meter. Just to match with our SAR data, we resample it to 10 meters by 10 meter resolution. So this is the LiDAR-derived canopy height. And then this is the sentinel image, amplitude of the sentinel image. We have collected 6 interferometric pairs, or LiDAR dataset obtained in the end of September 2025, and this is the dataset that we considered. So we have a 6 interferometric baseline. The temporal baseline is set here to 12 days, but you see here all the pairs. So we use the multiple pairs to just stabilize the estimation problem. And then we have also collected the NISAR dataset, approximately same period, but just 2 days difference from the Sentinel one. So this is the amplitude image of the NISAR. The average amplitude image, just if you compare with the Sentinel, you can already appreciate the L band. I don't know how, is it visible or not, but quite clear that how tall and short forests are distinguished, even just looking to the amplitude image. Then this is the sentinel coherency, again average across the different pairs. And moving to the NISAR, this is the coherency derived from the NISAR dataset. So let me move to the results. So on the left you see the LiDAR CHM, and on the right you see the sentinel derived canopy height model from the first strategy, which is polarization optimization. you see, this is the result from the Sentinel. It's not, of course, meaningless, but of course, there are plenty of issues with it, but still is promising. So if we move to the NISAR, again, exactly same method, this would be the result, which is, I mean, just qualitative comparison. It's quite visible that how much the result improve. I think, let me also show this density plot. The density plot from the Sentinel one, and then also the NISAR one. I think we can expect that L-band could give much better result than the C-band or Sentinel one, but it's also interesting to observe this from a spaceborne data set. So this was the result of the first strategy, polarization optimization. Let me move to the second experimentation, which is simplified RMOG model. Again, this is the result from the Sentinel on VH polarization. And moving to the NISAR, and this is the result from NISAR, but this time in HV polarization. I just forgot to mention that the polarization of the Sentinel, we have dual pole, which is VV and VH, but in NISAR is HH and HV polarization. And moving to the copole result. This is the result from the VV Sentinel and HH NISAR dataset. And maybe better to see this one, the result from co and cross-pole with the NISAR and the Sentinel datasets. Yeah, again, we can expect that the cross-pole, again, producing better result than the copole. Yeah. With this, I can conclude the presentation. So definitely low frequency data set L-band provide more favorable scenario. I think we could have expected, we already know this topic, there was plenty of the studies with the airborne data sets, some limited studies with even L-band data set like from ALOS Pulsar or even SAUCAM. I think still is nice to see this from the NISAR data set, how it's complementing the C-band result. And then this reduced order, I personally would like it, which is easy to tune its parameters and get the far side. And also it's work with different polarizations. You don't need to really do any optimizations. You always have the same number of the unknown to optimize it. And the key point maybe is remain how to use a dual frequency data set. Of course, each of them has added value. You have the C-band, you have the L-band data set. Each of them has a different measurement. So what would be the even better strategy to use both of them, a joint use of the Sentinel and NISAR data sets or C and L-band data set for far side estimation. Yeah, I think I'm done. Thank you very much.
We have time for plenty of questions. There are some. Yes, Marco?
Yeah, thank you, Hussein. So I was wondering, I was intrigued by your linearization maybe or polynomial approximation of the model. I was wondering if you quantified the residuals. So how well is that approximation? Is that holding for a broad range of values of the parameters, or is it?
Yeah, good question indeed. Definitely, that's I think most important and the tricky part of the implementation. So let me show this slide first. Of course, we do the kind of we search for these non-parameters on the plausible range. For example, for the motion of the scatter between 0 to 1 centimeters in case of the Sentinel. But I should say that this is not fixed across all image. We do kind of adaptive grid search. So we change it from pixel to pixel even. So for example, for the motion of the scatter or delta V here. So what is this plot? In our previous work, again, we collected a huge number of the Sentinel dataset. We fixed the farthest height from the JEDI dataset. And then we solved the delta V from the Sentinel coherency. So you see this kind of pattern here, exponential pattern. So we use this plot just to find the upper boundary of the motion of the scatterer. We have the similar things for the far side. We do not always search for the far side within the range of, let's say, 0 to 30 meters, 0 to 40 meters. But what we did, we defined a quite empirical features, I can call it, based on the coherency and intensity, which gives us a very good upper boundary of the height that we need to search from the combination of the coherency and intensity. And then in some pixel, we search for far side of like a 0.5. In other case, I don't know, like 30 meters. I hope I can answer it, yeah.
Any other question or comment? I may have one. I was expecting something surprising, and I got it. It is surprising what you're presenting. I was a bit puzzled by the fact that at the beginning you explained us that the volume decorrelation is negligible, more or less. And then that all the decorrelation patterns comes from the temporal decorrelation. But after the model you fit accounts for volume decorrelation, and we don't speak anymore about temporal decorrelation. So does it mean that you are looking at a kind of contrast of height, of your height map is a kind of contrast? I mean, once you believe in a given level of temporal decorrelation and you use the Armog model, then you get rid of this part, and what you get is gives you this part decorrelates more than this one, so it should be larger or taller or smaller. Because I didn't guess it at the beginning. You showed the gamma vol is about 0.96. So
yeah,
impossible to estimate correctly. And after you use this gamma v in your equation.
I didn't use the gamma v. I think we assume that we don't have gamma v. Yeah.
For instance, okay. Yeah. So here you show that it is.
This is the RVG. So if we move to this one, that you can call it, maybe Marcus better. It's the temporal decorrelation at the vegetation level, which arises from the motion of the scatterer.
Yes, but you still have this gamma v, and the ground to volume ratio. So you still have a decorrelation which comes from the volume, if I'm not wrong.
What I see is if you look at the parameters Q here, what I see is mainly arise from the delta V.
So in fact, for a scene, you need to set one. You need to set one T or your one decorrelation pattern. So you're looking at the contrast.
I'm not clear on.
If there's some wind, this volume decorrelation, I don't know if you. Normally, in the model, when we don't account for temporal decorrelation, the volume decorrelation is given by the extinction pattern or what you like. And in this case?
In this case, I think what I see again, it's motions. I mean, from the mathematical point of view, what I'm looking for is the kappa, that is, and also the delta V, which is the motion of the scatters. I mean, but if you look on the whole of this equation, from at least mathematical point of view, is that we have the temporal decorrelation at the vegetation level, but maybe Marco can correct me, not the volume decorrelation or geometric decorrelation, which this temporal decorrelation is rise from the motion at the vegetation levels.
So if it is windy or not, you will have different values.
Definitely. I mean. So that's one is like using the multiple pairs.
Yeah, okay.
To stabilize the prediction.
So you need to kind of calibrate it or look at contrast, and then you get a...
Yeah, something like that. So I think maybe the better is what we did is like using the more pairs you have it, but of course you cannot use 1 year's data set. Yeah.
Thank you. Any other question or comments? Okay, thank you very much.
Thank you. Yeah, then we can move to the last presentation, which given by Simon Singh Hee Tong from NTU Singapore.
Thank you for the introduction. Good afternoon, everyone. I'm Simon from the Earth Observatory of Singapore, NTU. Today I'll be presenting on the topic of analyzing seasonal forest phenology and long-term growth using incoherent cross-correlation of time series star stats. This is a work done in collaboration with DRR, so I will thank my co-author and supervisor Giorgio and Sang-ho for supporting this work. And so thank you all of you to be here for the last presentation of the day. So in the context of the work that I'm presenting today, we are thinking of SAR as a range delay measurement tool. And we know there are basically 3 broad techniques that are being used. And one of the most common one is the interferometry or INSAR method, where we can obtain a phase difference that are able to resolve to sub-centimeter or even millimeter sensitivity. However, the problem of using INSAR is that there's an ambiguity issue where we have two-pay phase unwrapping requirement and also the requirement of high coherence for the images to be able to obtain a good INSAR resolution. So this is often used for built environment and like arid or like desert regions. The next technique, a broad technique, is called the coherent cross-correlation. But this also requires, in the same vein, that both images are sufficiently coherent so that we can, from there, extract the delay. But for our context in this presentation, we are talking about forests or vegetation in general, and this decorrelates very fast. And therefore, I'm going to use a technique called the incoherent cross-correlation, which basically does correlation using the intensity or the amplitude. And this is robust even where coherence is lost, and therefore is often used for large body motion like glacier, landslide, or things that move very fast since it decorrelates. This technique is also called pixel offset tracking. So all these 3 techniques should actually yield the same target to satellite delay once all the geometric, tidal, and atmospheric contributions are removed. It's just how sensitive they are to what we are seeing on the ground. So what we do in this work is we analyze SAR stats of time series worth of 6 years from 2016 all the way to 2022, and that comprise around 200 Sentinel-1 SAR images. And we perform ICC on a sliding window of 512 by 134 pixels, which amounts to around 1.6 by 1.9 kilometers in ground swath. And for each image, we generate a range delay reference to the same image. So in our case, we always use the middle image of the time acquisition. For example, in the 6 years, we use the image of the third year to be the reference point. What this requires is also that every image is properly done for its corrections so that they are co-registered well. And this registration includes using precise orbit imaging geometry and DEM, correcting for troposphere using ERA5, ionosphere using the TEC map, solid Earth type using geophysical model, and finally, we remove large-scale ground deformation from GNSS measurements, so that at the end of the day, our residual on arid or like dry land, it should be in centimeter level. And this is validated with a site at the Turkey-Iran border, where we see over arid cover land, it shows only residual noise of a few centimeters around the 0 point. So this confirms that our method of model-based correction is working, and there's no residual atmosphere or tectonics left. And what we will see in the next slide and the results will be most probably vegetation-driven. And this is our result over the Bulgaria forest, which is in Romania. We see that the Bulgaria forest shows this kind of oscillatory motion when we do ICC over the entire scene, and average spatially. So we see this plus minus 20 centimeter oscillation, which amounts to around 40 centimeter peak to peak in the whole seasonal cycle, and it's riding on a 3 centimeter per year trend upwards. And over here, I inverted the shifts so that the minimum happens in the delay. Minimum delay happens in the summer because I want to correlate this to a physical phenomenon, which I will explain later. And therefore, it made more sense to look at this in the inverted way. Yeah, so when we see the summer, which is around July period, it is a point where the phase center of the backscatter is closest to the satellite line of sight. Yeah, and also I overlay this with a mean coherence plot, and we see that around the center reference image is where it's the most correlated, as we know. But as time passes, either direction, the coherence drops, as we know, because of temporal decorrelation. And therefore, what we are seeing here, this oscillation is not related into any coherence-based methods. And also, finally, I overlay this with this sinusoid oscillation. I know it's not the best curve fitting because, as you can see, this oscillation is not really sinusoid but a double sigmoid because of the phrenology idea. But then with a sinusoid, we can better extract characteristics for assessment, like the amplitude, the trend, and also the phase, the temporal phase, which will show when the peak happens. I also double-checked this with a 2D version. So we see if we have a ICC oscillation of around 20 centimeters, this should amount to around 7 fringes in the interferogram. But over the vegetated area, we see that there's no interferogram. And what's left of fringes, what's left is only the atmospheric turbulence because of the decorrelation that we would expect. So what we did is we extracted the amplitude, the trend, and the phase, but converted into month of year so that it's easier to understand, and compare it to land cover classes and tree cover class from the Copernicus database. And we see that the amplitude of the oscillation and the trend correlates largely with the forest classes, like the broadleaf and the needleleaf class. And so we see at the top right hand and also the bottom, where the forests are present, they show strong amplitude and trend as well. Also, another point to note is the date of year maximum, which is like the temporal phase, are all uniform across all the tree-related classes because they are all from the same climatic cycle, which is the Bulgaria forest. Another thing interesting is we see when the land cover is showing the broadleaf, it's much stronger at the amplitude oscillation, and the needleleaf is stronger for the trend, as seen over here. Yeah. So with this, we also realize there's different characteristics that we can be mapping, can be done using this technique. So I analyze this further by breaking down into a box plot to better understand what each class can be seen. And we first analyze the urban build-up class, where it shows zero trend, meaning the corrections are done properly and nothing is moving. But on the other hand, for all the forest classes, like the broadleaf and the needleleaf, they show a large amplitude and trend. In particular, the deciduous broadleaf is showing the largest in oscillation, while the needleleaf is showing the larger secular trend per year. And in comparison, the vegetation and agriculture is showing much lesser and smaller effects than the trees. And the physical explanation I will mention later is because of the tree height and also the canopy idea. Another thing that I did is to overlay this 6-year range oscillation into a single plot so that it's easier to analyze them. And I also did trended it so that it's only showing the amplitude change in the shifts. And we see for all the vegetation class, there's this spring peaking phenomenon happening around May region, where suddenly the shifts change from the negative to a much larger positive. And in particular, the deciduous broadleaf class shows the largest change in this. I also check it against the forest height and tree cover to understand further what is this phenomenon that we are looking at. And it's interesting to see that as amplitude and trend, they increase with more tree cover and more forest height or tree height. Therefore, with a denser and taller tree, this phenomenon is showing up much stronger, and therefore leading to a larger range shift in the phase center. This, of course, is not the perfect correlation, as we know that there's other possibilities that are affecting this phenomenon, but we know that now it's related to the tree height and density. Next, I also check between the descending and ascending passes. So we can see in this map, the right side shows the descending pass, but it's the common pixels among both swaths, so that we can compare that one-to-one. And we can see that the descending pass, which is the morning pass, has a stronger change in the oscillation compared to the ascending pass on the left. And I think this is because of the vegetation water content in the morning that will soon be gone by evapotranspiration by the end of the day. And therefore, this change will reduce when we look at the ascending pass. Also, I check the polarization and also the choice of reference image. So in this 1-year data set output, we see that among the same reference point plot, which is the 15 Jan black line, and also the red line, the choice of VH shows a stronger change in the range shift compared to the VV. And this is understandable because cross-pole is more sensitive to vegetation structure. On the other hand, I checked the reference image where we choose one is the January, one is the September reference point, which is between the red and orange graphs. We show that it's largely invariant to the choice of the reference image that we choose. This is also done to assess in the whole wide region over 1,500 Sentinel-1 images to see what are we looking at when we talk about the amplitude and trend. We see that this stacks, even though it initially was built for tectonic monitoring, we analyze it for forests using the invariant cross-correlation method. And we see the forest regions are showing seasonal trend and also cyclic oscillation, while the arid and urban areas, which is the desert in the middle, are remaining flat globally. The more interesting thing is the date of year maximum, which is the temporal phase. We see that it helps to track the local climate, where the northern temperate peaks are around the orange region, which is around July, while the southern hemisphere peaks around January, which is around the summer on the other side of the Earth. Yeah, so it's also interesting, we see the tropics happen around September, while the equatorial forest basically has no idea of seasonality, but only the trend exists. So this sort of validate that what we are looking is not only in one forest, but can be applied to the whole Earth and its phenomenon. So what this could be, one proposal that we think could be possible is this two-coupled seasonal mechanism that's resulting in what we are seeing in this oscillation. So one factor of it is the structural change, where there is a leaf-on canopy during summer. You add biomass and scatterers to the top of the canopy, and therefore the phase center will migrate upwards. Together with that, there's this idea of a change in dielectric, because during summer, the tree and the leaves and the branches require water, and so they extract more water into the top of the canopy, and therefore the backscatter will increase in that section, and therefore the phase center will reweight even further. And with that, that's why we are looking at this change in oscillation between the winter and the summer season that is causing this phase center change. And why INSA and coherent-based method are not able to see this is because this displacement of the coherent scatterer only show up as a decorrelation when we use coherent method. And therefore, what we are looking at is probably a phase center shift. Of course, I also looked at some preliminarily, some phenomena in S-band, L-band as well. So for S-band, using Terasa X of 2-year SAR stack, we see a similar kind of idea where the oscillations have happened and the peaking is around May period. But we see that it's only the deciduous broadleaf class that is mainly showing this, while the other classes are a bit jumbled because of the idea of S-band probably is looking more at the canopy change instead of the water content across the whole tree. I also look at it in the spatial sense, where we see the same climatic variation across the forest, and also the idea that there's amplitude and also trend in these classes. For the L-band, this effect is not detected preliminarily. Of course, more study must be done, but we believe it's because the L-band penetrates the canopy, and therefore the return is mostly from the ground or trunk level bounce. And with that, we think this phenomenon attributes more to the canopy or tree branches than soil moisture. So this is a conclusion of my work. We validated this technique over urban and desert scene and make sure that it is no noise. And but then on the other hand, during forest or vegetated area, we see there's this oscillation happening. And we attribute it to the movement of the phase center across the season, which is strong as C and S-band, but absent the L-band and coherent-based methods. And we also validate it globally with hemispheric phase consistency. And so possible applications include forest phenology monitoring, biomass tree structure estimation, ecosystem carbon studies, and vegetation moisture monitoring. And the next steps includes quantifying this signal with physical parameters, and also integrate multi-frequency and interferometric methods to constrain the scattering process. And with that, thank you all for your attention, and feel free to email me if you have any ideas for collaboration or questions. Yes, thank you.
Do we have any questions in the audience? Thank you very much. So you said you didn't get this effect at Elban at all. You did not see any change?
Yeah, for our 1 year data set, it's not visible. Like, there's no oscillatory trend. It's just a downward slope. And yeah, that's all.
So what you're observing is mainly the water cycle, no?
Yes. Okay. I mean, for C-band, it's probably the water cycle and the canopy structure change. It's a coupled mechanism, something like that. Yeah.
Maybe you will be happy with the biomass data because we see many effects related to the water.
Maybe, but I don't know whether the structure change is playing more role in this oscillation than the water or vice versa. So it will
The thing is
depend.
that you will never have this time series.
Yeah.
Okay.
Yeah, that's true.
Have to make more hypotheses.
Yes.
Any other comment? Thank you very much.
Thank you.
I think that now with this, we can close this session.
We have also the round table.
Yes.
Yeah.
We have the round table, but together with our friends from the volcanoes,
Yeah.
I think.
We can also invite our colleagues.
Yes.
Yeah.
There are two volcanoes and then
okay.
went to the mapping.
Okay.
Because otherwise it'll get very crowded. So,
Yes, thank you.
so it would be more logical. Because I don't know if we have chairs here. Okay. For the volcanoes. It will be a short.
Maybe we are 3 minutes early, so we could wait for the...
Okay, and give them people time to, okay, that's makes logic. Good. Bene.
Do we have our colleagues from the first mapping session? We have Zibi. Perfect.
Perhaps 5 minutes. Ecco. Want to sit down? Put some chairs there? You prefer? Okay. It's better to.
Because we have more mic order.
She handles the upper road. Okay. You need help?
You know, you do. Yeah.
Okay, you're here and she's there. There's so not that many people, so I suppose we can cover it up. It's a lot of. Yeah, but too.
Hello. Hello. This is like roundtable discussion.
Okay. So it's like to discuss whatever has
Okay.
been discussed.
Okay. People
Or presented, yes. So it's just that there's like nobody. We give them, so I think it was.
People are coming to join the session. Okay. So there will be more people. After a few minutes, we will start.
Okay. So should I go back up?
Yeah, you can go. Just sit and chill. Because in this session, people have opinions, suggestions.
Okay.
We just talk about the stuff.
Yes, so lots of running for us.
Yeah,
I guess.
yes.
Okay. Yeah, that's fine.
And sometimes they don't have, so.
Okay. Yeah. So I'll go back up.
Ladies and gentlemen, let's start this discussion. We prepared 2 seed questions from the first session, but I don't, maybe they can, but this was not volcanoes from thematic mapping. Yes, yeah. So in fact 3, because in the first part of this thematic mapping session, we have quite a mixture of different thematic mappings. But there was one thing that was common for many presentations, that was the issue with soil moisture. And the question is that we developed together with Barbara, what is the current breakthrough in methodology using INSAR? Could it be already converted in the future new ESA provided product or Copernicus product? Maybe somebody can comment on that? I think there is not much people attending this.
Maybe I can make one comment. Yeah, yesterday there were many presentations about the, I'm here, sorry, about this phase triplets technique where they see incoherencies and phase anomalies. And today we had a presentation about using these phases, using an analysis in terms of volume light scattering when you have phase which oscillates, and they could map moisture with it. It could be an alternative or at least a complement. So this phase triplet can also be related to tomographic-like processing, like INSAR processing. And I think it's something which should be favored because both approaches lead to this famous phase estimate. And at the end, the techniques are not so far one from the other, so the convergence could be encouraged at different frequencies, of course. I mean, this is at least what we saw from the presentation of, I think, Giovanni.
Yeah.
It was very convincing and it's very different in terms of formalism compared to what is normally done with the phase triplets. Worth noting it.
The second one?
Yeah, the second one, what was it? Yeah, about the transferability of found methods from local scale to more regional or global scale. But I think if now more people are present from the last session, it's more a topic of like forest, and I'm not sure if you have any seed questions to ask, if we don't get a discussion going.
Yeah, I think the second question also is valid for the forest site estimation. We don't have, I mean, always having quite, I mean, benchmark data set. Nowadays you see AI is becoming more and more popular and really super effective. So we need the data and benchmark data set. Maybe, I mean, it's some things that ESA can consider to support the community with benchmark data set. I saw in the morning one presentation by Irena on the airborne campaigns for the soil moisture. I think we need more probably.
We heard also this presentation from DLR where they showed this. It was hard to transfer. I mean, it could work. Sometimes it works, sometimes it doesn't work. It depends on maybe things we don't know yet today. We still have to understand. Should we put an effort on this? I mean, it was very interesting that automatic technique sometimes. What should we change to have to improve the fitting score?
Yeah, from my understanding, from the deep learning side, let's say, it's really a matter of training data. And what I showed, right, was like the very first experiment I did for the PhD. It's basically, it was kind of to set up a threshold of, okay, just take a model and apply it elsewhere. What is the worst performance I can expect? Of course, this is not, let's say, the right approach to do it, also if we want to scale globally, but at least we have a lower bound for performance. And from the performance side, I agree that we should have some benchmark which are globally spread for the community. I mean, for the community-wise should be adapted to benchmark our product, because otherwise it's impossible, let's say, to say which product is better or which product works better on a given condition or field. And what I'm working on right now, it's really trying to select in a more careful way without just throwing everything I have in the model during the learning thing, the learning, let's say, yeah, the learning period, but trying to select data that are really informative because of some conditions, vegetation or whatever. So it's more kind of trying to not just throw whatever we have inside, but carefully select what we want the network to catch.
I think your message was very clear. If you increase the size of the data set, you don't necessarily improve the performance at the end.
Or let's say if you don't have like a benchmark, you can also show that you that you are fine with performance, but in the end, if you take like case by case, rare domains just breaks this robustness.
Should we make a recommendation about furthering the access to, this the initiative called GeoTrees? GeoTrees is a network of people not managing forests, but at least measuring forests. I mean, forestry people, they know they are responsible for generally quite large areas all over the world, and now they're together in a network, and they plan to make available their data in terms of elevation, AGBs.
Yeah, that's true, and we are also working on a project for with biomass and deep learning for the ABGD estimation. And this GeoTrees provides, let's say, a global valid benchmark, let's say, European-wise at least.
I think it would be a nice way to try and separately to tune the training all over the world with some data that are available, should be available to everybody, I think.
That's
recommend this. Maybe one last point concerning forest and the vegetation. We saw today the difference between people who are using large enough baselines, others were using currently available zero baseline systems, and we're trying to extract information to characterize forests. And the current trend seems to be like going for zero baseline systems to have a systematic acquisitions with the Roselle and others. Should we, for forest working, for people trying to analyze natural volumes, this is a nightmare. And we recommend really the development of companion missions that would be really cheap and would provide incomparable information for people working on volumes. I think it's the right place to do it. If we want to do this recommendation, we need to do it at Fringe or ESA or Paulin's conferences.
Yeah, I think also many of that applications and algorithms we will further develop it together with Harmony mission.
Yeah, you're right, at different bands. At L-band with Roselle, Harmony will provide something, for sure, but Roselle, I don't know, the development of a company mission is not something acted yet. It could be a good way to ask for it. So I take it as a yes. As a yes reply.
I don't know if there is any more. Please feel free to raise your comments. Any, scientific or even technical gaps that you feel that ESA should address it in the next couple of years, but that should prioritized by the ESA. Now we see any gaps that you see currently in your applications, technical gaps, anything. I think from my perspective now is a really multi-frequency. Yeah, in case of its forest area, or even in, if you see deformation, of course, the wavelengths is really important, even in case of the INSAR or tomographic deformation.
And we saw it many times today, yeah? People combining X-band data, X-band estimates with lower frequencies. Yes.
Yeah, please.
I'll just say that I'm not a forest person, but you might want to talk to Marco Lavale, who's the NISAR deputy project scientist, and he's here, because there's a NASA is developing, it's in the early stages, a mission called STV, Surface Topography Vegetation. And one of the concepts, at least that Marco is trying to push, would be some kind of SAR co-flyer to get multi-baseline interferometry to go after vegetation structures. So I don't know if that's of interest.
Yeah, this is something which is really needed and very important for the community, so we'll mention it.
There's also strong LiDAR advocacy within it, so we don't know if it's going to be radar or LiDAR or some combination.
Yeah, yeah. Oh, yeah. Can we move the slides back onto the volcano ones?
There's the volcano crowd.
It's perfect.
Okay. So I hand.
Not many. It's going to be a small group discussion. Yeah. Okay, I think this is going to be a pretty small group discussion. I can't see too many volcano people in the audience, but that's fine. We were asked to prepare some questions to get the discussion going. So I guess the overall objective here is this one: which recommendation does the community give to ESA in this INSAR domain regarding targeted R&D activities in the short and medium term and in preparation for future missions, particularly Roselle, Harmony, and Sentinel-1 Next Generation? So the first one, what is observationally missing to get some of the outstanding questions in volcano science? Any suggestions? What are we missing? What do we need? Oh.
Well, for those who know me, I work in high latitude and mid latitude volcanoes, and we are still missing a lot of temporal resolution in those regions, and I don't know if ESA can do something with that, because the ESA satellites work on a C-band, and in regions like that where you have snow half of the year with C-band, there is pretty much nothing that you can do. So I consider that the Roselle, it could be a huge contribution to have a better imaging in those regions, but that will be in some years. I can't remember how many years, maybe 4 or 5 from now. But listening to a lot of talks from the glacier community who are using the one-day pairs for measuring ice deformation, maybe we can make a better use of those one-day interferogram for places, I don't know, Kilauea. Kilauea is it's the most studied volcano on Earth, but because it is doing so much things with this, like almost 50 lava fountains going on, maybe we can observe something about the lava fountain dynamics using these one-day pairs that Sentinel-C and D are acquiring until I think the end of the month. So that's one thing that we are still missing. And the other problem, which is not really related to the mission themselves, are the atmospheric corrections. We are still having issues with that all over the Earth. So I don't know if ESA can do something about that, but at least it's something that should keep us working as a volcano community.
Yeah, Sang-ho?
I always thought, especially after I moved to Southeast Asia, I always thought in INSAR volcano community, there's a elephant in the room, which is explosive volcanoes. We've always talked about this nice deformation. It's obviously a larger signal, easy target for INSAR, but explosive volcanoes are the ones that causes fatality and air traffic disruption and all that. It has a enormous impact, but everybody know that we have relatively limited capability to observe it, very localized. So it's related to number 2, your question number 2. So I want to second that, the importance of it. Also in Southeast Asia, there are a lot more exposure to that kind of volcanoes.
Yeah, we actually did a review recently of the use of Sentinel-1, and we found that for the explosive eruptions, lots of them hadn't been covered by Sentinel-1, but a lot of them that had, people are now using the backscatter products to study explosive eruptions, and that seems to be a really growing field in volcano science for these really big explosive eruptions.
When you say backscatter, you mean amplitude-based analysis, like Elliot's? Okay.
Yeah.
But Sang-ho, when you say, I guess I'm not clear what the gap is. You think there needs to be higher temporal sampling? Are you talking about measuring deformation? That's very transient? Are you talking about, we've seen talks on domes and how they can be very dynamic, so maybe repeat topography. What exactly do you?
Right. I guess I started from the frustration of the community on the ground. And then if I backtrack to technology, I guess that would connect to first observation, yes. And then what kind of observation would be more relevant? We saw high-res, like Capella or other amplitude analysis was useful to measure the dome growth. Because dome growth inevitably comes with temporal decorrelation, then you might as well go with like tandem X-based topography differencing. We also saw Tomosar that captures the elevation difference. So we can be a little creative to see if there's a elevation difference using non-INSAR based approach. But we should identify a lot of explosive volcanoes have very localized deformation, if any.
Right.
So, yeah, Sang-ho, are you talking about precursory deformation, which doesn't cause topographic change, or are you talking about once the explosion has happened, in which case you can use topographic change and backscatter amplitude, whatever, to track those?
Well, dome growth is pre-eruptive,
Well, no,
precursory.
it's eruptive, right? A dome is
Yeah,
is an eruptive.
right.
Eruptive
Before
and
explosion.
yeah.
Yes, yeah.
It's always impact oriented. Yeah.
Yes, okay, all right. I'm just trying to be clear. Yeah, thank you.
Thank you.
I mean, to your question a little bit, I would say that, so I think we've seen a number of talks. Delphine gave it, I mean, Piton de la Fournaise is a great example of getting, what, 1 or 2 per day, something like, you know, incredibly high temporal sampling. And of course, that's a very specialized location. But so I think in highly dynamic situations, or I remember years ago when the group in Potsdam had something at Colima. Somebody talked about Colima today as well. But they were able to see from Terrace RX, they got a serendipitous 11-day, and they could see very shallow, I think, inflation right before it exploded or something. And so that was a lucky case, but often volcanoes like Colima had been thought of in the past as, oh, these kind of open conduit systems, they don't really deform. Instead, in that, at least in that one case, they saw that, yes, it deformed, but in a very short time scale. And so, you know, so one thing would be higher temporal sampling. And then for what you're saying about domes and stuff, I think that gets more to a topography or topography change observation. And so that gets, I mean, that feeds into the thing I said about STV earlier. So, and I'm not trying to plug STV, but it's just a matter of, I think, more about defining it in terms of what is the observation you really want, as opposed to, I mean, I think a lot of people are very good about taking SAR amplitude or doing things that are kind of working with what we have as opposed to what we really want. And I know with, like, for example, with STV, we're making recommendations to NASA, and one of the concepts is, gee, maybe you need a high altitude, long endurance capability that's you know, just observing constantly over a particular site for some period of time, if a volcano is in rest, for example. Or you could have constellations of small sats or whatnot. But so I think that maybe, at least in my opinion, the key thing is to tell the space agencies what we want in terms of an observation, and then whether or not they can get creative and achieve that, that's another story, right? So.
Yeah. So I think we've seen some great examples looking at topographic change. Now, Harmony is going to be doing that, of course. A little segue, but of course it's limited to Sentinel, so it's going to be doing it every 12 days. So Arthur showed some nice examples of what we can do with very high resolution data, but there seems to me still there's a gap, right? You can do it with very high temporal and spatial resolution data if you have the right DM in advance and things like this. Or should we be looking at bistatic missions like Harmony, which are going to be limited to Sentinel resolution as well? So we're going to have 30-meter resolution with that.
But it's a precursor. I mean, it's a test mission fundamentally, right? So
no, officially.
No, not anymore.
We're on record here.
Okay.
It's a science mission.
Okay.
That is its primary focus.
Okay.
But yes, of course, we do hope there will be more Harmony-like missions, multi-static missions. Okay. Yeah.
But I like the co-flyer concept overall. If in a sense that that could be an investment that an agency makes to not build a new system, but basically build a co-flyer to an existing one. So SDV context, like ESA could invest by, instead of building their own mission, to build a co-flyer to something like whatever the SDV concept would be, to allow for topographic mapping, or a co-flyer to NISAR, or NASA could build a co-flyer to Roselle or whatever, to, in addition to the repeat displacements, to have the repeat topography information.
Yeah. I think with Harmony, one thing we've learned is you do need synchronization with the illuminator. So I think it is much easier to do that internally within a space agency, for ESA to build co-flyers with Sentinel, for NASA to build co-flyers, or ISRO to build co-flyers with NISAR, for example. But it does seem like if it works well on Harmony, then it seems like that's something we would want more frequently than once every 12 days at 30-meter resolution, yes. That could be a recommendation. Elliot wants to say something.
Oh, sorry. No, I mean...
Arthur has actually got the microphone.
Yeah, no, it was just to bounce about like what Juliette just said about Harmony.
Oh, sorry.
So, yeah, I think... I mean, we shouldn't choose between radar kilometry or bistatic INSAR, because they are both, they are complementary and they don't use the same part of the data. So another effort should be made on how we compare DEMs from multi-sensors and multi-techniques, because this is also something we need to think of. Like, we will never, I mean, I don't know, but it's not for the short term, having a one-day basis DEM time series from the same sensor with the same technique. And so we should also think of how can you compare two very different DEMs and know that the differences you're measuring, some are due to differences in sensors, but some are also due to actual changes. So I guess, yes, there is something to do also on the methodology about comparing DEMs, because sometimes vertical referencing is not the same. Vertical precision also depends on the technique you're using, on the steepness of the slope, and so on. So it's not very useful for space agencies, but it's more for us as a community also to think about multi-techniques DEM time series.
Yeah, that's great. I'm a bit aware of time. We've talked a lot about topography. Should we try and look at some of these others? Data continuity between missions and historical missions. I think we ought to make a strong recommendation, and Francisco would like to say something.
Just to put an example about this specific question, in the 3 times during the 6 months of this year, I published a paper with all MBSAT data that no one had ever looked. I gave a new grad student MBSAT data to start working on his PhD, and I processed MBSAT data for a proposal. So there is still a lot of old MBSAT data, and maybe for ERS2, that probably has never been looked on detail, and even after it was acquired 15, 20, 25 years ago, I really think it should be more available.
Okay. Yeah, so availability of legacy data is an important thing, but I think this question is really asking about continuity of those legacy missions, those legacy modes. So for example, Sentinel-1G will have a Sentinel first generation mode. I think that's what the question's getting at.
It has both components in it, but yes, it also.
But I think availability of legacy data is something that we can definitely put in the recommendations. Absolutely, yes. Yeah. So as actually, it's a good example, right? So we are still using this old data and combining it with new data to make 30, 40-year-long time histories. Do we need continuity of some kind of data? Do we need exact continuity of modes?
I would say that's nice to have, but not, I mean, I guess I misheard. I thought I heard that the Sentinel-1, the next generation or whatever it's called, would not be interferable with old
won't
data.
be, but it's going
to be in the same geometry, so you could...
Yes, but it is going to have some kind of legacy mode so it can interoperate with Harmony, so the time series can overlap with the same But I think that it's not the primary mode. It's like a secondary mode, a backup mode.
Okay.
So I guess as long as the missions have a decent time series, if we have a different set of parameters every 6 months, it's going to be chaos. But provided we have each time series lasts for 10 years or something, then we're fine with no continuity. Yeah?
No.
Sang Ho would like to say something?
That's an interesting question. I guess we could potentially start with what's underlying physics that require us to have continuous observations. For example, we need some basic understanding and modeling tool. Like for example, in tectonics community, they have interseismic, viscoelastic, very long, and earthquake cycling model. Like it's like hundreds of years of earthquake cycle, and we know that strain accumulation needs to be monitored for a long time. Are there such thing in volcano community that we're concerned and can model with long history of time, same type of data?
But, so I think that's the point. So we can put together long time histories from different satellites, as long as there is some kind of overlap between them, particularly with Sentinel-1 next generation, which is going to be in the same orbit. So it'll have the same pointing directions and everything. I think the real question is, do we need it to have the same, do we need it to be interferable between new missions and old missions? And I think the answer I'm hearing is that's not particularly important.
Well, whether it's important, I think it's a nice to have, but otherwise there are other ways of kind of integrating time series to a certain extent. But I would get to what Sang-Ho was saying. I think fundamentally when dealing with heterogeneous, it's a little bit like if you're modeling and you're trying to create 3D displacements which have issues because of the temporal offsets depending on how dynamic your behavior is, versus simply keeping everything in line of sight and let your model sort it out in terms of, fit whatever your model parameters are, having them best fit all the data in whatever look geometry. And so kind of to what you're saying, if it was a long process, maybe you've got a dynamic volcano model that has some decaying exponential recharge that goes to some kind of long time series, you might just use the model that best fits all the data and not worried about necessarily specifically trying to connect the time series as a continuous data set.
I feel like in relative sense, compared to tectonics community, we always feel like, I always feel like our interest is more localized in space, exactly where they are, and time. So smaller space-time window. So if I were to choose, I would go for more frequent observations over long, consistent timing. If there are new missions that can achieve more frequent acquisitions, then I would vote for that over interferability between old and new mission.
I would just add that there are cases now that we start to have 20, 30, whatever years it gets kind of murky in the past, but as you start to get longer time series of behavior, of course, we start to look at processes that become, in some cases, inter-event behavior. If you take something like Sierra Negra, you've got, of course, long GPS. The INSAR is a bit more scattered, but you can build these long time series, but invariably you're then having to do so with different missions, and somehow we find a way to do that. So it is, the long time series are opening up studies of longer term behavior, and at the same time, when it comes to events, of course, we want to have very high temporal sampling. So.
Great. Speaking of Sierra Negra, it's been observed for a long time, and if I imagine, do you want to interfere with the old mission, or do you want to capture transient behavior of 2018 intrusion, which was crazy? Spatial detail was like unexpected. I'd rather like to be able to capture that snapshot of deformation.
So maybe that leads into the next conversation, is because if you'd had like an ISI constellation at the same time, where you get like over certain sites daily repeats to, you know, when there's an activity going on, that could be really enlightening, in addition to sort of the background Sentinel-1 and
Yeah,
NICE
be able to targeted deployment and then start tasking frequently over that area.
Yeah, and so there is the supersites activity, right, where but I think it doesn't include currently ISI and some of the new space constellations that can provide this kind of temporal sampling. And it might be really interesting to engage with you know, ISI's, Capellas, Umbras of the world to see if they would be willing for certain sites to provide that kind of sampling for just the sake of studying their contribution to this kind of research.
I mean, Arthur may be able to say more, but my understanding is they are quite willing to contribute, but on a case-by-case basis. They're not engaging with CEOS supersites type mechanisms at the moment. Is that fair? Mm-hmm.
Yeah.
Yeah?
Yeah.
But this could be a recommendation to really push these existing international mechanisms to incorporate the commercial data providers.
Maybe before we totally move away from the sort of the data continuity, it would be nice if we have a recommendation to, I still believe that, and Sung Ho said that too, that there's, or Francisco said it, it's like the NVSATs and the ERSs, they are very useful to the community. I think they are underutilized, mostly because of the data aren't really fully available. You have to sort of order them. They are not as discoverable as some of the other data sets. I think it wouldn't be a lot of effort for ESA to actually just consistently process all the ERS SOCs and make them discoverable in some established way. Like we are now used to the Sci-Hub and how we find Sentinel-1. Maybe there's a way of co-locating those so that you can discover the entire C-band time series that ESA provides for this kind of research. I think that could be really useful.
I believe there is an effort, but I don't know the details about how far they went with this in terms of processing. Yeah.
Is a bit of an elephant in the room that the data's, what we've learned from the commercial satellites is actually that they're most useful when they're in the same orbit. So like Cosmos SkyMed has 4 satellites in the same orbit, and that's why it's becoming really useful. We could have 6 new missions, but if they're in 6 different orbits, we are in the same position that we're really in today. And actually the fact that they're in the same orbit is what gives us the advantage that we're looking for.
The high repeats, yeah, absolutely. Yeah.
I would make, you know, back to the, I mean, when we're talking about the commercial data, I mean, super sites is one thing, but I think one thing that's a big challenge, and I don't know how we can overcome it, but I think that we need to, it would be great if, and I don't want to say anyone or any observatory, but if there could be a really rapid, easy way for whichever company or whatnot to task satellites like, oh, there's a volcano that's not one of the known suspects that becomes a super site, but something that's, you know, and wherever it's in some remote location, nobody studies it, but there's some, maybe you have good information that it's entering on a rest date or something. You say, okay, now if we could just capture it at high temporal sampling, you know, maybe we'll catch some really great transient behavior. But I don't know how, you know, that could be set up in a way that would be some kind of interface that would be easily accessible by a variety of people, scientists, observatories, etc.
Arthur also wants to say something.
I mean, you can go.
Oh, I was just, whenever we were asked, especially scientists being asked by space agency, what do you want? and we always pause like, we want everything, but we don't want to sound like too outlandish or even stupid. So you want to start thinking about what is the incremental achievement that they can realistically make that would that we can get the most out of it. What's the biggest bang for the buck? And when we identify, oh, that's really low-hanging fruits, then we get excited. And I just experienced that by talking to Francisco. I didn't know ERS data, NVSET data are not available at Vertex. NVSET not. Look, wait, everybody loves Vertex. I love Vertex. It's very reliable. And whenever you do something, and once you found that interface doesn't work once, then that interface dramatically reduced the reliability, and you stop using it. Vertex was very reliable so far, and what does it take? So my question, what does it take to make ERS and NVSET, all the historical data set, be made at Vertex? I think that's quite achievable. We're not asking for new mission here.
Yeah, and I think, so we talked with Isa about this already, so like making, so one interest is to make data discoverable jointly, no matter where they are located. And so there's some data, sort of metadata stuff that needs to be done. Stack catalogs for these data sets would accomplish that. This would allow, for instance, ESA on their platform to show NICER data and make them discoverable for folks that are familiar with their platform. And we could at the same time take ESA's like Roselle catalog or biomass catalog or the ERS catalog and make them accessible through Vertex. That is the cheap thing to do. It's hard to sort of replicate the archive because archiving data costs money, but making them discoverable is achievable. And so that could be a recommendation, to just work together between the agencies to make data sets mutually discoverable for the communities that have, places where they go to discover these data sets.
I think this is a Vertex issue, not an ESA issue. All ESA's data is open and available for anybody to get. So I think this is a problem with Vertex needing to load up the MVSAT data, not a recommendation for ESA.
So it's Fran's problem.
Well, yeah, I mean, it is still, because we have to agree on sort of joint catalogs so that we can mutually discover them. So there is a little technical piece in it. But,
yeah, but I think that they do have, ESA do have their own tools where you can access and process the MVSAT data.
Yeah.
So it's not that it doesn't exist, it just doesn't exist in this format. I'm kind of aware that we're 15 minutes past our time. Oh. Yes. I think we need to wrap up. Does anyone have... Oh, Arthur has been waiting.
I had just one last point on the commercial constellations.
Yeah.
So instead of asking ESA to design new missions that are inspired by their way of acquiring data to have high responsiveness, as it's written here, we could also integrate them into the data acquisition plan. And instead of investing money in designing new missions, and it will take time and also efforts, we could also ask ESA for money for quotas to get some data there, because what they are looking are customers, and ESA could provide permanent, can become a permanent customer of those constellations. So yeah, I mean, it's only asking for money, and I don't know if it's very scientifically interesting for the space agency, but at least for the monitoring part, it would be nice, because with quotas, we could think of a strategy to really, we know we have, I don't know how tens of Capella space image per year, how tens of Umbra, and then we could think of a real strategy instead of a case-by-case approach, which sometimes is a bit hard to make because it relies only on individuals and not on a space agency or something more formal.
Yeah, I think this is a clear recommendation. I'm not sure about the money, but the clear recommendation that some access would be really good. I think we should wrap up. I think there's one thing I wanted to say, this last question. I guess if anyone has anything really burning to say about it, please email one of the three of us. And the one thing that's missing that Philippe asked me to add after I'd uploaded the slides was it should also include digital twins. So if anyone wants to say about digital twins, but I think we should wrap up.
Yeah, so if you look at the questions, if you have any other comments, email us. There's going to be a summary session on Friday where we report out all your feedback.
Yep. Okay.
Thanks.